I am starting the recording. I can't hear you, Mia.
Can you please mute?
Yeah, sure.
Thank you. Well, 3:30, so I think we can start. Welcome everybody to the second session of the Beyond the Standard Model session, ICHEP 2020. I'm Mia Tosi. I'm from the University of Padova, and the co-conveners of the Beyond the Standard Model session are, as you well known, Mikhail Malinsky, Alexander Souza, and Yu Nakahama. Few reminders before the start of this session. I invite the speaker to turn on their video. And for the audience, I suggest to make a question at the end of the talk or make use of the Mattermost channel. I'm going to remind the link in the Zoom chat in a few minutes from now. The schedule is pretty tight, therefore let's start with the first speaker of this session, Georgios Zeleus, who will talk about Beyond the Standard Model physics at the LCC and the FCC-EH. Please.
Hey, can you hear me?
Yes, very well.
Okay, I'm sharing the screen. Can you see it?
Yes, thank you.
Okay, well, so thank you for this opportunity to talk about Beyond Standard Model physics at the LHEC and FCC-EH. There will be more future EP collider studies and other physics, a few talks at this conference. So, let's see. Okay, the LHEC is a collider with a 60 dB electron beam produced in an energy recovery LINAC on the 7 TeV LHC beam and the center of mass energy 1.35 TeV. The FCC-EH has the same 60 TeV beam with 50 TeV proton beam from the FCC of it, and square root of S is 3.5 TeV. And we expect about 100 photobarn. So the LHEC will run concurrently with the LHC for some period of time, and more details can be found in these references. And there will be more talks on this. Okay, so BSM physics at EP colliders is of course limited by the center of mass energy, but there are some major advantages. It has a low background, very low pi left, and much improved PDFs. And for this, I invite you to see the talk yesterday from Claire Quinlan and the polarized electron beam. So these BSM constraints can be obtained from precision measurements, and possibly new physics can be explored in challenging regions of phase space not available at EP colliders. The conceptual design report was published in 2012, and the new updated version is being submitted imminently. So there's a rich program of BSM physics, but for the short time allocated, I have selected a few topics highlighted here. Some other topics will be presented in other talks on this conference as shown here. Okay, I shall start with leptoquarks. This is the BSM topic which first comes to mind for EP colliders. Leptoquarks are both lepton and baryon quantum numbers and are predicted in various models of high energy physics. They are classified according to their representation in the standard model gauge groups, and as you can see in this table, they can be scalar or vector. In the last few years, they have gained in theoretical interest as they have been proposed as a solution to the so-called B anomalies, which are excesses or deficiencies in ratios of ranging ratios with different generations, leading to question lepton universality. And some of these leptoquarks, in particular the S3, the R2, for example, could explain these discrepancies with the standard model predictions, as shown in this table. There are also leptoquarks like the R2 allow for the possibility of the right-handed neutrinos. So because leptoquarks are produced resonantly in the S channel, the production is very sensitive to the coupling of the leptoquark EQ coupling, which can be significantly higher than electromagnetic strength, which would be about 0.3. This is in contrast to the LHC, where the main production process is pair production by the strong interaction. This plot shows, for example, an estimate of the sensitivity of the coupling as a function of the leptoquark mass. Also, if the leptoquark is observed, then the properties can be measured with very high sensitivity. This has been shown in the LHC CDR. The fermion number, the charge, the spin, the chiral structure can be studied from, for example, the asymmetry, comparing electron and positron projection. If the leptoquark mass is very high, much higher than the center of mass energy of the collider, the process is interpreted as a contact interaction, and the scale of contact interaction is estimated at about 65 TeV at LHC. At PP colliders, as I mentioned, the scalar leptoquark production is pair production and is independent of the coupling. So the constraints are quite strong. They are model independent because they don't depend on the coupling. They're usually, however, presented as a function of the branching ratio to the charge lepton, which is, of course, related to various couplings in some way. And there could be some regions of phase space when the branching ratios are low, which remain unexplored. And at FCCEH, we have enough energy to go beyond the limits at LHC. The plot at the right shows the product of couplings B mu, S mu, which are consistent with the B anomaly in this blue band, and the expected limits of present and future colliders, high luminosity, high energy, and FCCHH. So at EP colliders, there's a chance that we could have improved the coupling to the extent the region which can be explored. Okay, another topic which has been studied at EP colliders is the search for charged Higgs. Dedicated talk on the Higgs will be given later today by Peter Klein, but here I concentrate on the charged Higgs and the Georgi-Machacek model. This is a model which is built to satisfy explicitly custodial symmetry at tree level. It is an extension of the Higgs sector with higher isospin multiplets, including the bidoublet and two triplets. And the physical states include a quintuplet, which does not couple to fermions and which can therefore only be produced by vector boson fusion. There are two basic parameters, the mass and the mixing angle. And an analysis of the singly charged Higgs with fast detector simulation and BDT and the test for the detector simulation gives a 95% estimate of the sensitivity in this blue band here compared to the present limit at LHC. The doubly charged Higgs is also being studied at EP colliders. The plots here show limits at FCCHH without and with electron polarization. And the black curve is the present CMS limit, which is better than a single charged Higgs because there is very low background at LHC for same sign leptons. I just list here other searches for charged Higgs. The two Higgs doublet model with flavor violation for flavor violating decays into quarks. The process benefits from a relatively clean environment and also predicts interesting sensitivity. Okay. Some studies have been performed looking at the possibility to observe a heavy neutrino in the process of EP to lepton plus 3 jets. So very briefly, this can be observed either by displaced vertex if assuming the tracking and displacement resolution, if there's a very low mixing, the neutrino can be long-lived. And assuming these parameters, we can see that we have a considerable improvement in the mixing angle that can be explored. This is in the case of electron, and this is where the lepton is a muon. This can be interpreted in an effective Lagrangian parameterization, and the limits can be placed on the couplings. We can question also that one can discriminate between sector and vector effective interaction. And there was also a study of the left-right symmetric model where in fact the lepton is charged, is a plus. And there the sensitivity depends on the charge misidentification, but it can cover regions inaccessible in other searches. So turning now to supersymmetry, one region of phase space which is not easily accessible at the LHC is a so-called compressed scenario, where the NLSP, chargino, neutralino, or lepton is close in mass to the LSP. It is difficult to investigate at the LHC because the decay products are soft and they are buried in a high level of background. A case study here assumes a mass difference of 35 GeV and essentially degenerate electroneutrinos. The lepton being at 35 GeV will be produced on shell, as in this Feynman diagram. The mass limits obtained in these curves, you can see at FCCH are comparable or somewhat better than what can be hoped to obtain at the high luminosity LHC. More studies on supersymmetry, similar search for light Higgs zeros in a compressed spectrum, but this time in a decoupled scenarios, that is where heavy lepton produced, which is not produced on shell, and therefore the cross-section is lower. So we have a somewhat poor limit. R parity violation, it was shown that the couplings of R parity violation can be considerably improved for very low spot-on mass in this case of this kind of coupling. Another study searches for prompt decays of low mass gluinos. This is a region which is difficult to study at PP colliders. 95% exclusion limit can be obtained at LHEC with one inverse autobarn. So it's difficult at LHC colliders because there's a lot of noise and multiple subjets. And of course, in general, we could have an improved interpretation of the LHC mass limits, for example, for gluinos, given very good partial distribution function uncertainties that can be obtained at the LHEC. Okay, the thin environment and low pileup at PP colliders also allow for it to search for long-lived.
2 minutes left.
So, so we have the possibility to look for displaced vertices, and this showed large impact parameter single track or displaced vertices. It's difficult to predict how well the background can be controlled, but depending on the number of single or doubly displaced vertices observed, here we see 10 or 100, we have a significant improvement on the reach that can be obtained at the LHEC. The black lines here show the limits of disappearing track searches at high luminosity LHC. And similarly for FCC-HH. The search for long-lived particles can also apply for an analysis of scalars which can mix with the standard model Higgs and decay to BB. The black curves show the limits at FCC at LHC. The red and blue is PP colliders, and the black curves, we see that we have some improvement in the cover. And the plot at the bottom right gives the constraints on the mixing angle as a function of mass. So in the next slide, we look at signals for a dark sector, a dark photon, which is arise from an additional U1 with weak kinematical mixing of U1 and hypercharge. Weak mixing and low mass imply long lifetime, and again, the displaced vertex. And we see that we can improve considerably the limits here. And for the axion particles, which are pseudoscalar particles, generally of low mass, the plot on the right shows that there is some unexplored phase space that can be covered. So to put this in context, we see the complementarity of EP colliders for the dark sectors. We see the dark scalar mixing with the Higgs boson. This is a contribution of EP colliders. Axion-like particles coupled to photons reach this region of phase space. And here we see the limits on spin-independent WIMP nucleon coupling based on the Higgs portal model with Majorana on the top, or scalar dark matter. And this is taken from the briefing book of European Strategy Update. So as a conclusion, thanks to the clean environment and low pileup, EP colliders offer a rich program of DSM physics, mostly on precision measurements, and can probe sensitive regions of phase space difficult to access at LHC. And at higher energies of the FCC HH, we have more phase space to explore. Thank you.
Thanks a lot. Other questions or comments? Let me see on the napkins as well. I have a very brief question. Can you please remind me the plans or time schedule for the FCC EH and AEC?
There was a schedule, I'm not 100% sure, but it is certainly going to be ready before. It can be ready at the end of the high luminosity LHC, I believe, maybe soon. You can have more information on the references.
It belongs even after the European strategy, right? Even the EH collider belongs to the famous.
Well, of course, it's not approved yet, but it is planned that it would be one of the first detectors one of the first accelerators to be ready before the other colliders, so it can be ready before.
Thanks. If there are no other questions, I think we can move to the second speaker of the session, Aaron Finberg. Precession frequency analysis of the E989 neon G-2 experiments round 1 dataset. Please.
Hi, thank you. Can you see my slides?
Yes, thank you.
Okay, I'm Aaron. I'm going to talk about the precession frequency analysis in the Fermilab G-2 experiment. In the Fermilab G-2 experiment, we are seeking to measure the muon's magnetic anomaly, A mu, which is defined as the muon G factor -2/2. This quantity is interesting for us to measure because it can be predicted very precisely using the standard model. And this prediction is achieved by summing all of these contributing Feynman diagrams with the leading contribution is QED. And then we also are sensitive to hadronic vacuum polarization and hadronic light by light. And we're also sensitive to the electroweak contributions to G-2. In support of our experiment, I'd like to mention that there's recently been a full reevaluation of the standard model value, which is released by the muon G-2 theory initiative. So I would invite all to follow this link at your leisure to see the status of the standard model evaluation. There's been a lot of work recently, especially towards addressing the non-perturbative contributions, which are the dominant source of uncertainty in the standard model calculation. A mu has been measured very precisely by the Brookhaven experiment at 540 parts per billion. This result was released in 2004. And this result is in tension with the standard model prediction at the level of 3.7 sigma. And this discrepancy has persisted ever since Brookhaven released their result more than 10 years ago. You can see on this graph the evolution of standard model estimates, where the changes are driven by these hadronic contributions I mentioned, and then the deviation here between the Brookhaven measurement and the prediction. This deviation, of course, could be an indication of new physics. So in the Fermilab experiment, we're trying to measure this with improved precision, and we're hoping to reduce the uncertainty by a factor of 4 to get to 140 parts per billion. That's our ultimate goal. As of now, we've completed 3 data runs. So on the left side here, we have run 1, 2, and 3, which are in the past, and we have 2 more runs planned in the future, which we expect to bring us to our ultimate goal. But my talk today is going to focus on run 1 from 2018, which is similar in size to the entire Brookhaven data set. So we're hoping our run 1 analysis will be competitive or slightly better than the Brookhaven measurement. The way that we measure a mu is by observing muons in a magnetic storage ring, and specifically observing what we call the anomalous precession. So if you place a charged particle, let's say a muon, in a uniform magnetic field, it will travel in a circle, and its spin will also precess. If the G factor were exactly equal to 2, the spin would rotate at the same rate as the momentum, as shown in this graph on the left. On the other hand, in reality, G is slightly larger than 2. And so you have the spin precess slightly faster than the momentum is rotating, as shown in this graph on the right. And after 30 orbits, the spin will make 1 full rotation relative to the momentum. So we call this phenomenon anomalous precession, and the frequency is called omega A. And it's essentially the rate of change of this angle between the momentum and the spin of the muon. And this is what we're trying to measure. And this quantity, omega A, is proportional to A mu, not G. It's actually proportional to G minus 2, which is what allows us to measure A mu so precisely, provided we have an equally precise measurement of the magnetic field. And these equations, they apply to a motion entirely perpendicular to a perfectly uniform field, which is of course not the case in our experiment, where there are slight deviations from that ideal scenario, and we apply corrections to these equations for those deviations. This is a photograph of our experiment at Fermilab. We store 3.1 GeV positive muons in this storage ring, which has about a 7-meter radius. We store the muons in a series of fills where we inject a big bunch of muons, and then we observe them rotating and decaying for 700 microseconds. And we do this over and over to accumulate our statistics. We measure the magnetic field using proton NMR. So we measure the magnetic field in terms of the precession frequency of free protons. I won't talk too much about this or any more about this. There was a presentation yesterday by Saskia Charity that covered this measurement in detail. Once we have the anomalous precession frequency omega A and the proton precession frequency omega P, we can take a ratio omega A over omega P, and that is related to A mu when combined with these other highly precisely known constants. So what we are really measuring is this frequency ratio omega A over omega P, and then we combine with these other quantities to obtain A mu. And all of these other quantities are known so precisely relative to what we can measure that they don't contribute to the final uncertainty of our reported number. The way that we actually measure this precession frequency is through observing the positrons that are emitted when muons decay in our storage ring. We have 24 electromagnetic calorimeters placed around the inner circumference of our storage ring. When a muon decays, the positron that's emitted will have less energy and curl inwards to hit one of our calorimeters, and the path length will be dependent upon the energy of the positron. And when you look at the positron energy spectrum in the lab frame, you see that the actual shape of this spectrum depends on the relative direction between the spin and the momentum. And the reason for that is the parity violating nature of the muon decay. So by observing the modulation of the energy spectrum, we can arrive at omega A. Essentially, the period of this modulation is what we're trying to measure. And it's entirely through looking at the decay products. Shown here is essentially a binned calorimeter data. So different energy bins going up vertically, and on the x-axis is time. And when you look in each energy bin, you see essentially these oscillations that are coming from this modulation of the energy spectrum. And the period of these modulations is what we're trying to measure. And you can parameterize this behavior using this distribution I'm showing on the right, where there's a normalization and an asymmetry as a function of energy, and all energy, and this is positron energy. And all of the bins are going to be oscillating at this precession frequency. In practice, we generally collapse this 2D distribution into a 1D time spectrum by applying energy dependent weights in such a way as to optimize the statistical power of the measurement to obtain this one-dimensional time spectrum that we then fit. And in the most ideal case, you can fit this with a 5-parameter function that includes this normalization, the decay lifetime, and overall asymmetry, which depends on the weights you're using, and then a phase and the precession frequency, which is the only parameter that we're actually interested in this fit. This measurement in practice is complicated by a number of effects that can bias the frequency that we extract, particularly effects that cause a time dependence of the phase. And when I'm talking about time, I mean time in the muon field between when the muons are first injected and when we stop measuring the decays. The reason for this, you can see, is if you imagine this phase is time dependent, any linear part of this time dependence is completely indistinguishable from a different frequency. So if we have something that causes the observed phase to change in the fill, we're going to bias our extracted frequency. And this is going to be a systematic error. So we have to account for all the effects that can lead to such a bias. Typical effects include beam distortion. So if the shape of the stored beam is changing over time, losses of muons from the ring. Some of these effects were discussed in a presentation yesterday by Sudeshna Ganguly. And then rate-dependent reconstruction. So detector effects can cause, for example, the time reconstruction to be biased over the fill. All of these are very dangerous, and we have to account for them in the analysis, and a lot of our effort goes into that. Just to further illustrate that, if we take our calorimeter spectrum and we fit it with this 5-parameter function that I mentioned, and then we look at the residuals in the time domain and the frequency domain, we see that there's a lot of residual oscillation. You can also see a slow component of this. Essentially, the fit is completely inadequate in describing the data. Many of these peaks in the frequency spectrum of the residuals are related to beam oscillations. So these are characteristic frequencies at which the beam oscillates inside of our storage ring. So those beam dynamics have to be understood very well to adequately fit our data in this experiment. To help us understand these beam oscillations, we employ tracking detectors. So we have tracking stations placed in front of our calorimeters. 2 calorimeters feature tracking stations. And these can extrapolate positrons back to the decay vertex. And in doing so, we can build up a distribution of where the muons are actually living inside of our ring. So this is an example of a transverse slice of the storage region and where the muons are as seen by the trackers. And if you look at this binned in time, you can see that the distribution is oscillating under the influence of our electrostatic quadrupoles and magnetic field. And then we can use the trackers to understand how the beam moves and make sure we understand the frequencies and the lifetimes at which these oscillations decohere. and we use that information when we fit our data. I'll also mention two important detector effects in the experiment. One is calorimeter gain. So calorimeter gain can be perturbed by the large flash that's observed when the beam is injected initially. So we have a laser calibration system that tracks the gain over time in fill. On the x-axis here is the time relative to when the muons are injected, and this dashed line is when we start our fit. And we measure with a dedicated laser calibration system how the gain is perturbed. And we need to keep this under control at the 10 to the minus 3 level to meet our systematic error goals. Another very important effect is pileup. So you can see in this diagram, if you imagine two low energy positrons being emitted at the same time and being detected such that their sum is the same as this single, the sum of their energies is the same as this single high energy positron. If you can't resolve them, you'll place this pair of particles in the bin for a high energy positron. But since their path length is different, they'll have the wrong phase. And the prevalence of this occurring is time dependent because it goes like the rate squared. And we have evidence that we do see pileup. The muons we're storing are 3.1 GeV. So we expect our positron energy spectrum to have a sharp endpoint at 3.1 GeV here. But what we actually measure has this tail going out at high energies from unresolved pairs. So we have to apply correction for pileup, which is extracted from the data itself. So this green curve is our pileup correction, and you see it describes this non-physical high energy tail very well. And we apply this correction before we build the histograms that we use to fit for omega A. After we have applied all these corrections and we do our fits, we no longer see residual oscillations or slow drifts in our fit residuals. So that gives us confidence that we're understanding the behavior of our data very well. And this is an example of a fit to a subset of the run one data. The current status of this analysis is that we've completed all of the run one precession frequency analysis, and this has been done by 6 independent groups. Some of the groups did multiple analyses, treating the data slightly differently. So each of these bands on this plot is an analysis or a separate analysis of the same data. We've imposed a requirement that all the analyzers use the same data quality cuts. So all of these points are going to be very highly correlated. So the red points and the blue points are all the same data used, just treated differently. And each of them is one of sub data set from run one. So we divided run one into 4 sub data sets. But what's different between these analyses is that each group independently developed corrections for these beam dynamics effects I mentioned, and also for the detector effects. There are independently developed pileup corrections, independently developed reconstructions, so 2 completely separate reconstructions built from the ground up. These analyses were conducted blind relative to each other. This plot shows a relative software unblinding between all these analyses, although there's still a global blinding, so we don't know how what this means in actual frequency, but the common blinding allows us to compare between analyses. And we find full agreement between all of these analyses within their lab statistical differences. And having completed the run one analysis, we can say that we expect 430 parts per billion statistical uncertainty for our run one result in the G-2 experiment. And we can compare this to the Brookhaven combined result, which had a 460 parts per billion statistical uncertainty. So we're at least, we've exceeded BNL in terms of the statistics of our measurement. We're still working on finalizing this systematics. The next steps are to complete the combination of the independent analyses. We're working to fully understand all the correlations between our analyses so we can do a global combination between all those results I showed on the previous slide. We'd like to finalize the systematic corrections. So there's some, like I mentioned earlier, we have to correct for deviations from the ideal case of perfectly uniform fields and motion entirely perpendicular to them, and similar things, which Sudeshna talked about yesterday. So I invite you to look at her presentation. We have to combine the omega A and B field measurements. So this is something that is being finalized as we speak. And we're targeting fall 2020 for a final unblinding and publication of the Run 1 result. So thank you very much.
Thanks a lot, Aaron, for this very nice and clear presentation. Are there questions? May I have a very quick one, because as we said, we have a tight schedule. Actually, two. So the level of control of the B field, even in this summary slide, you mentioned the importance of the measurement of the B field. Can you highlight the level of control and uncertainty on the B measurement you have?
Well, so the control, it has to be, what we need to know is the magnetic field averaged over the distribution of the muons in our storage ring. And that has to be controlled in terms of, it has to be known to a similar precision as this just goes directly into our systematic error budget. So for Run 1, we're aiming at something like 100 parts per billion knowledge of that average field. However, the field itself can move a bit from sub-data set to sub-data set because we're continually calibrating it and continually monitoring it. But the precision at which we can measure it is enough that we can ultimately know this average field at the 100 parts per billion level.
Thanks. And very last, even if I'm afraid you will need some time to explain, in your pile-up profile, you have in slide 18, there is a structure which is not totally clear to me.
You mean the green curve?
Exactly.
So what's happening here, this is the absolute value of the pile-up spectrum. So what's happening is it changes sign here, because what we're trying to do is correct for what we want to arrive at, what we would have seen if we had basically perfect time resolution and we could resolve all pairs of pulses. When we don't resolve a pair, what happens is we gain a false count at high energy and we lose two counts that we should have seen at low energy. So that means the pile-up correction can be negative, and this is where it changes sign.
I see. Okay. Thanks a lot. If there are no other questions or comments, I remind you we can use Mattermost channel. Thanks again, Aaron. We need to move on to Meghna Acharya. Still on the G-2 measurement, search for CPT and Lorentz violation effects in the muon G-2 experiment formula. Please.
Hi, everyone. I'm Meghna, and I'm going to talk about the CPT and Lorentz violation tests with the muon G-2 experiment at Fermilab. So as Aaron already mentioned, the primary goal of the experiment is to measure the anomalous magnetic moment, a mu of the muons. And in order to calculate or evaluate the anomalous magnetic moment, we experimentally measure two frequencies, two quantities. One is the anomalous precession frequency, omega A, which comes from the spin precession frequency of the muon and the cyclotron frequency. And the other quantity that we measure with the NMR techniques is the magnetic field. And so Aaron has already given a very, very nice overview of the frequency extraction techniques that we use in our experiment. So I'm going to focus on the CPT and Lorentz violation aspect of the experiment. And for the CPT and Lorentz violation tests, we use the ratio of these two frequencies, the omega A, the anomalous precession frequency, and the proton precession frequency, and try to look for the signal. So now we know that minimal standard model of particle physics is CPT and Lorentz invariant, but there are standard model extensions that allow for CPT and Lorentz violations. And for the muon sector, the standard model extension Lagrangian has 5 CPT Lorentz violating terms, and using the muon G-2 experiment, we can look for the BK coefficients. So we are sensitive to the BK coefficients using the muon G-2 experimental data. So for the CPT and Lorentz violating signatures, we can look for 2 such signatures using the G-2 experimental data. One is the sidereal oscillation search in R, where R is basically the ratio of omega A over omega P, and these 2 numbers coming directly from our experimental measurements. And the other signal is basically the difference between the properties of the particle and the antiparticle. Now, for this talk, I'm going to focus on the sidereal oscillation search. And in order to look for the sidereal signal in our data, we use 2 techniques. One is the spectral analysis technique, and the other one is to perform a multi-parameter fit to the ratio of omega A over omega P. And this gives us information about the transverse component of the BK coefficients that I showed you in my last slide. So for the first half of my talk, I'm going to focus on simulation studies. So in the first half, whatever you show, the plots are from simulated data, pseudo data. And then I show you a preliminary study on our run-2 data set, subset of our run-2 data. So first, what I do is for the simulation studies and tests, we start with the time distribution of R with an average value of this number and a data point uncertainty of about 20 ppm. So here what you see is a time distribution of R generated with where the data points are generated with Monte Carlo simulation, and over a duration of 2 months. And in order to go from the time domain to the frequency domain to look for the oscillation signal, the sidereal oscillation signal, we use, as I mentioned, 2 techniques. One is the Lomskargel test, which is a spectral analysis technique and which is uniquely designed for unequally spaced data and widely used in astronomical observations. So basically what Lomskargel test gives us is it's more like an FFT-like approach, where it will give us the frequency where the peak appears if there is a significant oscillation in the data that we are looking for. And the multi-parameter fit, on the other hand, is a 4-parameter fit to the data, where R of t, the ratio, is basically the ratio of omega A over omega P. And this gives us directly the amplitude of the signal if there is a signal present in the data. So basically R is constant with respect to time, where which is denoted here by C0. And compared with this constant, the amplitude of possible oscillation signal is very, very small. And the oscillation amplitude is obtained by a least square fit of R to this 4-parameter function. Now focusing on the Lomskargel test. So basically what we do is we scan for frequencies over frequency range and calculate the Lomb power, the spectral power at each frequency within a given range of frequencies. So this Lomb power, or the spectral power, is a measure of the statistical significance of a signal at a given frequency. Now, our point of interest when we go from the time domain to the frequency domain is the sidereal frequency. And you can, as you can see in here, so this is with pseudo data. And you see that at the sidereal frequency, there is no significant signal peak present. So basically, the higher the Lomb power, the more significant the periodic signal will be at a particular frequency. And now if we plot the Lomb power distribution, or the spectral power distribution, you see that it is following an exponential distribution, and which tells us that there is, which confirms that there is no statistically significant signal present in the data. And this comes from the statistical properties of the Lomskargel test or the algorithm. So now if we look at an ensemble of simulated data groups, we can determine the range of maximum Lomb power values that we would expect for a given data set with no signal. So for example, the lower left plot shows a maximum Lomb power, you can see, of about 10 for one data set. Now, when we perform the analysis for 10,000 such cases, so each time we start with a time distribution of pseudo data, we perform the Lomskargel test, we look at the Lomb power distribution, and we get the maximum Lomb power value. And for we repeat the procedure for 10,000 such cases, and then that gives us the upper right plot. The upper right plot shows that for 10,000 simulated data groups, the range of maximum values extend to a spectral power of 15. So for example, if there's no signal present in your data, then at max you can have a Lomb power of 15 and no higher than that. So that you can see from this plot where we added a 10 ppm signal to the pseudo data. Oops, sorry. And you can see that the Lomb power distribution now stretches out to a much higher value. And this is indicative of a significant signal peak being present. I mean, significant signal, oscillation signal present in the data. Now, going back to the case where we had 10,000 simulated data groups. Now, if we plot the frequency position of maximum Lomb power for each of these 10,000 cases, then we see that we see a flat distribution showing that the algorithm is not biased toward any frequency across the search range that we are using. Now moving on to the to test the sensitivity, like how sensitive our Lomskargel test is as a function of the signal amplitude. So how big the oscillation amplitude has to be in order for the algorithm to be able to significantly detect it. So in here, what we did was we started with the same pseudo data, but in here we kept adding signals at the sidereal frequency into the data, and then perform the Lomskargel test and see if we can, if it can detect the signal or not. So in the first case, you see when we added a 1 ppm signal, the algorithm, I mean, we don't see anything at the sidereal frequency. But as we kept increasing the amplitude of the signal, the more and more prominent the peak becomes at the sidereal frequency. So from this study, we conclude that so if the data point uncertainty is around 20 ppm, then in order for the algorithm to be able to detect a signal significantly, the oscillation signal has to have an amplitude of greater than 5 ppm or so. Now moving on to the data analysis. So here what I show you is a preliminary subset of run-to data analysis plots. And so the first plot shows you the frequency, omega A frequency, over a period of 13 or 14 days of data taking. So here each point is basically a 1 hour period of run duration. And from that 1 hour period of run duration, we extract the omega A frequency, like Aaron mentioned, using the 5 parameter fit. And the second plot shows you the proton precession frequency over the same duration of time. So once we have the omega A and omega P values, we have our ingredient ready for looking for the oscillation signal, the sidereal oscillation search. So we take the ratio of omega A over omega P for 13 days of data taking, and then we perform the multi-parameter fit and the Lomskargel test on our run-to subset of the data. So here, what I show you is the when the we perform the multi-parameter fit, and in here what we did was first we just performed a constant fit. So which means we performed just to C0, a fit to C0, and then we added the oscillation amplitude term to that. And what we saw that in those two cases, the chi-squared over NDF doesn't change. So which confirms that there is no significant oscillation going on in the data. Also in here in the left plots, what I show you is a case oscillation period scan, where what we do is we step through, in this scan we step through different values of T0, keeping all other parameters constant. And basically the motivation here is to search for time structure other than the sidereal period. And so you can see that in here also, from here there is no oscillation going on at the sidereal period, or for that matter any of the period or slash frequencies scanned. So you can see that there is no global minima in the unnormalized chi-squared of the fit over the period scan that we performed. Now, moving on to applying the Lomskargel test on our run-2 subset of the data, you see again, so now that you're familiar with this plot, the spectral analysis plot, you see that at the sidereal frequency, again, our point of interest, we do not see anything significant going on, or any significant peak present in the data from the spectral analysis. And so when we look at the Lomb power for at the sidereal frequency, it is around 0.83, so which is very, 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 very small in terms of the significance level in order for any signal to be present in the data. So to give you a feel about the Lomb power, so you can see when the Lomb power is 6, then the significance level or the confidence level is around 4.8%. So you can imagine when the Lomb power is 0.83, it's like very, 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 very small. This also is confirmed when we plot the Lomb power distribution, like I showed you in the simulation studies. So when we plot the Lomb power distribution, you can again see that it is following an exponential decay. So which also confirms that there is no signal present, no significant signal present in the subset of data that we looked at. So in order to summarize, so from the simulation studies, it shows that the sensitivity scales with the uncertainty of R, the ratio of omega A over omega P. And Fermilab Muon G-2 experiment aims for a 4-fold improvement of limits on the CPT Lorentz violating parameters. And as per as the run-2 analysis goes, it's a small subset of run-2 data that we performed the analysis on so far. And so there's nothing significant at the sidereal frequency, but stay tuned for the full run-2 analysis. And also, so this will be the first time that we perform an annual variation search for the signal with the ratio using the G-2, Muon G-2 data at Fermilab. And that's it from me. I would like to thank the organizers and everyone involved in organizing a successful ICHEP meeting.
Thanks a lot, Magna. Are there questions?
Can I have one question?
Please.
Yeah, this is Takashi Higuchi from Osaka University. In this long power analysis, if there is an oscillating signal, do you also see harmonics like in the FFT?
Yes, I mean it depends on the nature of the signal. But so when I added the oscillation amplitude to the simulated data, so the range I was looking for, I did not see any harmonics present.
Okay.
Yeah.
So what I mean is, so if there is, for example, oscillation at the sidereal frequency in the data of the long power spectrum, do you see peaks at harmonic frequency? That's what I mean. As certain sort of artificial effect on the analysis, do you see?
I suspect that we will. But yeah, that's a good point. Yeah, I suspect that we will.
Okay, I see. Thanks.
There is one other question on the Mattermost channel. Let me read it very quickly. So the first one is if you are taking into account the Lucas-Ware effect in the power spectra corrected.
Sorry, what?
If you are taking into account the Lucas-Ware effect.
I haven't.
And the other question is in slide 12, why does the confidence level intervals not follow the power spectrum and are simply straight lines? I think you can answer directly in the Mattermost because I'm sorry, I think we are in late.
Okay, I'll get back.
I invite you to discuss on the Mattermost channel. Okay. Thank you. Then the next talk, so thanks again, Magna. And the next talk by Giovanni Abbiendi from Bologna, status of mu-Ni experiment.
Hello. Let me share. Okay, so, sorry. Okay, I will tell you the status of the mu-Ni experiment. Can you hear me, please? Do you hear me?
Yes, we do.
Okay, sorry. Okay, so I benefit from the introduction from the previous talk on G-2, so I have not much to add. Simply that the muon anomalous magnetic moment is really one of the best observables to test in a stringent way the theory, the standard model, because it is so precisely measured and also very precisely calculable in the standard model. So as I said, the main contribution to the theory uncertainty is the hadronic contribution, the leading order one, actually, that is basically the vacuum polarization. Its relative uncertainty is 0.35 to 0.6%, and this is not calculable by perturbative QCD. So the standard way to obtain this contribution is to use the plus and minus two hadrons cross sections with this dispersive relation that is an integral over them. And you can see the difficulty in the low energy region to have this integral due to the resonances and the threshold effects. So in alternative, there are also lattice QCD calculations that are more and more progressing. So the status, as you heard, is that there is a 3 to 4 sigma discrepancy between the data and the theory. And so there is a possibility to have new physics, although a recent lattice QCD paper claims there would be no discrepancy at all, but I have no time to describe this result. Sorry. So as you heard, the new Fermilab experiment is aiming to a reduction of the experimental error by a factor of 4. And consequently, the theories should be improving as well. And the mu-Ni experiment has been proposed exactly to help the theory prediction to improve. So what is this new approach? It is based on the space-like data. So using the the scattering interaction like scattering. I will see our case, but to measure the running of the QED coupling in the negative T domain, momentum transfer. And the difference is that in this case, the integral that is given here in this formula is a smooth integral that you can see here. So there are no peaks, and it's much easier in principle to have this contribution, although it's a tiny quantity. So in this delta alpha hadronic is a 1 per mil effect, and then this is not an easy task. So our proposal has been put out in this paper is to measure the elastic scattering of muons from a CERN beam of 150 GeV on atomic electrons of a fixed target with low Z, like beryllium or carbon. And from a precise measurement of the differential cross-section, determine the hadronic delta alpha. So here is a scheme in leading order of this idea. And the elastic scattering, of course, has many benefits. The kinematics is simple. And for example, there is a clear correlation between the outgoing angles of the electron and the muon that you see here, that make easy to reduce the backgrounds from inelastic or radiative events and to select the elastic scattering. And also the phase space that is covered with this proposal is 87% of the mu integral. So it's possible to have a smooth extrapolation to the full integral. So the layout of the detector that we are proposing has been described in this letter of intent that has been submitted to CERN last year. The concept of the detector is simple, although the challenge is to be able to keep the systematics at the level of the statistical error, because we need very high sensitivity, we need very large statistics, and then minimal distortions are tolerated on the outgoing trajectories of the electron and the muon within the material of the target, also small rate of radiative events. So we came to a proposal of a modular structure as depicted here. This would be one station, a structure of 40 independent such stations tracking the outgoing particles with a split target in total equivalent to 60 centimeters of beryllium. And at the end of the array, an electromagnetic calorimeter and a muon filter to help the identification and the rejection of background. So as you see the dimensions, one station is long 1 meter, and there is the target and the 3 tracking layers. And each station sees the incoming muon from the previous station that makes the tracking. And you can notice that the transverse size is just 10 centimeters. So this is one peculiar aspect. So basically, we cover the whole acceptance in just one sensor that is large enough. And this helps reducing many systematic errors. So the extraction of the hadronic running is easily displayed by taking ratios of the observed angular distributions and the theory prediction evaluated for just the leptonic running. So as I said, since the hadronic running is an effect of 1 per mil and the wanted precision is 1%, we need to measure the differential cross-section to 10 to the minus 5. That is really challenging. In the plots, it is shown an example toy experiment where you see muon angle on the left and the electron angle on the right, with the statistics corresponding to 3-year run, that is our nominal plan, and superimposed the fit, that is a template fit, obtaining the muon anomaly, actually with this value that you see, that is quite a good result, although this is poorly at the statistical level. So in the last years, we completed beam tests at CERN and many simulations based on GEANT. For example, in 2017, we studied the multiple Coulomb scattering on thin targets for low energy electrons, 10 to 20 GeV, and we published the results. You can see a plot here. The 2018 test beam is now, the analysis is ongoing, so we will have other results. I have no time to describe the simulations, but I mean, after all this work, we came to the choice of our basic detector, that is the CMS sensor used for the upgrade of the outer tracker of CMS. So this is described again in the letter of intent. And the characteristics of this sensor is that it is a large 10 by 10 centimeter square sensor of microstrip, silicon microstrips. Actually, they are two close by planes of strips. So it provides a track element like a stub, so-called, that helps suppressing the background. It has a good position resolution. And the main difference with respect to the LHC operation is that in our case, the signal is asynchronous, while in LHC, the sampling is dictated by the bunch crossing at 40 megahertz. So this is a non-trivial change, but it can be overcome with a specific configuration of the front-end chip. So here you see a drawing of a muon tracking station that has the target in front, then the three tracking detectors that are actually a couple of modules measuring X and Y with the orthogonal, orthogonal strips, the first and the third, and the middle one is rotated at 45 degrees to solve the ambiguities. We have stringent requests on the mechanical and thermal stability that has to be better than 10 microns. And the structure is made in INVAR for that. We need a cooling system and a tracking enclosure to guarantee the room temperature stabilized to 1 or 2 degrees. So next year we will have a test run in fall 2021. 3 weeks are allocated at the M2 beam line, CERN. Basically, it is upstream of the compass detector where there is a 40-meter space available. This is the configuration we will have at this test. So 2 tracking stations, as described, followed by a prototype calorimeter and a muon filter that here is not drawn. In front of it, another station without a target serving to track the incoming particles. So for us, it is very important. It has to confirm the detector design and the capability to sustain the rate. And we have to be able to control the systematics to the level that is desired. So after the commissioning, we will take data to measure the leptonic contribution to the running of alpha, that is like an intermediate step towards the final step of measuring the hadronic contribution. However, the expected sensitivity of this test is really quite good. So basically, in 1 week, we should get 5 inverse picobarn luminosity. That would be equivalent to 1 billion elastic scattering events. And with such statistics, this is the sensitivity that we can have on the measurement of the hadronic running of alpha. So actually, we would have initial sensitivity at the level of phi sigma, purely statistical level, but definitely we will have a sensitivity to the leptonic running that is 10 times larger than the hadronic. And we will study, as I said, the systematic effects that are crucial for our proposal, in particular the multiple Coulomb scattering. Here, this plot shows the effect of a flat error of 1% on the core width of the multiple scattering. So you can see that restricting to some fiducial region, actually the big effects due to the multiple scattering, to an error on it, can be tolerated and are not dominating the statistical error bars. Another important effect that we have to control is the beam energy scale. So we need to have an absolute calibration of the beam energy scale that is 150 GeV, at best than 3 MeV in one single station. And this can be reached in less than 1 week data taking with a full beam intensity. We have developed the methods to do so, and described in the letter of intent, and the plot shows what can be done with just 1 hour data taking in one station. So you see this gray area is the data uncertainty, and these histograms show the prediction of theory with a shifted beam energy. So you can see that 1 GeV, for example, is an enormous change that we will be able to spot even in less than 1 hour. And of course, then with more data, we can reach the goal, that is this one. So about the theory, there have been impressive progresses in the last years. The state of art is summarized in this report of the muon theory initiative. So I have no time to go through all these nice achievements, but let me say that there is even more to come in the next years, because we need excellent calculation at next to leading order plus resummation of the leading logarithmic terms. And this is the goal, and it will be reached in the next years. I just want to add that there are also studies of the possible contaminations of muon from new physics. And these two independent papers have clarified that muon is not vulnerable by possible new physics. So actually we will measure the hadronic contribution to the muon anomaly, the leading order term. So I am to the summary. So as I said, the muon experiment proposal is trying to help solving the long-standing puzzle of the muon G-2 with an alternative measurement of the theory contribution from the leading order hadronic component to the muon anomaly. It is done by measuring the elastic scattering of muons on electrons at the CERN beam with 150 GeV muons on atomic electrons. And it is competitive, the precision that can be reached, and it is completely independent and complementary to the other methods that now are usable. So we submitted the letter of intent to CERN last year, and CERN has recognized the fundamental interest and approved this test run to be carried out next year, which should verify the detector design and decide about the future, because if it will be satisfactory, we will proceed to the full-scale experiment foreseen in 2022-2024. So this is the end. Thanks. And this is the current muon collaboration that is still growing up. Thank you.
Thanks a lot, Giovanni. Are there super urgent questions? on this very interesting, intriguing new experiment proposal. If not, I invite you to use the Mattermost channel, and in addition I saw that apart Giovanni, as an expert on the experimental part, Massimo Passera is connected, who is one of the theoreticians behind. So in case, I think even we can profit from Massimo's presence here. So thanks again, Giovanni, and let's move to Svetlana Pfeiffer, SEAL G-2, so muon G-2 and scalar lepton quark mixing.
Thanks a lot. I'm just trying to get my screen. Do you see? Not yet. Is it okay now?
Please, if you can make the full screen.
Yes. Okay.
Thanks.
I would like to thank organizers for giving me this chance to talk online, although I would much more prefer to be in vicinity of Carlsbridge and see it after my talk. Okay, so my talk is containing, of course, motivation. I would a little bit remind you of standard model and new physics explanation, but I should skip that a lot because thanks to all other speakers that I got excellent introduction for my talk. Then I would go into the explaining discrepancy G-2 by lepton quarks. And then that will contain some phenomenological constraints. And also I would briefly mention what's happening for electron G-2. So basically everything that's here, it's in the first paper by 3 of us. And then I just briefly mentioned what we did quite recently. So as we know already, that the discrepancy between experimental and standard model anomalous muon magnetic moment is of this size. And if you just look here, there are enormous effort for 70 years to calculate all these corrections properly. And as we already heard, that the lattice is also doing a great advancement, and maybe we wouldn't talk about this discrepancy anymore. But we would need some time to clarify it, as well as on experimental side, we might get a little bit different result, hopefully. So the working hypothesis of my talk is that this discrepancy should be explained by new physics. That means that, just to remind you, that this new physics, what we need, is really very large comparing the electroweak contribution, which is of this order. So when we talk about new physics, explaining this discrepancy, we have to know that it's a huge, from point of view that standard model electroweak interaction gives that. So as we often do in theory, we first write the effective Lagrangian, which is of dimension 6 here. H is, of course, a Higgs field. And if you just plain game, putting that we can show that muon anomalous magnetic moment with discrepancy can be written in such a form. And but this right now unknown coefficient C should contain also loop factor, because it's a loop effect as you see it. And we can see that there is a possibility that new physics, if we got this form, is close to TeV scale. Of course, that one should consider it with cum grano salis, because this has to be specified. And it's just a game that in the case when we get, for example, top quark, if it's here, then in this case, scale of new physics can be much larger than in this case. Just keep it in mind. So, but when we talk about new physics in the loop here, one can have standard model fermion, new bosons, new fermions, and standard model bosons, new fermions, and new bosons. Of course, from a theory side, we always like, if we destroy standard model, just to have some simplicity, that it's only one of scalars, so one of new vectors instead of a plethora of new states. So we try to use scalar leptoquark in the loop and couple it to only quarks and leptons from the standard model. So we already saw some of that. If it comes to scalar leptoquarks, we systemize them using SU3 color, SU2 weak, and U1 of electroweak. And we can have these states. Of course, we have quantum numbers of quarks, but because of weak isospin, we can have a triplet, a doublet, and a singlet. Why it's important? Because then this gives us a possibility that we couple leptoquarks either to doublet of a standard model or to singlets of the standard model, depending really of the isospin of this state. Also, what's important is that here weak hypercharge is defined, introduced through electric charge, which is then I3 plus hypercharge. It could be 1/2, so one should know which convention has been used. So as you see here, just to remind you, that when we have this fermion number equal to -2, that then these leptoquark states in principle have also diquark couplings, and then they can cause proton to decay. Now let me come back to G-2 of muon. If we have only one scalar leptoquark, in order to get explanation, best would be that we have a scalar leptoquark, and then some heavy quark, for example, top. And then on the end of the day, we would get some chirality flip inside the loop from both diagrams. And that will give us possibility to explain it. And you see it, you see it from this Lagrangian, that we can have fermion number 0 or 2, and we can have these Lagrangians where scalar leptoquark couples to quarks and leptons, or quarks with a charge conjugated state and leptons. So if you use such a Lagrangian, one can write most general formula, which has one possibility m mu here. And you see that it comes only when we have one chirality of the leptoquark, either right-handed or left-handed chirality. But in the case where we have both chiralities, as you see here, then in this case, one can get enhancement of new physics contribution. So if we have product of two chiralities, then in the loop, then we can come to new physics of this form. So that means we can get an enhancement accounting the mass of the top quark in the loop. So basically from this table, only S1 and R2 can explain A mu in such a way that they have this chirality flip in the loop. And that means that they both can couple to both chiralities of muon. So that's why we end up with this explanation. But we were thinking in different way. Not all of leptoquarks has been used all these leptoquarks have been used for B meson phenomenology, for all other studies. So some of them are not having both chiralities. But one way of dealing with this problem is that if we, for example, have a S3, which is a triplet of SU2, has these three charge state, but the same charge is also with this S1 leptoquark, and this S1 leptoquark, they can really mix. So basically, experiment cannot say, is it from S3 or is it from singlet state? So this is very interesting because physical states can be subject of mixing. So which mixing we can have, S1 and S3. And then in the loop for G-2 is an up quark. And then if we have this S1 tilde and S3, that's mixing through for third state, then down quarks are in the loop. For these two lower cases, we can only explain neutrino masses, and they cannot explain this mixing, cannot explain G-2. So basically, if it comes to mixing of leptoquarks, then we can have all these three situations. So what did we learn? In principle, as you know very well, if we have mixing, then in this case, like we have mixing of neutrinos or mixing of kaons, what's relevant is that our states, physical states, are S plus and S minus if we have mixing of S3 and S1. And these two components mix through this angle zeta, but then we have a mass matrix which is not diagonal, so that these states are not on the mass shell. And then we introduce this mixing parameter omega, what we should see what's the origin of this. So basically, if we want to diagonalize this matrix, we get these two states on a mass shell, which depending on input masses in such a way here, and mixing angle is determined through the omega. So now we have to write down Lagrangians, which are responsible for mixing. So we have mixing through Higgs field of the standard model only, simplicity principle. And then we can have S1 and S3 mixed through such a way, and that's a psi parameter, which is relevant for us. And then we can mix S1 tilde and S3 and R2 tilde and R2. So mixing parameter omega is related to this psi, and of course we have condensation of the Higgs, so we get this vacuum expectation value of the standard model. So now you see that we put mixing of leptoquarks basically into this parameter psi related to omega. And now the point is, can we know something about psi? And what one can say that from oblique corrections from delta t parameters, basically that's when you have W's here, and you have one leptoquark which is from one with one isospin and the other one with another isospin, and one can study that and obtain that from this experimental value. If we try to see what's the fit coming from here, one can get information about this mixing parameter psi. So if we use LHC bound on mass of S3 and S1, it should be 1.6 TeV, about that. We can get psi that is 3.1 or 3.9, depending if we are on 1 or 2 sigma level. If we have splitting between these two states, that they are not the same, that's the lowest possible mass allowed by LHC, then we got psi, which is quite large. So naive perturbativity limit give us that it should be square root of 4 pi. So this is really larger than this naive perturbative limit. Another.
Sorry for interrupting you. You have 2 minutes left.
Okay, thank you. So another constraints are from Z, coming from Z. And we see that from LHC constraint, we get the glue and QQ into leptoquarks. And then by using this assumption, the branching ratios we decay into these states, we get constraints on the masses of leptoquarks what one can use. But we are generous on the safe side and use 1.6. So if top quark is in the loop, one gets these contributions, and then it means that we can determine Yukawa couplings. And here dark blue is 1 sigma region allowed by Z to dilepton, and LHC searches of proton-proton to mu-mu. So here is when we have different splitting between S1 and S3, and you see that currently it's allowed within 1 sigma that we have masses of both leptoquarks within LHC region. Then if it comes to B quark, we can have a mixing of R2 and R2 tilde. And in this case, mixing is a little bit different. But what you learn using the same bounds and is in previous case, we can only get explanation of G-2 at 2 sigma level. This not very dark blue, that's this region here. So it also similar situation is for S3 mixing the third component, and S1 tilde. In this case, we are again at the 2 sigma level. So for charm quark in the loop, unfortunately, it's a factor which is very important, that if you include the constraint coming from D0 to mu mu, we only can get, due to this value from the mu, marginal improvement of A mu. So basically tell us it cannot work very well. If we put now question due to the results from 2080 that the electron anomalous magnetic moment is also differs from experimental value from the standard model value, but the sign is opposite. The question is it possible to explain both using the same new physics model? We can study that, and one can write this, and on the first side, one can see that maybe we can be able to realize this sign. But unfortunately, what happens, we have constraint from G minus 2, from mu to E gamma, and we get in this formula such a dependence on delta A squared and delta mu squared. And if we derive minimum value of this branching ratio, we can really see that it's even independent in such a way from leptoquark masses. And it can be only 10 to minus 4 comparing mag result 10 to minus 13. So that tells us that either such a model cannot work if we use the same model for both. So we went through all these variations, and mu to E gamma is really such a strong constraint that we cannot use the same model in this case. So that means the only solution is that electron anomalous magnetic moment is explained by one leptoquark and the other one by another leptoquark, but not with the same one at the same time. So I'm coming to my end, and this is that it's important that we get new measurements. 2 light scalar leptoquarks can resolve existing discrepancy, but with only top quark in the loop if we are happy with 1 sigma solution. With 2 sigma solution, others can work, but it's not that convincing like this case. So basically, if we go to electron and muon simultaneous explanation by single leptoquarks or by mixing, then we see that a strong bind comes from mu to E gamma. So thanks again.
Thanks a lot, Svetlana. Other questions or comments? Mattermost, I do not see any. If not, thanks again, Svetlana, and we move on to probing CP violation in photon-photon interaction by Inbar Savorai from Weizmann Institute. Inbar, we can see you.
Hello?
Yes, ciao.
Okay.
Thanks.
Okay, so thank you very much for the introduction. So today I'd like to talk about 2 proposals for probing CP violating photon-photon interactions using cavities. So our first motivation for considering photon-photon interactions is, of course, the fact that lightsabers are really cool and we can't have lightsabers without photons interacting with themselves. The second motivation is, of course, beyond the standard model physics. So in particular in models like the relaxion, so the relaxion can interact with the photons both through its mixing with the Higgs and through its axionic nature. So it can generate 3-level photon-photon interactions. At the level of the EFT, we can get operators of the form FF squared, which is CP conserving, FF tilde squared, which is also CP conserving. And since the relaxion is not a CP eigenstate, it has both a CP even and a CP odd coupling to the photon. We can also get a CP violating coupling of FF tilde. So within the standard model, we know that photon-photon interactions are forbidden at tree level. However, they can be generated at the loop level through the electron loop that you can see here. Going below the mass of the electron at the level of the EFT, we can contract this loop to a point and get the Euler-Heisenberg Lagrangian, which is of the form of ff squared and ff tilde squared. So on top of this loop suppression, specifically CP violating photon-photon interactions are significantly suppressed within the standard model to about 20 orders of magnitude. So as a result, CP violating photon-photon interactions could be a good probe of beyond the standard model of physics, since they're essentially background free from the standard model of physics. Okay, so as for the experimental constraints, so we know that photon-photon interactions or light-by-light scattering has been observed at the LHC, and there's still some room for new physics there. However, at low energies, photon-photon interactions have not been observed yet, although they have been searched for. Now when we can consider the EFT framework, and from now on, alpha 1 would be the coefficient of this ff squared term, alpha 2 is the coefficient of the ff tilde squared term, and alpha 3 is the coefficient of the CP violating term. So it turns out there have only been direct measurements of CP conserving photon-photon interactions, bounding or constraining both alpha 1 and alpha 2 to be about an order of magnitude above the Euler-Heisenberg prediction. But there haven't been any direct searches for CP violation in photon-photon interactions in low energies. What we do have is a theoretical constraint. So we know that from the consistency of the EFT or from causality or unitarity, we know that this alpha 3 coefficient should be smaller than roughly the geometrical mean of the CP conserving coefficients. So since there are no direct experimental measurements of this effect, this is exactly what we would like to do. So our first proposal is considering or using superconducting radio frequency cavities. So the idea is the following. So consider our cavity with some background field or some pump mode. So we pump into the cavities with two eigenmodes of the cavity, E1 and E2, with frequencies omega 1 and omega 2. So we can think of photon-photon interactions, or the self-interactions of these pump modes would be some sort of a source of a new field that we denote by E nonlinear. So this field would be cubic in the background fields. And as a result, its frequency would be some linear combination of omega 1 and omega 2. So for example, 3 omega 2 or 2 omega 1 plus omega 2. So the idea is that we pump our cavity with modes with frequencies omega 1 and omega 2. And what we will see if we had photon-photon interactions is another mode with some frequency of, as we said, for example, 2 omega 1 plus omega 2. So that would be our signal. If we want to really be able to measure that, what we would like to achieve is that this new field that we create excites some resonance of the cavity, such that it is also amplified and enhanced. So to make sure that happens, we need to take care of two things. So the first is some spatial overlap, meaning that the new field, the non-linear field, should be in the direction or in the polarization of some resonance of the cavity. And the other condition is a frequency matching, meaning if we want to match some resonance of the cavity, we also need to make sure that one of these frequencies of the nonlinear field matches a frequency of a resonance of the cavity. Okay, so how can we use that to specifically measure and isolate CP violating photon-photon interactions? So it turns out that if we make a specific choice of the resonance mode that we would like to excite and of the pump fields, we can essentially tell CP violation contributions or CP violating CP odd fields from CP conserving fields by their frequencies. So specifically, if we want to excite a signal mode that is parallel to E2, let's say, we can choose our two pump modes such that they are orthogonal, meaning E2 is orthogonal to E1, B1 is orthogonal to B2. And we also want B1 to be in the same direction as E2 as well. So it turns out that if we do that, the only scalars that we can compose are using the same field twice, so E1 squared, E2 squared. And the only pseudoscalars we can construct are a combination of E1 and B2, for example. So the result of that would be that the only pseudo vector that we can compose that will have some projection onto E2, so the CP odd field that we generate must have an odd number of the one field and an even number of the two field, and vice versa for the CP conserving field. So as a result, the two fields would have different frequencies. So the CP violating part would have a frequency of, say, omega-1 plus 2 omega-2, while the CP conserving part would have a frequency of omega-2 plus 2 omega-1. So what we can do is essentially tune the geometry of the cavity such that only the CP violating frequency matches a resonance of the cavity, and only that one will be enhanced. Okay, so moving on to our next proposal, which is measuring birefringence in Fabry-Perot cavities. So, so far we considered photon-photon interactions as some source of a new field. So that would be taking our 4 photons and setting 3 of the legs to the external field, to the background field. What we would like to do now is discuss the next term in this expansion. So that would be quadratic in both our background field and the photon field. So that term would essentially modify the dispersion relation of the photon in the presence of some background magnetic field, let's say. And what we would get is some non-isotropic vacuum refractive index, as you can see, for example, in the case of a scalar here. So the implication of that would be that if we have, for example, some probe beam that is polarized in some direction that is not an eigen state of the propagation, the polarization would start rotating, right? Because it's not an eigenstate of the system. So if we have this probe beam coming in, interacting with the magnetic field, and then going out, if we had some nonlinear photon-photon interaction, we would expect to see something when we use a crossed polarizer at the exit. So to understand how this could be measured, we need to also understand that the signal grows linearly with the length of the interaction region. So in experiments like PVLAS, they're using a very nice trick. So instead of having a very long arm in which this photon or this laser beam can interact with the magnetic field, they're just using a Fabry-Perot cavity, such that the effective interaction length is even up to 10 to the 5 times the actual physical size or the length of the cavity. However, that trick cannot really be used in the case of CP violating photon-photon interactions, because they will just be canceled out in a round trip. So the effect would be, would just flip sign when our probe photon is going back and forth. So this is the reason that PVLAS is essentially insensitive to CP violating interactions. So how can we overcome this? So we have a very simple solution. So instead of just using a line cavity, we would like to propose to use some ring cavity or a rectangular cavity. So we have our probe beam coming in, interacting with the magnetic field in the interaction region, and then instead of being reflected, it will be reflected outside, such that it goes back in the same direction as before. So the CP violating contributions will not cancel out. And so in this scenario, both CP conserving and CP violating photon-photon interactions can be measured. So now we need another way to tell them apart. So that could be done if we have a magnetic field that is rotating, as we do have in PVLAS. So CP violating and CP conserving contributions would basically have a different time dependence, because their eigenstates of the CP conserving and the CP violating interactions are different and are actually shifted by 45 degrees. So essentially our signal should have a shift in time of pi/2. So if we analyze the temporal dependence of the beam, of the outgoing intensity, sorry, we can tell these two contributions apart. So just for the result, or what are the bounds that we can achieve? So if we go back to our relaxion picture, or the relaxation of the scalar that is interacting both in a CP odd way and in a CP even way with the photons, we can put a bound on the geometrical mean of this G and G tilde, so the CP odd and CP even bounds. So as you can see in the plot here, unfortunately, the bounds that we can predict or achieve in a realistic scenario is currently pretty far away from the bounds that you can get by using independent bounds on the scalar and the pseudoscalar coupling of these fields. So for example, by combining fifth force measurements with Astor bounds or with PVLAS. However, in the EFT picture, things look a bit more promising. So we can see that in both of our proposals, so our cavities on the left and the ring cavity, so the Fabry-Perot cavity on the right, we can see that in both scenarios, we can actually probe the theoretically consistent region, meaning that if we use our proposal to directly observe the CP violating photon-photon interactions, we can get a bound that is better than this theoretical constraint coming from just measuring the CP even contributions. So that is even if we have the same sensitivity as PVLAS has at the moment. Okay, so just to conclude, we presented two methods for measuring CP violating photon-photon interactions. So one using superconducting radio frequency cavities, and the other one using a ring Fabry-Perot cavity, so in a setup similar to PVLAS. We showed that CP violating interactions can be isolated from CP conserving contributions, and we can probe them directly. So either by the frequency of the signal or by the temporal dependence, so by the phase. We saw that the bounds on relaxion-like scalars are quite far away from the current bounds from combining scalar and pseudoscalar bounds. However, in the EFT picture, which is model independent, we see that we can probe theoretically consistent region that has not been probed before. Just to conclude with future work, so we would like to also estimate the bounds coming from the electron EDM on the EFT contribution. We'd like to maybe also consider other molecular probes and perhaps also to see if we can probe CP violating photon-photon interactions using intense laser backgrounds. So that could increase our sensitivity. So that is, so thank you.
Thanks a lot, Imber. Other questions or comments? Please raise your hand. If not, I remind you also about the 1 hour extra time we have at the end of the session for the discussion. So thanks again, Imber. I think we can move to Praiwal Murthy with the estimation of CP violating EDMs from known mechanism in the standard model.
So hi, I should share my screen, I suppose. There we go. All right.
No, I do not see it.
All right, is that better?
Thank you.
All right. All right, I'm Prajwal, and I'll be talking about estimating the CP violating EDMs from certain known mechanisms in the standard model. So we'll quickly take a look at the CP violating origins in standard model, which you may all already know. And then we can start estimating the numbers that they generate in subatomic particles, leptons and baryons, in atoms, and of course, finally in molecules as well. So a non-zero EDM of subatomic particles, leptons and baryons is a signature of CP violation and parity violation and time symmetry violation as well. Not only that, a non-zero EDM of an atom also violates parity, CP, and time. I have illustrated an example on the right-hand side here to demonstrate that a neutron or an electron does indeed violate a non-zero EDM in a neutron or an electron does violate parity and time. Jumping right into the sources of CP violation in standard model, most of it comes from essentially two mechanisms: the CKM value, the delta CP in the CKM value, and the QCD theta. We'll neglect all beyond the standard model effects in this essentially. So each of the cases that I present, you will see essentially a bar that you see here. The red one being the experimental constraint that has been imposed. The gray one being the value that comes from the QCD theta, and the purple are indicated by the blue text here, which comes from the CKM value. So here you see the values calculated for the electron. Electron has one of the best experimentally constrained EDM values on the top here. And the standard model QCD theta value and the CKM values have also been calculated. Note that the theta value here comes from the constraint of NEDM, which you'll hear about soon in the next talk. In between, in the white space, is fertile ground for any BSM. So if you were to measure an EDM in this white space, then that would be reason to expect BSM contributions. Now, for the muon and the tau lepton, the EDM just scales as 1 over their masses. And so the QCD theta EDM and the CKM EDM of the electron can just be scaled up. And that's what's been done here. There are experimental constraints on the muon EDM and the tau lepton EDM as well. The muon EDM comes from the G-2 experiment, essentially, that you've heard about. And the tau lepton ones comes from positron-electron collisions from Bell collaboration. Now, moving on to the neutrinos, there are actually experimental constraints on the neutrino EDMs as well, also from positron-electron collisions, but there are no theory that sort of calculate and puts an estimate on the theta QCD contribution to the EDM or the CKM value. So I leave that blank here. Moving on to the light baryons, this is probably, again, another interesting scenario where the neutron and the proton, the values of their EDM has been quite strongly constrained. The neutron EDM, the experimental value essentially sets the constraint of the QCD theta term. That then goes into contribution, that then goes into the gray portion of the EDM that you see in both the neutron and the proton. The CKM value also is quite relatively larger compared to the electron. Reason being that the figures that generate EDM in baryons is a one loop diagram, whereas in the leptons, it was a 4-loop diagram. And so the CKM value naturally is orders of magnitude higher. For the proton, one can exchange the U with the D and essentially generate the same diagram. And so the CKM value for the proton and the neutron are essentially the same. And the QCD theta contribution to the EDM is limited to whatever the neutron constraint is. Going to heavier charge, heavier strange and charmed baryons, here we also limit the QCD theta EDM to essentially what comes from the neutron. And then for the CKM contribution, there are relationships between, to begin with, the delta zero baryon and the neutron. And so a simple relationship between the two gives us the CKM contribution, which translates directly from the neutron onto the delta. This is also the only strange baryon in which there is actually an experimental constraint coming from fixed target experiments. With respect to the sigma cascade and the charmed versions of them, essentially comes again from a ratio between the delta sigma and the cascade EDM values. And then with regards to the delta charmed and the cascade charmed baryons, we do the same trick that just like the neutron and proton were interchangeable in the diagram that generated EDM. Similarly, the delta zero and the charmed delta are interchangeable, as well as cascade zero and cascade charmed. And so essentially the EDM, the CKM EDM values are the same for delta zero and delta charmed. Same for the cascade zero and the cascade charmed. Next, we move to the atoms. The first set of atoms that I want to talk about are essentially the paramagnetic atoms. These atoms have a large sensitivity to the electron EDM. Now, again, I want to also caution that this particular method of presenting neglects scalar and tensor contributions between the electron cloud and the nucleon. And so the CKM values that you see here would rather be underestimates. There are papers where the CKM value can be as high as 10 to the negative 27, but you see that here the numbers are quite low, orders of magnitude lower, but the contribution of the QCD theta term in the scalar and tensor formalism is not quite well understood, so I leave that out. So there are experimental constraints going back to 1960s in rubidium, cesium, and thallium. The francium one is up and coming. The way that we estimate the CKM and the QCD theta contributions to the EDM is essentially by scaling up the electron numbers that you saw a few slides ago by a factor that has been calculated and rigorously shown in multiple places. And so you can see that rubidium starts off with sort of a multiplicative factor of about 25, and then it goes all the way up to 900 or so. Francium is still in progress, being a radioactive element. Should expect an experimental constraint on that soon. Now, the next series of atoms is diamagnetic atoms. Now here, unlike the paramagnetic atoms, which were sensitive to the electron EDM, the shift moment dominates the CKM contribution. So essentially what this slide is showing you is that the shift moment of mercury 199 can be broken down in terms of the constituent proton and neutron EDM. And then that allows us to plug in the values of the CKM and the QCD theta contributions that we saw multiple slides ago from proton and neutron. And that gives a value of mercury CKM expectation and the QCD theta expectation for mercury. One word of caution here again is that actually the proton EDM comes from mercury, which is quite strong, as well as the neutron EDM can also be calculated from the mercury EDM, but then those things assume single sources. And of course, that is quite a dirty way to extract compared to the direct measurement, which you'll hear from the next talk. The other diamagnetic atoms of interest are xenon and radium-225. Particularly, radium-225 is a octopole deformed nucleus, which means that the ground state parity doublet has an energy difference, and then that leads to an enhancement above and beyond the shift moment that you saw in the previous slide. And so most of the papers refer to the enhancement factor with respect to mercury. And so I have presented essentially the enhancement of the shift moment with respect to mercury. Xenon, being a spherical symmetric one, does not have any octopole deformation enhancement, but there is nevertheless a ratio between the shift moment. In fact, the shift moment is smaller than that of mercury in the CKM and theta QCD formalism. With respect to radium and radon, there's approximately 10 to the 2 order of magnitude, or rather 10 to the 2 factor larger enhancement. And so sort of combining all of them, one can enhance the mercury values that you saw a few slides ago by these octopole enhancement and the shift moment enhancement to get the values of the CKM and the QCD theta here. Xenon and radium-225 have an experimental constraint. Radon.
Excuse me for interrupting. 2 minutes left.
So going on to the molecules, thallium fluoride is very similar to the diamagnetic atoms that we saw before, only that the decomposition of the EDM is a bit different. Most of the EDM here comes from the unpaired electron on thallium. And then one can plug in the values again that we had for electron and proton to get the CKM expectation and the theta QCD expectation here. There's of course also an experimental constraint on thallium fluoride. Finally, we come to the polar molecules of hafnium fluoride, lead oxide, ytterbium fluoride, and thorium oxide. Here again, just like for the case of paramagnetic atoms, we probably are underestimating the CKM EDMs here because we neglect again the tensor and scalar coupling of the electron cloud with the nucleus. Nonetheless, a molecule has an advantage over atom given that there are intramolecular electric fields that are of the order of gigavolts per centimeter. This is far larger than you can ever apply in a lab between two plates. And so in order to compare, I have normalized the voltage that the experiment applied with the intrinsic intermolecular field. And so in most of these polar molecules, the electron is what is seen. And so they are essentially sensitive to the electron EDM. In fact, the electron EDM comes from thorium oxide. Radium fluoride has been proposed. And you can see that the radium fluoride has a electric field that is about an order of magnitude or 2 orders of magnitude under the intrinsic electric field of the other 4. Most notably because in radium fluoride, the relevant nucleus is the radium nucleus, whereas in the other 4, the relevant species is the electron. And so the mass difference leads to that 2 orders of magnitude smaller electric field. So finally, I want to conclude that there is a way to estimate the CKM and theta QCD contribution in terms of expectation and what we expect that allows us to sort of see what the experimental limits really mean. Particularly, I want to again caution that the polar molecules and the paramagnetic atoms probably are underestimated in the CKM expectation. And I want to note that the charged lepton have probably the most fertile ground to search for background-free EDMs where one could be sensitive to beyond the standard model. And also I want to note that the species of neutron and mercury 199 and probably proton in the near future, and also the radium in the near future, are probably systems where the EDM, if discovered without any improvement in sensitivity, can already be explained in the standard model with just the theta QCD. Well, that's about it. Thank you.
Thanks a lot. Are there questions?
Maybe I'll have one. I was trying to raise my hand, but I can't find. Oh, I'm co-host, so I couldn't. Sorry. If I may, so I wanted to ask, where do you see where it would be more useful for the experimental work to concentrate? There's a huge landscape of EDMs here. Are there some that you think we should focus more on?
Again, there's
of course, there's many experimental efforts, but yeah.
Of course, you see that people have searched for over 24 species here, varying degrees of experimental sensitivity, and some of them are still being improved. I have not shown the ones that are still being improved as to what the reach of those improvements are. But again, going back to your question, there are probably 2 ways to really approach that question. One is to sort of look for standard model background free situations where you want to be sensitive to some beyond the standard model effect. Where, for example, let's say that mercury, probably the best constrained hadronic EDM. If you were to measure some EDM in mercury, it really need not be from any one beyond the standard model source. It is quite well explained within the standard model. And so if you want to be sensitive to sort of beyond the standard model ways of doing things, then you want to look at charged leptons, electrons, and muons. And so that's one approach of coming about it. And if you want to measure the standard model value, then probably going for things that are octopole deformed and put them in a molecule like radium fluoride or thallium fluoride is probably the way to go.
Okay, great, thanks.
Thanks. If there are no other urgent questions or comments, let's move to the last presentation of the pre-coffee session by Benoit Eric Clement, new measurement on the neutron electric dipole moment at PSI.
Okay, so good afternoon, everybody. I'm going to present, so after this nice review of all the potential EDMs. I'm going to talk specifically on the neutron EDM and the latest result on the measurement of the neutron electric dipole moment. So, oops, yeah, here we go. So just to remind you, for the theoretician, as we've seen, the EDM is a CP violating term in the electromagnetic current. And looking for new sources of CP violation is something that's very important in respect to understanding the asymmetry between matter and antimatter in the universe. It's one of the key ingredients to understand this asymmetry. But in the standard model, as we know, the CP violation is small, it's only through the electrorecurrence, and to have an effect in the electromagnetic current, it only happens in the 3-order or 4-order loops diagrams. And this results as a EDM for the neutron. In the standard model, it's very small, 10 to the minus 31 electron centimeter. But beyond standard model physics could contribute much higher because it goes to one loop or 2 loop order. And then you can go to 10 to the minus 29, 10 to the minus 26. And then you can reach the region that the experimental sensitivity is able to attain today. Now, from the experimentalist point of view, the experiment that we perform is a T violation effect. Basically, you put neutrons in a magnetic and electric field, and you're going to measure the Larmor frequency of the precession of the spin. And if there's an EDM, an electric dipole moment, then the Larmor frequency for the two spin, for magnetic and electric field aligned and anti-aligned, will give a slightly difference in the frequency. So measuring the difference in frequency will give you access to the measurement of the EDM. And the limit before the result I'm going to present today was the EDM smaller than 3, 10 to the minus 26 electron centimeter. This result dated from 2006 and was updated slightly in 2015. So it's been 14 years before new result. So how do we measure EDM? So as I said, we measure a frequency, and the basic idea is to use this called the Ramsey method. So you start with neutrons that are polarized along your B field. Then you apply your pi pulse, a pi over 2 pulse to rotate the spin in the transverse plane. And then you have a long period of free precession of the neutron. Then you reapply the same pulse, and you get some asymmetry between up polarized and down polarized spin states. And this asymmetry you can relate to the precession frequency. And the sensitivity you will get is inversely proportional to the electric field, to the time of the free precession, and to the square root of the number of neutrons at your disposal. And especially to increase the time, we use the so-called ultra-cold neutrons, so that very slow neutrons that can be stored inside a physical volume, so here in a precession chamber, and we can store the neutron for up to a few minutes, 3 minutes for the Ramsey method free precession in this example. But the disadvantage of ultra-cold neutrons, as we'll see later, is that they're sensitive to gravity. So the basic of the experiment is presented on this small diagram on the bottom right. First, you have a polarizer that will polarize your neutrons. You inject them in the precession chamber. In the precession chamber, you apply this Ramsey method, and at the end, you extract the neutrons, analyze the spins, count the spin up and spin down, and measure the asymmetry. Now, the EDM experiment, it's a small international collaboration of roughly 50 physicists, mostly in Europe. And the result I'm going to present today correspond to data taken over 2 years at the Paul Scherrer Institute in Switzerland. But we're using the apparatus that was used previously at ILL for the previous results on the NEDM, as well as collaboration. And what's important to see here is that the statistical sensitivity over these 2 years is of the order of 1.1 10 to the minus 26 electron centimeter, which is roughly similar, a bit better than the previous result. Now, the main issue of this kind of measurement is controlling your magnetic fields. Because any magnetic effect, any variation of the magnetic effect of the magnetic field will change the Larmor frequency. So what you do is first you reduce the ambient, the external magnetic field. So you use mu metal shielding. You have external coil to compensate for fluctuation. And you try to work in as much as possible a magnetic free environment. And then you try to measure the magnetic field to correct for any further variations. And for that, we have two kinds of magnetometers: external magnetometers using cesium atoms, and they use mostly to measure the field gradients, and a mercury co-magnetometer, that means mercury atoms that are inside the precession chamber and that will sample almost the same magnetic field seen by the neutrons. And the main part of the analysis is in this almost, trying to understand the small differences that induce systematic effects. So you can see on the plot on the bottom, the frequency of the neutron, and you see these large fluctuations that are mostly due to fluctuation of the magnetic field. The fact we have co-magnetometers, and you can use a ratio of the frequencies, and you can cancel the fluctuation of the magnetic field, and that's what you see here. Now the two different colors, blue and red, correspond to the two signs of the electric field, so parallel and anti-parallel configuration. And if you add an EDM, you would see a shift between the mean value of the blue points and the mean value of the red point. Obviously, with the eye at this level, you cannot see anything. Now, the problem that we have with this co-magnetometer is that any effect that will be dependent linearly on the electric field on the mercury frequency will appear as an effective EDM, so what we call a false EDM, and bias the measurement. And in fact, we're going to use this effect inside the analysis to improve it. So basically, these fake mercury EDMs come from the relativistic motion of the mercury atom in the electric field, which build a motional magnetic field, and the magnetic inhomogeneities in the chamber, so the gradients that remain in the chamber. And this DN4 you can decompose into a gradient that is linked to the gravitational difference of the neutrons and higher order gradients. Now, this gravitational effect, I mentioned before that UCN was sensitive to gravity. And what happens is that the mercury gas inside the chamber and the UCN, ultra-cold neutron gas inside the chamber, does not have exactly the same average age because the neutrons fall a bit because of gravity. And this small difference we can measure independently. It's minus 4 millimeter roughly. And due to this effect, it generates an effective gradient, magnetic gradient between the two species. Now in our analysis strategy, what we do is instead of trying to cancel these gradients, we create magnetic gradients with external coils. So we have several sets of magnetic configuration, 99 different magnetic configurations in the analysis. And for each configuration, we're going to feed the ratios of frequency as a constant, plus a term that is linear in the electric field, and that this term contains the neutron EDM. Now, obviously, these quantities, so this L0 and this Dn that are fitted here, they're sensitive to these gradients, and we know we can compute these corrections, and they both depend on this gravitational gradient. And in addition, the L0 depends on transverse field homogeneities, and the Dn, as seen before, or on higher order gradients. Now, the higher order gradients and transverse field homogeneities we can measure. What we do is that we remove the precession chamber and we do precise mapping of the magnetic field inside the apparatus. And from these maps, we can extract these quantities and correct the L0 and Dn from these quantities. And so at the end, you get this Dn core and L0 core that are mostly only linearly dependent on the G-graph, and the dependency is a known slope. Only the sign depends on the magnetic field sign, or the relative sign of the magnetic field and electric field. So you just have at the end to plot these two quantities, one versus the other. You get two lines, and where this line crosses, that we call the crossing point analysis, then the G-graph cancels out. So you don't have to cancel the G-graph with the apparatus. You just measure for different gradients and extrapolate for G-graph equals to 0. And that these values of EDM measured at the crossing point should be the true EDM. Obviously, it's always a slightly more problematic than that. Other systematics effects that can be added, and we have done very detailed studies of many systematics effects I won't enter into any details here, but for example, we have looked at every piece of the apparatus after it was dismantled to check for any magnetic contamination from local dipoles and see the contribution that it could have to the EDM. But at the end, when you combine all the systematic effects, we have a control of the systematics of the order of 0.2 10 to the minus 26 e-centimeter. And that's very important when you plug that into the final result. Yeah, I see I have 2 minutes left. So we made 2 different analysis teams working separately on the analysis on blinding data, and then we are blinding progressively in 2 steps to check at every step that our understanding of the statistical precision and the systematic uncertainties was okay. The plot you have on the left is this crossing point analysis, so these 2 lines that crosses here at the value of the EDM. And both measurements from both teams are consistent with each other, obviously. And when you average over them, you get a new value of the EDM that's fairly consistent with 0. So 0 plus or minus 1.1 statistical, plus or minus 0.2 systematics, 10 to the minus 26. To compare to the previous results, which had, as I said, almost the same statistical sensitivity, but we have a huge gain in the systematics. And that's very important because this is only the first step toward a new project, the next generation experiment, it's the N2 EDM project. And we can use the understanding of the systematics effect that we have gained over the analysis of the NEDM to inject that into the design of a new generation experiment that will be basically the same kind of concept, so a precession chamber with co-magnetometry and external magnetometry, but now we will have a double chamber to cancel some of the systematics, so you measure simultaneously both field configuration. We have a larger magnetic shield with a large factor 100,000 shielding factor, and much more magnetometer to have a much more understanding of the gradients and the higher order gradients. We will have an increased electric field, so that will directly impact the statistical sensitivity, and we will also increase the statistics with a larger chamber volume, longer data taking, and so on and so forth. So to conclude, I have just presented the new result for the NEDM measurement. That means that the new results from the last 14 years, and we hope that the next one will be in a few years from now. It's still consistent with 0, so you can consider that as a limit, 1.8 to the minus 26 electron centimeter at 99% confidence level. As I said, this limit is improved by a factor or a bit less than 2. So the result in itself is not the most important. What is really important in this result is that the systematics are reduced by a factor of 5. And this shows that the NEDM collaboration has a good enough understanding and control of systematic effect to pretend that we can do better with the next generation apparatus and to inject this understanding of the statistics, systematics effect into the design of the next apparatus. So the design includes this understanding, reduced statistical, and the ultimate goal is to reach 1 order of magnitude in the limit, so 10 to the minus 27 electrocentimeter in 2027, which means either a new improved limit or hopefully discovery of a signal in this region, because some beyond standard model physics could predict an EDM in this region. Thank you.
Thanks a lot, Benoit. Are there questions? Check on Martin's.
Maybe I have a question.
Please.
I mean, those ultra cold neutrons that you're playing with, I mean, that must be like a wonderful tool. Like 4 meters per second is amazing. So are there any other games that you plan to do with your apparatus, like exploiting this feature?
Well, the basic interest of these ultra cold neutrons is that they're very slow. That's one feature, but the main interesting feature is that they're reflected at all angle of incidence. So once you have them, they're trapped. You can guide them just through simple tubes, store them into bottles, and they're very practical to use from this point of view. but the speed in itself is not really interesting at this level. There are other kind of experiments that will use the fact that you have a very slow velocity spectrum for the neutron, but that much for flow-through experiments rather than storage experiments. So that's not for EDM.
Thanks. If there are no other questions or comments, let's thank again all the speakers of the pre-coffee session. And I think we need 10 minutes break. So the post-coffee session will start at 6 p.m. And I invite the next speakers to check their audio and sharing feature in these 10 minutes.
Hello. Let me try then. Although we checked before, but
Go ahead. Yeah, we
can you see slides? Can you hear me?
Yes, perfect.
Let me change slides. Okay, that works.
Yes, it works here.
Perfect.
So is Alexander Frelich around? Can we try?
Yes, I'm here. We also tried before, but I can try again. So let me quickly share. Oh, no, that's the wrong one. No, you should see slides, right?
Yeah, we do.
Okay, great. So let's quickly go to the full screen.
Fine.
Transition works. Okay.
Yeah. Next one is Josef Juraj. Is Josef around?
I can try again.
Great.
So can you see me? Hear me?
Looks okay. Yes, changing. Can you say something? I mean, there were some glitches to the sound.
Case study about the mass exclusion limits beyond standard model vector resonances.
I mean, the sound does not really sound very clear.
So I will switch off the video.
Yeah, for me, it was also breaking up.
So I switched off the video. Now I can try to talk again. The case about the mass exclusion limits.
I'm afraid you didn't switch it off the video. Josef, excuse me. I'm afraid you didn't switch it off the video.
Okay. It doesn't work. Okay.
Can you keep saying something?
Oh, I will stop.
May I?
Sharing at first. So I stop sharing. I will stop the video now. Then I have to go to presentation mode.
Now you sound way better.
Okay. Okay, so I can't use the video. And I'm starting the presentation.
Yeah, your sound is perfect now.
Okay. And I'm place 4. So I have to presentation mode first, and then okay, I have to start it again. So, why I can't see the control panel of the Zoom?
Is there any technical problem? Maybe we can like skip to the next speaker, and you have time to resolve it.
Okay, I'm the third one.
Yeah.
So, yeah. Okay. Skip the next speaker and then come back to when I'm asked. Okay.
Okay. Perfect. So Radovan Dermishek, can you?
Hello, I'm here.
Great. We can see you now.
Okay, let me try.
Yeah.
Okay, can you see the whole slide?
Perfect.
Excellent. See you soon.
Can you try the transition?
Oh, okay.
Supposedly it's good. Good works. Thank you.
Okay, thank you.
Next one is Christian Peña.
Hi, can you hear me?
Yes.
Okay, and perfect. Let me try the sharing part. It should be this one. Can you see that?
Yes, we can.
And then full screen. Does that work?
Yes, it does. How about transitions? Good.
Works?
Yes, it does. Thank you.
Okay, thanks.
Next one is Monica Verducci. Monica, are you around?
She's connected.
Yes. Okay, maybe we can go meanwhile to Pavel Guzovsky.
Hello, can you hear me?
Yes.
And share screen. Nope, that doesn't work.
We see your window, like windowed presentation, but not anything full screen yet.
Oh. Okay, I'll fix this. Okay, come back to me.
Okay, we will. Next one is Tovary Holmes. Tova, are you around? Connected. Tova, can we hear each other? So perhaps we skip to Beatrice K. Beatrice, can you hear us? Okay, no response. So how about James? Painful. I can't see him on Zoom. So maybe it's time to go back to Joseph. Joseph, can you hear me?
Yes, I can hear you.
So can we try again?
I try to share. So can you see the sharing?
Yes, we can see, and we can see the transition. Can you say something?
Okay, a case study about the mass exclusion for beyond vector resonances.
The sound is not good still. Looks like I mean, there's something with the
okay. I can start the computer. Sorry.
Can you say something again?
I can't hear you now. Okay. It seems there is low capacity. It was tested before, but so now the situation is different. I don't have video.
With some breakouts. So maybe we can go for an assisted Zoom.
Okay, now can you hear me better?
Yeah, it's somewhat better. It's louder. There are still breakouts, but go ahead, say something.
Oh, breakout, okay. So, is it better now? A case study about the mass exclusion limits for the beyond standard model vector resonances.
Now we can at least understand. I mean, it's not ideal, but we can understand. So let's see how it goes. In case it's impossible, then what we can do is we can share your slides. Sorry, we can share your slides for you, which should unload your computer.
Yes.
Okay. So that's
okay.
Joseph. Then we have Monica. Monica again, Monica Bertucci. Are you around? Monica, can you hear us? No response. So Tova Holmes, are you around? And Beatrice?
I'm sorry, did you want me to?
Yeah, Tova, I just wanted to test your connection. Could you please?
Oh, sure. Sorry. I had my volume turned down because I was practicing.
Sure, no problem.
Okay, do you want to see if I can share?
Indeed.
Okay, let me, sure. Sorry about that. Let me see, share screen. And desktop to share. Okay, I am sharing now. You should see a mountain, island. And now hopefully you can see my slides, my title slide, and then the second slide.
Indeed, yeah, that's perfect.
Great, okay, wonderful.
And Beatrice? Oh, James? Oh, James is not around. Beatrice is. Beatrice.
I am it, yes.
Yes, Beatrice, could you try sharing your presentation?
Oh, yes, sorry. I was out for a moment.
No problem. That's the purpose of the coffee break, indeed, yeah.
Yeah, I was late, sorry.
No problem.
Is it okay?
Yeah, we see your presentation in a window. Could you try full screen?
Let's see. Yes?
Yes, we can see it. How about transition? Could you try to switch to slide 2? Yes, that works. So I think the only one who was not tested yet is Monica Verducci, but I think we are already late. So could you please?
So what, I do escape here?
Yeah, please share your screen, and we will start with the first talk of this session. So now we are. Okay, go ahead. Beatrice, could you please unshare your screen? Okay, I'll do that for you. So we should start the after coffee block now with a series on heavy flavor at Collides, and then we turn to long-lived particles. So the first talk is by Héctor de la Torre Perez. I will use some kind of a reminder tool like this to let you know that it's your time is almost up. So 3 minutes before the end of your talk, I will make the sound, okay?
All right.
Okay, so please go ahead.
Okay, I should be sharing now, and can you hear me okay?
Mm-hmm. Good.
Okay, so hello everyone. I'm very happy to be here to talk about this topic, about searches for new physics in finite states with heavy flavor quarks using the ATLAS detector on behalf of the ATLAS collaboration. in final state with bottom and top quarks, so a large part of the searches program in Atlas, and of course in the LHC in general. We use them to search for supersymmetry, for generic resonances, for leptoquarks. We use it to search for PS standard model through top quark properties. We look for vector-like quarks or for dark matter. And you can see, you can follow the links and find a lot of these type of final states in different talks by Atlas speakers during ICHEP. This talk in particular focuses on giving you details on two very recent Atlas searches by the Atlas collaboration. The first is a search for TT-bar resonances in fully hadronic final state, and the second is a search for dark matter associated with a single top quark. So these use the full range dataset taken between 2015 and 2017 with a total of 139 inverse Fern-to-1 of good for physics Atlas data at 13 TeV. And beyond the increase in integrated luminosity, they also take advantage of the full range of improvements that were done during and also after run 2. For example, better bottom and top tagging performance, better Monte Carlo simulations, and more advanced techniques such as data-driven approaches to estimate backgrounds or machine-learning-based analysis techniques. So now starting with the first analysis of the two that I will talk about. This is the search of TT-bar resonances in fully hadronic final state. It is a search on the invariant mass of two large jets, which are anti-KT calorimeter jets with radius equal 1.0. And both jets are expected to be top tagged, that is identified as coming from a top quark, and associated with B-tag jets, that is jets that are identified as coming from a B quark. It is a bump hunt, which is focused on high mass, and it uses a functional form to estimate the background. Regarding interpretations for the paper, there were just one benchmark model, which is a top color assisted technicolor C prime, but we consider it widths. And it has also now been reinterpreted in using a model with a vector axial mediator C prime for dark matter. So this is a new iteration of an analysis that was already performed with partial run 2 data with 36.1 inverse Fern-to-1. You can find the link there, but it has several improvements, which I will talk about. One of them, I already mentioned, the functional form used to estimate the background, but the top tagging and the B tagging have been also improved. Now they use the deep neural network to identify tops and works. And in the case of the B tagging, these are run now on variable R jets, which are anti-KT inner detector tracks with an effective radius that depend on the PT of the track jet, and they work better in busy environments such as this than the fixed radius that we used in the previous iteration. Speaking a bit about top tagging, this is the first analysis in Atlas using the new high-level DNN top tagger that was developed, which uses several jet moment observables related to the substructure as input to a DNN. And this provides large improvements over previous algorithms used by Atlas, in particular, much better like jet rejections or background rejection, especially at high mass. This is shown on the plot on the right-hand side, which comes from the W and top tagging performance paper. And there it compares the background rejection as a function of the signal efficiency for different algorithms. The one used here is the red line, which shows us DNN top, and the one used, for example, in the previous iteration of this analysis corresponds to the green point on the towards high values of signal efficiency. And as you can see, it provides around 4 times better background rejection. Now, as I mentioned before, this analysis uses a fully data-driven background with a global function that is fitted directly in the signal regions. The global function is I saw on the right-hand side of the slide. And this functional form and the uncertainties that are used on it are estimated and studied using a template which is built using a mixture of Monte Carlo and a data-driven ABCD multi-jet estimation. This is done in order to have enough effective statistics to be able to study this function properly in the whole range. To define the signal regions, we have an event selection that has starts with a larger jet triggers. Then we select events with 2 larger jets with high PT. And then there's also some additional angular variables to reduce the contamination from multi-jet events mainly. There are 2 signal regions, one in which one of the 2 top candidates has to have an associated B-tag jet, and in the other one in which the 2 top candidates are required to have each of them an associated B-tag jet. The result in the signal regions can be shown in the 2 plots that I saw on the right-hand side. And you can see, of course, the data as a function of the mass of the invariant mass of the two larger jets. And you can also see in red the background estimation, which comes from this fit. And in the bottom side of each plot, you can see the significance calculated using BAM-Hunter. And you can see that it's not very big in the whole range. And the most significant deviation is actually on the very, very high mass tail, in which we really have very low statistics. Okay, so since there's no significant deviation from the standard model, we calculate limits. This is what I saw on the next slide on the left-hand side plot. This is the cross-section times Manchin ratio as a function, limit as a function of the mass of the C prime. And as you can see, it provides exclusion of masses up to 3.9 TeV and 4.7 TeV for decay widths of between 1% and 3% respectively. In addition, on the right-hand side plot, I saw a comparison with the previous analysis again. In green is this analysis, the current analysis. This is the expected limit. In blue is the same analysis, but in which the luminosity has been scaled back to 36.1 to be able to be compared with the previous analysis. And in black is the previous analysis by itself. And this comparison is very nice because you can see that even when you consider the same integrated luminosity, the new techniques are really improving this analysis quite a lot. Okay, in addition to the results that were included in the paper, now this analysis has been reinterpreted in the context of the dark matter summary plots that Atlas produced. And you can see one of these plots in the left-hand side. And this is a leptophobic C prime axial vector mediator model. I won't go into details on the plot. You can just find the TT bar resonance analysis with the pink line on the right-hand side of the, well, the purple line on the right-hand side of the plot. And you can find much more about dark matter Atlas results in the very nice talk yesterday during the dark matter session. Okay, now speaking about dark matter, I can move to my second analysis, which is a search for dark matter associated with a single top quark, which explores final states that have not been explored before in Atlas in this context. This is a search focused on a student, the 2HCM plus A model, which has an extended Higgs sector with CP even bosons, CP odd bosons, and also charged ones. And it has a Dirac dark matter candidate. It has 3 channels, one focused on the T channel production, which corresponds to the diagrams on the right-hand side, and 2 aiming to study the TW channel production, which is what you can see on the right-hand side. For here, we have 2 channels, 1 lepton and 2 lepton, depending if the 2 Ws in the final state decay leptonically or only one of them does. Going a bit on details of the analysis and started with the 1 lepton TW channel. This uses a selection based on a Messiniti trigger and 1 lepton plus jet selection. You can see the pre-selection on the right-hand side. You have at least 3 jets and at least 1 B jet, for example. And in addition, they use transfer quantities to improve the sensitivity and to define control regions and validation regions. And these are constructed using the missing transfer momentum on other objects in the event. And the main background for this channel is TT-val and W plus jet and W plus jets. And the way that the background estimation works here is that we define a series of control regions, and you can see the definition on the right-hand side, which are fitted to the data. And then that estimation is checked first in the validation regions and eventually in the signal regions. And this is what you can see on the left-hand side plot. The first 3 regions are the ones that are fitted, and then the validation regions, you can see the agreement between the background estimation and the data, and you can see that the agreement is very similar to the validation regions. Now moving on the 2 lepton TW channel, this uses a different selection with a dilepton trigger and opposite sign lepton plus jet selection, since now we have the 2 leptons from the 2 Ws. It also uses transfer and angular quantities to improve sensitivity. And here the dominant backgrounds are TT, TTZ, and WZ. And these are the focus of the control regions and validation regions that are created, and then you can see on the right-hand side table. The same procedure is done to estimate the background, and this is what is done on the left-hand side plot. You have the 3 control regions which are fitted on the left-hand side, and then the estimation is checked on the validation regions on the right-hand side. And to finalize the last channel, this is the 1 lepton T channel, which has, similarly to the 1 lepton TW channel, a missing T trigger and a lepton trigger combination, and it uses a lepton plus jet selection too. But in addition, this channel has a boosted decision tree with 9 variables, which go from the kinematic values of the leading jet, transfer quantities, and also some variables from the lepton VJet system. And that is used to define the signal regions and the control regions and the validation regions as before. In this case, the dominant backgrounds are TT1 and W plus jets, and you can see on the left-hand side plot the same procedure as before. The two first regions are the control regions which are fitted, and then the estimation is checked on the validation regions. Of course, where we really want to see the agreement is in the signal region. So this is what we do. And this is what I saw on the next slide. The summary of the procedure is on the right-hand side plot. In total, we have 10 signal regions in which we check the background estimation obtained from the control regions. The first, starting from the left on the plot, you can see the 4 bins from the TJ1 lepton channel. This is bins in BDT output starting from 0.6. Then we have 5 bins from the TW1 lepton channel in missing ET. You can see also the ranges of these bins in the left-hand side plot. And the last one is a single bin signal region from the TW2 lepton channel. As you can see, in general, there's a very good agreement with the standard model, a slight excess maybe on the TW2 lepton channel that doesn't reach even to sigma. Okay, so we can calculate limits using these results, and this is what I saw on the next slide. Sorry. So in addition, this is done using the 2HCM plus A model, but in addition to take into account the contributions from the single top plus dark matter diagrams, which are the ones that I showed on the first slide from this analysis, the contributions from the dark matter plus TT bar diagrams is also considered. This makes sense because this analysis, of course, is not only sensitive to the single top plus dark matter contribution, but it's also sensitive to this type of diagram. So even if it's not the focus, it makes sense to calculate the limits taking into account both contributions. So this is what is done in these limits there. And you can see also that there are 3 lines for each case. This is because in addition to the individual TW one lepton and TW2 lepton channels, we also do the statistical combination between both channels to get a combined limit. These limits are calculated in 2 different planes. The first is in the y-axis, you have the mass of the charge Higgs, and on the x-axis, you have the mass of the pseudoscalar mediator. And on the other plane, you have in the y-axis tan beta, and on the x-axis, the mass of the charge Higgs. And the rest of the choices of the parameters in the specific choices that were made to make these plots can be seen in the legend for each of the plots. In the case of the TJ1 lepton channel, this is not in the same plots, and the reason for this is the sensitivity is smaller due to the small T-channel cross section, but they still it still can provide some complementary sensitivity, and this is what is shown in the 2 one-dimensional limits plots on the bottom. On the left-hand side, for a tan beta equals 0.3, that provides some exclusion up to mass of the charge Higgs of around 800 GeV, while for a tan beta equals 0.5, this is really not the case, as it's not able to exclude anything. So in addition to the model-dependent limits, they also calculate model-independent limits. And for this, slightly different regions are used, which we call inclusive discovery regions. For the TW1 lepton, it uses inclusive regions in the same ranges of missing ET that were defined for the original signal region. So events above 5 different missing ET thresholds, 250, 300, 400, 500, and 600 for the last one. And for the TW2 lepton, this is the same signal region is used. And for the TJ1 lepton, only the last bin of the BDT distribution, so BDT higher than 0.9. And these are the results of this model-independent limits. I won't go into the details of the table, maybe just to mention the last of the columns, which is the P0, which represents essentially the probability of the observed events the probability of the background model to fluctuate to the observed number of events. And as you can see, in general, there's not a lot of excess in any of the channels, and you can see the same thing that you could see in the summary plot, in which the TW2 lepton goes up to about 2 sigma. Okay, so now I can reach my summary. won't read through it, but this I just want to share with you a very nice event display on the right of my slide, which shows an event from the TT-bar resonance analysis. This is a digest event with an invariant mass of 4.83 TeV. And it is very nice that you can see, for example, in the bottom left of the image, the three-pronged structure that is very in the deposits in the electromagnetic calorimeter that is very typical from a top quark, from a large jet coming from a top quark. And that's it from my side. Thanks a lot for listening.
Thank you very much. Now it's time for questions. Raise your hands. Okay, maybe I would have some kind of a simple outsider question. Actually, on page 10, you were describing the control validation regions in this T plus dark matter searches. I mean, why is it beneficial to have like a single bin control region?
It's not beneficial by itself. I mean, it depends on the analysis. In this case, this is better to define the regions this way instead of having, I don't know, like a distribution. It also depends on the number of events that you have.
Mm-hmm. I see. Okay, thank you. Further questions? Okay, if there are none, we can maybe
Excuse me, I couldn't raise my hand. I'm sorry. It's Mia. Yeah. Very quick question. Yeah. Can you comment on round 3 strategy?
For which case? I mean, for this type of searches.
In particular, in slide number 8, and trying to address the phase space, which is the most challenging one with very low mass value.
Of course, I mean, there are phase 1 ATLAS upgrades that aim to provide a better trigger, for example, to go to lower masses. This is something that is there, and it's, I think that's a general thing in both ATLAS and CMS, that we are trying to increase the coverage on the very low mass. I think this is the one that I can mention at least.
Thanks. So, but I'm sorry, but this is a hardware change, update, or in
yes.
approach?
I think both. So I mean the upgrade on the upgrade on the trigger for run 3 in the case of ATLAS is there, but of course there's also work in making the trigger. This is, I mean, the software part of the trigger chain to be able to go to lower masses better.
And instead for the largest mass value?
I mean, there you just need more data.
Just data, right.
Yeah, I guess, sure, if for resonances, I don't know, if you want to go, for example, for non-resonances, then of course having maybe different background estimation that you can use for non-resonance searches, which are important for the high masses, then that could be a way, yeah.
Thanks.
Okay, thank you, Hector. I think it's time for us to move on. The next talk is by Alexander Frelich, who will actually tell us about similar things from the CMS perspective. So, Alexander.
Yes, can you hear me?
Yes, perfect.
Okay, so yeah, I will present searches for new resonances coupling to third generation of quarks at CMS. And yeah, actually third generation of quarks are often seen as a window to the new physics. And one of the reasons why this is that they feature quite interesting decay signatures that can then be used to distinguish such processes from other standard model processes. And in this talk, I will focus mainly on heavy resonances in the form of heavy vector bosons. So I will show you also results on a Z prime decaying to a pair of top quarks. And then we will also explore some more exotic scenarios where we also allow these heavy resonances to decay into vector-like quarks and standard model quarks as well. There are also searches where those heavy resonances decay into bosons, which are covered in another presentation that is linked here. And in general, we are always assuming such heavy resonances and also vector-like quarks to be around the TeV scale. So we are looking at quite heavy particles. And when searching for such heavy particles, we can assume that the decay products of those particles are always highly boosted. So the subsequent decays are then very collimated, which then allows us to capture such decays inside one large radius jet, as is depicted in the sketch up here for the example of a top quark. And then using jet substructure techniques, we can try to identify such decays and also discriminate them from, for example, QCD multi-jet processes. One of those techniques is jet grooming, which gives us then a groomed jet mass. And an example for this is the soft drop algorithm, where this large radius jet is taken and is iteratively declustered, and at every step, the soft drop criterion shown on the right-hand side here is checked. And if it's not fulfilled, then the softer of the two subjets is removed from the jet, and the process is repeated until the soft drop criterion is then fulfilled. Another very powerful variable is the n subjettiness, which is a measure for the jet to have n or less subjets. And as you can see in the definition down here, in fact, this variable becomes small, close to 0, in the case where a jet is compatible with having n or less subjet axes, while it becomes close to 1 if it has more than n subjets. And usually ratios of this n subjettiness are looked at, for example, tau 3 over tau 2 in the case of top tagging. And then finally, since we can resolve actually subjets within our large radius jets, we are also able to use methods like B tagging on the subjets, so which then will be referred to subjet B tagging. And there's actually also a talk about the recent development in jet tagging techniques, which you can find when you follow this link here. Okay, that we now have all the tools at hand. Let me start with the first analysis that I want to present, which is the Z prime decaying to a pair of top quarks. And here we have actually a combination of 3 different channels, which cover the 3 decay modes of the TT bar pair. And here we are looking at different mass to width hypotheses for the Z prime, going from a very sharp Z prime with a width to mass ratio of 1% all the way to a very broad, almost non-resonant case where the width to mass ratio is about 30%. On top of this, we can also interpret a signal such as this in an extra dimension model, where then the mediating particle would be a Randall-Sundrum or a Kaluza-Klein gluon. Okay, starting with the all-hadronic channel, here the main feature are 2 large radius jets that are then required to be top tagged, which involves a requirement on the soft drop mass and also on the n subjettiness ratio. And then different categories are built based on the rapidity difference between those 2 jets, and also on the number of subjet B tags that were found. On the right-hand side here, we can see one of those categories, which is actually the most sensitive category, with a low rapidity difference and 2 subjet B tags. So 1 subjet B tag found for each jet. And then the QCD multi-jet background is estimated from another control region using an anti-tag and probe method, where the tagging criterion of the top tag, the n subjettiness criterion, is inverted to obtain an anti-tag. Moving then to the semi-leptonic channel, where we have 1 lepton and at least 2 jets. And here the main feature is a BDT that was trained to be able to separate W plus jets production processes from TT bar and signal processes. And then again, categories are built based on the BDT score and also on the presence of a top tag jet, which also then dictates the reconstruction of the TT bar mass. So if there is a top tag jet present, then this one is used as the hadronic top hypothesis, while the leptonic top hypothesis is always built from the lepton, the missing transverse momentum, and another jet. And if no top tag jet is found, then also the hadronic top hypothesis is built from small radius jets. And we can see here then the TT bar invariant mass distribution in the final state with a muon, and in this case, where a top tag jet was found. Moving on to the dileptonic channel, here we're looking for two opposite charged leptons and at least two jets, from which at least one has to be B-tagged, and this requirement is quite crucial to suppress other standard model backgrounds. And then again, categories are built now based on this delta R sum variable, which is the sum of the delta R between the leptons and their closest respective jets. So you can think of this as a measure of how boosted this event is. And in this channel, the invariant TT bar mass is not reconstructed, but instead ST is used as a sensitive variable in the statistical interpretation, where ST is defined as the scalar sum of the jet and lepton momenta plus the missing transverse momentum. And the distribution of ST in the boosted category with two muons in the final state is shown here on the right-hand side. And as all those three channels are statistically independent, we can actually go and do a combination of those, which then should give us enhanced sensitivity compared to the individual results. And indeed, looking at the plot on the bottom here, we can see the expected cross-section limits of three channels in green, red, and blue dashed lines. And then in the black solid line, we can see the combination, which indeed gives us higher sensitivity, especially going to higher masses. And since no excess of data, or at least no significant excess of data was observed, we can also go and calculate then cross-section limits. Shown here, the expected and observed cross-section limits on the left-hand side for a Z-prime model with a 1% width. And on the right-hand side in the extra dimension interpretation for a Kaluza-Klein gluon. And using the theory prediction, we can also convert this then to mass exclusion limits which are summarized in the table down here. Okay, coming now to the next search, which is exploring a more exotic model where we also allow the Z-prime to couple to vector-like quarks, in this case, to a vector-like T-quark. And these kind of searches are seen somewhat complementing our searches for vector-like quarks, which were presented already yesterday, which you can see following this link here. And in this particular search, we can build multiple categories, in this case, to capture the different decay modes of the vector-like T-quark. And this search is especially optimized for the case where the vector-like T decays to a standard model top quark and a Z or a Higgs boson. And here again, we use jet tagging to identify the boosted boson, in this case, from the vector-like T quark. And also we interpret this model also additionally in an extra dimensional and also in a composite benchmark model. Yeah, as I said, categories are built again now based on soft drop mass and subjettiness ratios and subjet B-tags to capture the different decay modes of the vector-like T quark. Two categories capture the case where the vector-like T quark decays into a top and a Higgs boson, requiring a Higgs tag with either one or two subjet B-tags. And then a third category requires a Z or W tag, which captures then the case where the vector-like T quark decays into a Z and a standard model top or a bottom quark and a standard model W boson. Then also subcategories are built based on the presence of the top tag jet, similar to the semi-leptonic search in the previous analysis, which also then dictates how the Z prime mass is reconstructed finally, which is then used as the sensitive variable. And additionally, some control regions are built by inverting the soft drop mass criterion on the Higgs and ZW tags for the case with 0 or 2 B tags in order to constrain the TT bar and W plus jet standard model backgrounds. Yes, and on the right-hand side, we can then see the distribution in the channel with a muon in the final state and the Higgs tag with 2 subjet B tags, but no top tag found in this plot here. And as you can see, there's also no significant deviation from the background observed. So we can also go ahead and calculate cross-section limits on the left-hand side now for the extra dimension model as a function of the mass of this Kaluza-Klein gluon, which then for a certain mass of the vector-like T quark can be converted to mass exclusion limits summarized in this table down here. And also cross-section limits are calculated as a function of the branching ratio of the vector-like T quark to Z top or Higgs top for a set mass of the Z prime and mass of the vector-like T quark. Coming now to the final analysis in this talk, which is a search for a heavy W prime boson that also has an intermediate decay via a vector-like quark, either a vector-like T or a vector-like B quark that then decay to a standard model top or bottom quark plus a Higgs boson. And here again, jet tagging is used to identify the boosted top and Higgs bosons from the vector-like quark decay. And different scenarios for the W prime and vector-like quark mass ratios are scanned. So here, as I said, we require the presence of 3 tagged objects, a top tag jet, a Higgs tag jet, and a B tag jet. And for the top tagging, again, we are using the soft drop mass criterion and subjettiness, and also the presence of subjet B tags. And for the Higgs tagging, we are using also a soft drop mass criterion, and then using a dedicated double B tag requirement. Using the 3 tagged objects, we can then go ahead and reconstruct the W prime mass, which is then used as a sensitive variable and shown on the right-hand side here. And again, control regions are defined using anti-tags, from which then the QCD multi-jet is estimated from data. And again, we don't observe any significant deviations from the background. So we go and calculate cross-section limits. On the left-hand side, we can see expected and observed cross-section limits for a model where the vector-like quark mass is about 2/3 of the W prime mass. And on the right-hand side for another case, where the vector-like quark mass is about 3/4 of the W prime mass. And as you can see, we are not yet sensitive to the theory prediction here, so we cannot convert those to mass exclusion limits. Yeah, let me quickly conclude. So I've shown you the combination of the Z prime to TT bar searches, and also explored some more exotic models with intermediate decays via vector-like quarks, which are of course only part of the full picture of searches for heavy resonances done at CMS, which are all summarized in this plot down here. And I've marked the ones that I presented in this talk here. And as an outlook, can be looking forward to new results coming soon, exploring the combined data sets of CMS from 2016, 2017, and 2018, where we also explore new tagging algorithms and new jet substructure techniques to even increase our sensitivity. And with this, I'd like to thank you for your attention.
Okay, thank you very much for the nice presentation, also for finishing on time. So it's time for questions. Please raise your hands. Okay, I mean, maybe I have a question. At page 6, you saw you showed yes, you show the reach of about 3.8 TeV for the Z to TT bar with 36 inverse femtobarn, right? So
yes.
Yeah, I mean, this number is 3.8 TeV. I mean, it's pretty much the same like in the previous Atlas talk, but they did it with, if I'm not mistaken, at least, they did it with 140 inverse femtobarn. So do I understand it correctly that this is because you combine the purely hadronic with semi and dilepton channels? Or
Yes, indeed. So the Atlas results that were presented were only for the all-hadronic search. And this is the combination of all 3 decay channels of the TT bar. And as you can see by the combination, we gain additional sensitivity, especially in the high masses, from especially the single lepton channel. So this really helps improve this this limit.
Maybe I can comment on this. If so, I actually took a look at the numbers before. So even though the crossing with the theory cross section is up to 3.8, but if you actually look at the numbers of the expected limit at around 4 TeV, this is very compatible with the results even scaling back to 36.1 in our case. So it is not true that this is roughly the same number when you look at the expected cross-section. The sensitivity when we scale back to 36.1 is very, very similar if you look at the numbers. Ours is about 2.6 at 2.6 times 10 to the minus 3 for the 139 inverse femtobarn, and this is roughly around 4 or something like this. So yeah, I would say that if you actually look at the expected numbers, the sensitivity is very, very similar.
Okay. Thank you, Hector, for the comments. Anybody else? I mean, of course, you can always ask questions to all speakers of the session on MetaMost. So if there are no more questions, we can perhaps go ahead and ask Josef Juran for his pick on the third quark interaction, third generation.
Yes, can you hear me?
Yes, we can hear you nicely now.
Okay, you can see my slides.
Perfect, yes.
Okay, so sorry, I will not switch on the video because of the technical difficulties raised during the second testing. So, hello to everybody. This talk is based on the paper published with my colleague Mikuláš Gintner in the European Journal, European Physical Journal C this year. So, experimentalists are searching for new particles, which should be a part of some non-standard model. Namely, Atlas and CMS collaborations are looking for a peak over the background, but up to now there is no discovery, even no significant statistical access. So they transform their data to upper bounds on the production cross-section times the Bayesian ratio. And we can use this quantity to restrict some beyond standard model parameters, for example, mass of the new resonances. So we derive mass exclusion limits. But these upper bounds are not universal. So we will focus on the vector resonances in this talk, and depending on the model and the assumptions and the integrated luminosity, the masses, the limits range from the 2 TeV to 6 TeV. But the values themselves will not be imported in this talk. We investigate the restrictions on the applicability of the generally used limit obtained procedure to specific type of vector resonances. Generally, it's known that it's tailored for the narrow resonances. But the upper bounds depend on various characteristics of the resonance, on the mass, its spin, gauge couplings, interaction patterns, fermions, if some decay channel is missing, and so on. And also, their validity is limited by the assumptions and approximations used during the recalculations. In this talk, I will focus on following particular questions. The restriction by narrow width approximation. So the rule of thumb is that the narrow width approximation is considered safe when the ratio decay width over mass is below 10%. So I will call this quantities fatness of the resonance. So going above the 10% makes derived limits less and less reliable. So I will show the impact of the resonance to fermion interaction to the mass exclusion limits, and I will comment on the big quark proton content. The model used is Tobbe's model. It's just effective Lagrangian based on the Bess model. Bess means breaking electroweak symmetry strongly. This model was published in 80s. So the main features, besides the standard model fields, we have only triplet of new resonances. They are degenerated in mass. Its mass and total decay width depends on model couplings. That's why they are entangled. And this is the reason why the total decay width grows quickly with the resonance mass. In our modification of the Bess model, with resonance interacts directly only top and bottom quarks. And new resonance mixes with the standard gauge bosons. So for parameters of the Lagrangian, which are relevant to this talk, there is additional gauge coupling G double prime, which is associated to the SU2 HLC gauge group. The new triplet is treated as gauge field of this new auxiliary symmetry. Another free parameter is S, and what is concerning to resonance to and bottom interaction is proportional to G double prime parameter, and depending on the chirality, it's parameterized by BL parameter and BR parameter. There is additional P parameter, which takes values from 0 to 1, and it additionally weakens the interaction of right-handed bottom quark. So in the case when the BL and BR are equal to 0, I talk about non-direct interactions. They originate from the mixing. They are universal to all standard model fermions and are suppressed by factor 1 over G double prime. About total decay widths, depending on the mass and gauge couplings, the decay width lies, in the case of no direct interaction, decay width lies in these dashed belts. So we can see that decay width grows fastly with the resonance mass. And also the fatness grows fastly with the mass. Main decaying channels, these are two decays to WW and WZ bosons and the top and bottom quarks. In the case of no direct interaction, the resonance is decaying only to WW or WZ bosons. The variation ratio is 99%. So we calculated additional production of the new resonance followed by two-body decay. We assumed two production mechanisms, Drellian and vector boson fusion. And as experimental input, we used upper bounds on production cross-section, time variation ratio of all these channels. And we find that only WZ and WW in final states restrict the masses of new hypothetical resonance.
I will mention here this vertex. This diagram concerns the Drellian production of neutral resonance. And this is only the vertex where the big quarks interact directly with new neutral resonance. And one would neglect this contribution from big quarks because of a tiny amount of big quarks in the proton, as we did it at first calculation, but then we were surprised. So coming to results, so we have upper bounds, experimental curve, and depending on the theoretical predictions, everywhere where the theoretical predictions exceeds the experimental curve, the masses are excluded. In the case, for example, G double prime is equal to 16, masses below 1.6 dB are excluded. So this back dot corresponds to fatness 10%. And if we go to the right, the fatness is increasing with mass. So for example, in this case, the exclusion limits 2.2 dB is not so reliable because of the used method. So this picture is clear and simple. And the situation becomes more complex when direct interactions are switched on. And the unexpected behavior originates from the big quark content in the colliding protons. Have a look to the production cross-section. For the charged resonance, the red curve, and the neutral one, the blue curves, these four curves are describing the production cross-section. There is no direct interaction. And if we switch on the interaction, just this curve is enhanced by a factor, by one order of magnitude. So this is effect of tiny amount of big quark in the proton. It was nice for us. And here we also can compare the Drellian production mechanism against the vector boson fusion. In the range of the investigated masses, they are comparable. So the effect of big quarks on the resulting cross-section for the particular direct interaction pattern, if we neglect the big quarks in the proton, we would get the red dashed curve. If we take them into account, we would get the blue dashed curve. And the first case, we have no mass exclusion limits, and in the second case, we can have some. So you can compare it with the curve of the no direct interaction. In the first case, it's decreasing, and the second case, the cross-section is increasing. So it's qualitatively different behavior depending on the if you take into account big quarks or not. So if we take into account all possible direct interactions, it means that the BL and BR parameters in absolute values takes the values less than 0.1. The resulting cross-section is within the blue belt. And then if we fix the interaction, we can have no mass exclusion limits, or we can have someone. Here it would be interesting to see how the experimental upper bounds restrict the direct interaction for fixed mass. And we can see it on the next slide. For the fixed value of mass and P parameter, the allowed values of direct interaction can be seen in the BL-BR plane. These are green regions. For example, here, the direct interaction is allowed up to some strength. Here in this case, the center part is excluded, so no direct interaction is excluded. But it can interact directly with certain quark configurations. And here the BR parameter is not limited at all. So we can see that there are parameter space where the allowed region is very variable. And when we fix the direct interaction, it has, of course, impact on the mass exclusion limits. So to summarize, we have investigated mass exclusion limits for topics like vector resonance. There are general narrow width approximation limitations depending on the fatness of resonance. So we are not able to derive higher mass exclusion limits than 2.0 and 2.8 dB. For higher values, some other analysis has to be used beyond the narrow width approximation. Even when NVA applies, so we can't ignore the B quarks in the proton, and there are parameter space regions for which mass exclusion limits are below 2 dB. So thank you for your attention.
Okay, thank you, Joseph, for your presentation. So time for questions. Okay, maybe I have a naive question. I didn't quite get the role. I mean, it was too fast for me. Didn't quite get the role of this extra SU2 symmetry. So you said that's a strong dynamic. So you mean this SU2 is confining?
Yes. Yes, we assume that the new resonance is composite state of some new particles.
Yeah.
And this new gauge symmetry, which is auxiliary. So the new resonance is introduced into the model via this Hill local symmetry approach. We assume this new auxiliary symmetry.
Yeah, its coupling is relatively large. So, I mean, is this the reason why, the B component of the proton cannot be neglected in your limits from PP collisions? I mean, because rho is strongly coupled to the third generation, right?
Yes, the coupling of new resonance to right-handed B quarks are proportional, or left-handed also, is proportional to G double prime.
Yeah, yeah.
And then the BL and BR. And so anyway, we go up to limit of the perturbativity that we take the G double prime up to 25. Okay. We of course our calculations are at 3 level, and if we go to this border to G double prime 25, there is a question about the perturbativity, but we didn't check it yet.
Okay, thank you. Other questions?
You're welcome.
I have a very probably silly question, I'm sorry for that, but you show in slide number 11, yes, the impact in terms of the absolute value of the, considering the B quarks. I'm wondering if you have the comments on the kinematics of the final state objects, if the B quarks will play a role or not?
So the effect, this let's say discrepancy, is done because the strong interaction of B quark with new resonance. And when we use the narrow width approximation, the production cross section is proportional to decay width of the new resonance to the B quarks, and it's too high when we increase the parameters, and that's why this effect.
Okay, thank you, Joseph, again. It's time for us to move to the next speaker, which is Radovan Dermishek.
Okay, I'm here. Let me share the screen.
See you now. Yeah.
Okay, so I'm going to talk about some interesting signatures of the charged and neutral Higgs bosons in models with vector-like quarks. And talk is based on the work done with Enrico Lunghi, Navin McGuinness, and Seodong Shin. Let me start with some brief motivation. So among the simplest extensions of the standard model are models with more Higgses, and perhaps the 2Higgs doublet model is the most studied one, or various versions of the 2Higgs doublet models, and also models with more matter fields, and I will focus on models with matter fields that copy the known standard model particles and corresponding vector-like partners or particles with conjugate quantum numbers. So you can think about these as a complete new vector-like family added to the standard model. And there are many possible motivations for these new particles, that they occur in supersymmetry, composite Higgs models, and various phenomenologically motivated extensions of the standard model. But my personal motivation is that exactly this particle content, together with corresponding superpartners, provide an understanding of the values of all large couplings in the standard model from the IR fixed point behavior, starting from some large random boundary conditions. So let me briefly outline how it works. So at some high scale, let's call it the gut scale, but it's not really important, we can assume completely random, unrelated couplings in some huge intervals, gauge couplings between 0.1 and 0.3, so fairly large couplings and fairly large interval, factor of 3 difference between smallest and the largest. They are represented here in different colors. Similarly, top, bottom, and tau Yukawa couplings, again, in large intervals between 1 and 3, given here. And also Higgs quartic coupling is plotted here, but in supersymmetric models, it's related to gauge coupling. So there is a huge interval for the Higgs quartic coupling as well, but it comes from the interval for the 2 gauge couplings. And we can take this random mess and evolve it down to lower energies according to the RG equations of the MSSM with a vector-like family, complete vector-like family. And we find that at lower energy, somewhere at several TeV, this is an example of 7 TeV, but it's again not completely important. At several TeV, we find that it's no longer a random mass, but rather a distinctive pattern of couplings emerges. So you can see that the ranges for 3 different couplings no longer overlap. The hierarchy is clearly established. And more importantly, this distinctive pattern is actually compatible with the values of couplings that we observe, which are given by solid lines here. They are evolved to the same scale, of course, from the measured values. And similar thing happens for the top, bottom, and tau Yukawa coupling and Higgs quartic coupling. Below this scale of new physics, where we integrate out all the superpartners and the vector-like family, we just evolve everything down according to the standard model RG equations. And at the electroweak scale, we find a familiar pattern of couplings and masses. So clearly the 3 gauge couplings match well the observed values, and also the top, bottom, and tau masses, and also the Higgs mass. So 7 observables, which correspond to the 7 largest couplings in the standard model. can be understood from completely random boundary conditions at some high scale, at the gut scale, even although the unification is not important here at all, as long as there is a scale of new physics somewhere in several TeV where there is a supersymmetry and one complete vector-like family. So I find this very, very interesting that even these kind of extreme patterns of boundary conditions like alpha 1 here being 3 times larger than alpha 2 and alpha 3 at some high scale end up in something at low energies which very closely resembles what we actually observe. So this is my so make it to make this make a conclusion out of this in a more quantitative way. We can always adjust 3 parameters related to scales, the gut scale, the starting scale, the scale of new physics, and tan beta, the ratio of the vacuum expectation values of the 2 Higgses. We can always adjust these 3 parameters in such a way that no matter where you start with these parameters, none of these 7 observables that I mentioned would be more than 25% from the measured values. And if you start with unified parameters, still in all these huge intervals, but unified, then none of the 7 observables would be more than 15% from the measured values, no matter what. So I find this quite interesting, and this is my motivation for considering heavy Higgses and the vector-like quarks and leptons because they are absolutely essential in order for this to happen. And there are, of course, many searches for either heavy Higgses or vector-like quarks and leptons. And we heard about them a lot at this conference already. But I want to emphasize in my talk that sometimes searching for their combined signature can be more advantageous than separate searches for these particles. For example, we can search for heavy Higgses in the case of new quarks. And this is really great because new quarks can be pair-produced at the LHC with fairly large production cross-sections. It's just QCD, so it's as good as it gets. This is an example for bottom-like new quark being produced that subsequently decay through a charged Higgs or a neutral Higgs into standard model particles. And then charged Higgs and neutral Higgs decay in the usual way Higgs is decay in the 2Higgs doublet model. And this is just one example. And it's not only a possible process that can happen in the model that I'm considering, but actually in the 2Higgs doublet model type 2, these branching ratios can be easily close to 100%. The vector-like quark can decay through a charged Higgs or a heavy neutral Higgs close to 100% of the time. You don't have to do anything special at all for this to happen. Even tiny couplings that mix vector-like quarks and standard model quarks will make them decay. And close to 100% branching ratios are really abundant in random scans. And it can be also understood analytically, but I will not go to formulas. It can be found all here. So we have huge production cross-section, close to 100% branching ratio, which means that we can basically pair produce heavy Higgses with QCD size cross-sections, right? And that's really what makes these signatures interesting. And there is not just that one I showed you. There are several more that are interesting. So on top here, there are decay chains, possible decay chains of bottom-like new quark through either 2 heavy neutral Higgses, 2 charged Higgses, or 1 charged, 1 neutral Higgs. Similarly here are the signatures of possible decay modes of pair-produced top-like new quark, again through heavy neutral Higgses, charged Higgses, or 1 charged, 1 neutral Higgses. And all of these have very unusual final states like 6 tops, 6 bottoms, 4 tops, 2 bottoms, 2 tops, 4 bottoms. All of these are very rare in the standard model, like production cross-section for 6 tops is very, very small. And there are, of course, many possible ways to search for all these processes. You can design specific search for each process separately, but there is one thing that all of them have in common, and that's 6 bottom quarks in the final state. That's because top quark eventually will decay into bottom quark and W. So all of these processes have at least 6 bottom quarks in the final state. And that's the search strategy we focused on. The reach of one of the search strategies that we looked at is given here as a function of the mass of a new bottom-like new quark or top-like new quark on the right. This search strategy requires only 5 high-PT, well-isolated B-jets, and nothing else. It doesn't matter what else is in the event. The projected reach or sensitivity of the LHC with 100 inverse femtobars of data is given in blue, and green corresponds to 3 inverse attobars, the ultimate luminosity of the LHC. And different lines correspond to different Higgs boson scenarios. The solid line is for a new quark decaying through a neutral heavy Higgs. Dashed line corresponds to decays through a charged Higgs, and the line in the middle corresponds to the scenario when decays through all heavy Higgses are simultaneously open, and the branching ratios are kind of what you typically find when they have comparable masses, when heavy Higgses have comparable masses. No matter what Higgs boson scenario you consider, the reach would be somewhere in the shaded band. So we find that the LHC would be sensitive to new quarks in these decay modes up to about 2.2 TeV. And it does not depend much on the mass of the heavy Higgs, so it also translates to the sensitivity for heavy Higgses almost actually close to 2 TeV, almost the same limit as on vector-like quarks, just a little bit lower because the decays have to remain well kinematically open. So the high luminosity LHC will be sensitive to heavy Higgses, both charged and neutral up to about 2 TeV. But even with current data, the charged and neutral Higgses can be explored up to about 1600 GeV, 1.6 TeV. Okay, to conclude, models with more Higgses and vector-like matter are among the simplest extensions of the standard model, and they can provide understanding of the values of 7 largest couplings in the standard model, just from the RG flow, from the particle content of the theory itself. There are interesting combined signatures of heavy Higgses and vector-like quarks per production of new quarks, followed by decays through charged and neutral heavy Higgses, or some other combinations with the usual decay modes of vector-like quarks through ZW or standard model Higgs. I did not talk about those kind of signatures. Some of these signatures are the same as in other models with various top partners, composite Higgs, Z prime or W prime. You can as well imagine this heavy Higgs to be Z prime, this charge Higgs to be W prime, and it's perfectly fine model that would be a perfectly fine process that would be complementary to some of the previous talks we just heard. And if somebody is interested, the reach of suggested searches can be easily interpreted in such models. And we found that LHC with current data is sensitive to having neutral and charged Higgses in these decay modes up to 1.6 TeV, and eventually LHC will be able to probe heavy Higgses up to about 2 TeV. Thank you very much.
Okay, thank you, Radovan, for a nice talk. So it's time for questions. Don't be shy to raise your hands. Okay, maybe meanwhile I can ask you a question, like this pattern of infrared fixed point. That's pretty peculiar. So how fragile or robust is your setting with respect to like alterations of your field content? Like, could you throw in like extra vector-like meta and still get these nicely converging patterns?
So this corresponds to exactly one complete vector-like family. So whole standard model family and corresponding vector-like partner. Because of, I did not show the flow, I could show the renormalization group evolution of the couplings and it would be clear, but I did not have much time in this talk. If you throw much more into it, then the required scale of new physics would move much higher.
Mm-hmm.
Just so the couplings would still remain perturbative all the way to some high scale. And higher the scale of new physics, less predictive it will become. So if you, for example, compare prediction at the scale of new physics, which is whatever, in this case, 7 TeV, you see that the band, even for alpha 3, is much, much smaller than it eventually is at the electroweak scale. Because from this scale, everything starts again diverging.
Mm-hmm.
So things are only converging close up to this scale till you integrate out the new particles. So if you throw in much more, this scale would be getting closer and closer to the gut scale or to some high scale, and the scenario would be less and less predictive.
Thank you.
I would be very happy to talk more about that, but
yeah. Mm-hmm. Further questions? Very urgent ones. If not, let's thank again Radovan, and now we will switch the gears and start looking at long-lived particles at accelerators. So the first speaker of this mini block is Christian Peña. Yeah, we can see your slides in full screen.
Perfect. Can you also hear me?
I hear you. Yeah, thank you. Stage is yours.
Okay. Perfect. Yeah, so my name is Christian Peña. I'm very happy to talk to you today about searches for long-lived particles at CMS. So the first question that you ask yourself when you go look for long-lived particles is why to look for long-lived particles or LLPs. And then a natural place of knowledge to look at, it's the content of our standard model. So here you see numerous particles having different ranges of lifetime and masses. Most notably in this kind of lighter color are the tau, the B mesons, D mesons, the K long, K short, and then the pion and the muons. And you see that those are sizable lifetimes in the size of our general purpose detectors. And the bottom line of this slide is that these ideas can also be applied for beyond the standard model physics. So we expect long-lived particles to appear in models beyond the standard model. To see that in a better context, we look at one good example is to look at the pion decay into a muon and a neutrino through the W boson exchange in the standard model. Just to remind you, the lifetime or C tau is about 8 meters for this particle. And on the equation on the right, I don't expect you to understand everything, but the key point is that's 1 over the lifetime. So the smaller the numerator, the longer the lifetime, the larger the denominator, the bigger the lifetime. So you want those ingredients in order to have a sizable lifetime that you can detect in your detector. So you have small coupling in the numerator, and you also have compressed spectra or reduced phase space. That's a denominator. So that gives you sizable lifetime. And also in this case, it's the mass of the mediator or suppression scale, also called like that. And in this case, it's the mass of the W. And as I said before, these general concepts are also applicable to many beyond the standard model physics. And therefore, you expect new long-lived particles to have a lifetime, or at least can be treated as a free parameter. So therefore, we should go and look for them. And another very simple fact, but a very important fact, is that for experimentalists, the lifetime parameter that we'll be talking about, it's just a number. And depending on that lifetime, all the decays will be exponential in the detector, in the actual size that we see. And that will mean that they will decay in the different detector subsystems. So for a particular set of lifetime mass and the process for which was produced, then that will yield different decay ratios in different detectors. And therefore, you have to use all the subdetectors to make the most out of your signature. So the first one from the interaction point of these subdetectors is the silicon tracker. And in the case of CMS, it's an all silicon tracker, which provides, first of all, and it was designed to provide an outstanding 1 to 3% track resolution for PTs of like between 1 GeV and 100 GeV. And that also implies that you have to have a bunch of layers of silicon tracker in it. And that in turn gives you a good impact parameter resolution, or D0. The cartoon in the left shows you a secondary vertex in red, and then also it's a so-called impact point parameter or transverse impact point parameter D0, which tells you how far apart from the interaction point it is. And the plot on the right, it's actual CMS measurements, in which you can see that even down to 1 GeV PT for muons in this case, we are most of the time below 100 micron time resolution. This good impact point resolution will in turn become your ability to reconstruct secondary vertex. And you want to reconstruct secondary vertex because that's your signature for LLPs, and therefore will enable good LLP sensitivity. So that brings me to the first analysis that I will show today, which is a search for LLPs in the tracker decaying to displaced jets. The benchmark model in the right, there are many benchmarks on this analysis, but this is one of the favorite ones that we have, which is the Higgs boson produces 2 long-lived scalars in blue. And they, in general, they decay to 4 B quarks because the scalars carry the same quantum numbers as the Higgs when the phase space is allowed. And the general strategy of the analysis is that you reconstruct 2 jets are coming from one of the LLPs that decayed from this red point in secondary vertex. And then you match these jets to this, now you don't know yet, but there's displaced tracks. And then from the track information, then you make secondary vertex. And you use the information of the secondary vertex to suppress the standard model backgrounds. So more concretely now, after you've already used the tracks and you've matched them to the jets and you are able to reconstruct the secondary vertex, you can start to look at some of the quantities of the secondary vertex. And the left, now you see the vertex track multiplicity. And for the background, you see falling distribution as you move to larger numbers of track multiplicities. While for the signal, you see a much flatter distribution as you would expect more tracks to be displaced from the interaction point. There are other quantities in the analysis. For example, the one that you may be wondering, the more intuitive one is the distance from the interaction point or the primary vertex to the secondary vertex is the LXY. And actually we use the significance, we divide by the uncertainty on that measurement in order to use that quantity. And in the end, what the analysis does is it uses all or a lot of information of the secondary vertex, and it puts everything into a gradient boosted decision tree or GVDT. And that's how the analysis is done. And then you can see here that the signal piles up at very large values of the score, as you would expect, while the background just keeps falling in the GVDT score. The analysis is performed in a fully data-driven way, and it uses a lot of, it's a very complex analysis, very generic analysis, but in the end, we're able to reduce the background to a negligible level with a very high signal acceptance when we have a lot of trigger efficiency. And we don't see any excess over the standard model prediction. Therefore, we can look at what the sensitivity of this analysis is. So in this case, it's a generic 2-jet approach. So not the Higgs model. I will talk to that in the next slide. But I wanted to pause a little bit on these plots because you will see them throughout the rest of the talk. And there's a lot of physics built in it, and also the decisions of using the tracker instead of other subdetector. You see, first of all, that the peak sensitivity, which is the lower you can go in the y-axis, occurs between 10 millimeters and about 30 or 50 millimeter, which is what you would expect from a tracker-based analysis, because that's where If you go to 10 millimeters, you can reject a lot of background. If you go past 100 millimeters, plus a few centimeters, 10 centimeters, then you start to lose acceptance because you cannot reconstruct tracks anymore. And as you see that as you go, for example, to 1 meter, then you start to see all the curves go up in the y-axis, which means your losses sensitivity. Another important fact is that you see as the masses get lighter and lighter and lighter, that's the different colors in the plot. And the most stringent case is the black one. You start to see sensitivity loss as you go to lighter masses. And that's partly due to the problem that we have, that we don't have dedicated triggers, so we don't have a particular way to trigger this. We use just standard HT triggers at level 1. We do have a dedicated HLT trigger, but we still pay a price for that. So that's something to improve for the future. And this is the case of the Higgs. So same plot, now it's sensitivity, or in this case, is the branching ratio of the Higgs to these long-lived scalars. And we have placed very stringent limits for, again, this good range for the tracker between 1 and 50 millimeters for masses of the scalars between above 40 GeV. And in these cases where they decay to BB bar. And unfortunately for masses below 20 GeV, the sensitivity drops too much such that you go above a branching ratio of 1. So, and in the range between 1 millimeter and 50 millimeter for these masses above 40 GeV, this at the moment is the most stringent result. And another thing that I wanted to mention is there a new result from CMS, which is a deep neural network based LLP tagger. And I don't have, unfortunately, time to cover that here, but I encourage you to go look for that in our Twikis. And then moving on next from or farther away from the interaction point, there are the tracker results and sorry, the electromagnetic calorimeter results. So in CMS, we have an all crystal electromagnetic calorimeter. It played a crucial role in the discovery of the Higgs boson and the observation into Higgs to gamma gamma particularly. And the stringent results of the Higgs to gamma gamma decay posed stringent requirements on the energy resolution, and that in turn basically put a lot of constraints on the pulse shape requirements for the reconstruction of ECAL. And that, as you will see, enable good time resolution, which is good to discriminate signal from background and will enable LLP searches. So the first analysis that uses that, it's a search for now delayed photons. We use the ECAL information, that's what's shown in the plot on the left. The y-axis is the time resolution in nanoseconds. And as you move in the x-axis, you see that we approach about 100 picosecond time resolution for large energy deposits, in this case coming from photon. And another key signature is that for LLP decays, you can imagine them going in a different direction as opposed to those coming from the primary vertex. And then you can just that geometric information will create a shower, which will occupy now more crystals than a normal shower to discriminate even more signal for background. So we use time and the shower shapes to discriminate signal for background. In order to see that more clearly, I have some nice cartoons here. The left is what you will see now in the eta5 map of the calorimeter. The larger the box is, the more energy deposit in red, and you see the background in the left. It's nicely symmetric around what we call the seed crystal, which is the most energetic crystal, and the signal, which has this slanted angle geometry. You see that occupies many more crystals sharing a lot of energy. And now if you do some pattern recognition, you will see there that it has some kind of angle or information that you can reconstruct. It looks like an ellipse. So we actually, what we do is we use this so-called S minor and S major axis to discriminate farther signal from background. The final analysis uses on top of this slanted signature, the time resolution, as I said. So you can see that on the plot on the left, you see that signal prefers to be much more delayed than the standard model background, which kind of dies off at about 1.5 nanosecond. And then we also use missing energy in order to further reduce the standard model backgrounds and be able to perform the analysis to background free or like below 1 event. And that we have to ask for a PT or PT miss or missing energy requirement to be above 200 GeV. in order to achieve that. And this brings me to the result, which is interpreted in this GMSB model, where you have a long-lived neutralino now here. And that long-lived neutralino decays to a photon and a gravitino. The photon is the one that gives the signature that I described, and the gravitino leaves missing energy. Therefore, our cut is well motivated. And in the plot on the left, it has the axis inverted. I apologize for that with respect to the previous plot. That's the way it's presented. Y-axis now is C tau, and x-axis is mass. You can see with this result is it's the red one with the black line. So you see that we've extended the C tau coverage in the y-axis, but about 10-fold with respect to the previous results. We've also extended in the x-axis the mass range, and you can see here at the tip of this plot that the max sensitivity actually is achieved as where you would expect, which is the equal radius, about 1 meter. So this kind of makes sense. And another extra piece of information for maybe for a bit more expert level, it's that in this case for CMS, we added in 2017 an extra dedicated trigger at HLT to allow for 1 photon in the HLT menu, and that allow us to extend the C tau coverage by accessing more of the acceptance of these decays. And the last one, very shortly, that I will present as analysis, it's using the same kind of idea, using now the calorimeter and its timing performance, but now to reconstruct the time of a jet. So the left cartoon just shows you that you would expect from a normal jet some of the energy being part of neutral pions or kaons, and then they will decay back to photons ultimately. Those will leave energy in the calorimeter, and you can reconstruct those times using the same reconstruction technique that I described before, and then you have a timestamp for your jet. The part of the left, it's the actual result. You see now that we have to cut harder on the time in order to suppress the background to a negligible level. The cut in this analysis was actually 3 nanoseconds instead of the 1.5 with respect to the photons. And it also has the missing energy cut in the analysis. It's not extremely necessary to have that cut, but that's what it was used for this first result or iteration of the analysis. And on the result, again, we don't see any excess over the standard model with negligible background levels. And you see this result is it's the red and yellow contours with the black lines inside. You see that the peak sensitivity interpreted in this long-lived Luino case, 2.4 TeV. You see that it peaks the sensitivity again at about the place you would expect, about 1 or a few meters, which is the location of the calorimeter. And you see that it goes below theory expectation for this high mass of 4.2 TeV in that lifetime range. And another point that that's something that I kind of hinted before, you see, although this is the older result for the tracker-based analysis, you see some complementarity between the tracker and the calorimeter, because as the tracker starts to lose sensitivity as you approach 1 meter, then that's the place where the calorimeter is the most sensitive. And up to now in CMS, we have the best sensitivity for large masses with this calorimeter-based search, and it increases the acceptance to longer lifetimes. And that brings me to my summary, which is that we've performed a CMS tracker-based search that provides outstanding sensitivity for lifetimes in various ranges of masses, a very inclusive result in the range of 1 to 50 millimeters. Maybe there's a typo there. It goes actually a bit farther to like 50 centimeters, I'm sorry. And this CMS equal timing actually allow us to extend the lifetime coverage and access unique LLP decay to photons, which, for example, the tracker will not be sensitive to because of the neutral particle being the only detectable energy or signature that we have. And one point that I would like to stress that we've started to look at these signatures. We've done a very good job, but there is a lot more to do in the future. And that remains the case for run 2, obviously run 3, phase 2. And a few things that I wanted to highlight are LLP aware triggers that will be very key for run 3. Innovative LLP reconstructions. I mentioned one using machine learning or a deep neural network And then, of course, the new upgrades. And one of them that I hinted here was precision timing, which will now increase, but about a tenfold the actual resolution that we can use in the detector by the upgrades of the MIP timing detector. So I think that's all I have. Thank you.
Okay, thank you, Christian. We've got 2 hands raised, so go ahead, Rebecca.
Hi, thank you. Thank you, Christian. This was a very nice talk, to the point, and very interesting. So I have a little question that ties up with your last point and relates to the first analysis. That is that you say that you're using HT triggers, and that, of course, right. I mean, having like dedicated lonely particle triggers, I guess, will make things better. But have you actually checked how much better you can do with, like, for example, the kind of track trigger CMS can have for run 4 or anything that you are thinking for run 3? So that's the question.
Yeah, that's an excellent question. Yeah, so one thing to mention is maybe I said it too fast, but so we have the L1, the hardware, we call it L1 based leads. Those are just like jets, HT. So, but that feeds a dedicated HLT, and we have put in the menu like a displaced jet reconstruction in there, and that allow us to actually lower the thresholds for the signals. So we have like for the lighter masses, I think about a few percent or like close to 1% efficiency. So that's kind of the current status. That's only available because of this HLT improvement that we put in run 2. For run 3, we don't have the track trigger, so we're like planning to keep working on that. And one thing to mention is that we're maybe other detectors like the ECAL or the immune systems are actually working towards level 1 seeds, hardware seeds, and then you can feed off these cross triggers. So maybe the level 1 will be a level 1 LLP aware from the ECAL or the immune system, but then you will still have some decays that will be 1 LLP in the tracker and 1 LLP in the muon or ECAL. So that's something that we have to study. I don't have the numbers, unfortunately. And for the high Lumi LHC question, I think the numbers I've seen is that with respect to this Higgs model, which is the light mass, which I quoted 1% now, we can go like close to 10% or around that for the track trigger. So that will be a tenfold increase in acceptance. I don't know what that will translate in the final limit, but we'll have definitely like I think 10 times more events recorded. So
that will be nice. I mean, I don't know if anybody's following up this for snowmans, for example, but this is the kind of thing that I think is time to start like checking. So this was very interesting. Thank you very much for your answer.
Thanks.
Okay. Thank you, Laura. Rebecca, sorry, and Laura, do you have like perhaps a short question?
Sure, I'll cut one of my questions. Thanks for the nice talk. I was wondering if you could talk about how much sensitivity you gained from using the GBDT for the displaced vertex analysis, opposed to using more conventional discriminates from the input variables.
You mean here? Right. Okay. Yeah. So I don't have numerical values, but so there was a previous iteration of this analysis, and I remember, if I remember correctly, the improvement was non-negligible by changing to this approach, which is throwing everything into the GBDT, plus also having betas for the tracker material. So this analysis, as you see here, it says 95.9 inverse femtobarns. It's when it was done for the 2016 data set alone, and then now for 2017 and 18 separately, and then combined. For the next new iteration, it was added this GBDT and also these betas to trigger, to reject backgrounds coming from conversions. And if I remember correctly, those were like the bigger things that were changed, and the significance improvement was significant. So it's not negligible. I don't have a numerical number, unfortunately. I will have to get back to you to that. So, but it's not negligible.
Okay, thank you, Christian. I think we have to move on. So the next speaker of this section is Monica Verducci. Monica?
Yes, I'm trying to share my slides. Let me know if you can see it. And I should even start the video. Okay, so I think, let me know if I can start.
Sure, go ahead.
Okay, so I will talk about the search for long-lived particles.
Could you please go full screen?
Yeah, sure. Okay, so I will talk about search for long-lived particles and unconventional signatures with the Atlas detector. So first of all, just a brief introduction to the unconventional signatures and in particular to the long-lived particle searches. This class of particles have quite unusual and unique signatures, and this makes the searches of this particle extremely challenging.
Slides change, so maybe could you try to the full screen again, or like?
I'm making the full screen now.
We see no change in the.
Okay, let me.
On the screen.
Okay, let me do this way. So can you see now?
Yeah, now it's cool. It's
okay, so if it's okay, probably I can do in that way.
Sure, go ahead.
Okay. So mostly these kind of signatures are detector-based in the sense that we try to look at how the decay look like inside the detector and try to get the observables that can drive the identification on this. These kind of searches in particular need customized trigger and a self-made object for the reconstruction algorithm because they clearly need an ad hoc reconstruction and trigger, otherwise the standard trigger will not select these events. And last but not least, they need an ad hoc strategies, in particular for the background identification, since in most of the cases, the background is non-standard. So this means cosmic rays or beam-induced background. And this is quite challenging even. And of course, normally, and most of the cases, the background use data-driven estimation. On the right side of these slides, I just report a draft that mostly highlight the searches that I'm going to describe in this talk. So we'll try to report about the displaced leptonic vertices, displaced jets in a different part of the detector. So I will point the attention to displaced jets in ID, in the calorimeter, and in the mu spectrometer. And then we will see even the combination of some of these signatures, the displaced lepton jets and the heavy ionizing particle. In this talk, I will not cover the SUSY searches with the lonely particle that will be covered by Tova Holmes' talk just after. So moving to the next slide, starts with the displaced jet signatures. So looking at the left draft, we will try to figure out how these displaced jets can be actually identified inside the detector, depending on where the long-lived particle decays. So we will call displaced jet ID vertices all the classes of long-lived particle that will decay before or just in the pixel. So this will require a non-standard tracking system, and we will see non-tracking algorithm. We will see more details once we will move to the displaced ID vertices analysis. We will cover even a class of long-lived particle searches where the long-lived particle decays inside the hadronic calorimeter, just at the entrance of the hadronic calorimeter and on the edge of the ECAL. In this case, we will end up on an atypical jets with a narrow cone and with a well-defined fraction of energy between the electromagnetic calorimeter and the hadronic calorimeter. And last, we will see the displaced jets in the mu spectrometer. Mostly it's called displaced MS vertices. In this case, we will highlight the optimized tracking algorithm needed by the analysis to identify this kind of displaced vertices. Of course, this kind of displaced jet signatures participate in different analyses depending on the benchmark models, and in particular, they are using to fit and actually to set limits in the Eden Valley models and Stealth SUSY. Moving with the displaced jets in hadronic calorimeter. So this is the model used for the, let's say, for set the limits of the benchmark model used by the team. So this is an hidden sector model where you have actually an heavy scalar boson that can be even the standard model Higgs decays into a couple of long-lived particles that are neutral on the standard model. This, in this analysis, so in this displaced jet search, we have this long-lived particle that decays simultaneously into the hadronic calorimeter. So we have a very, let's say, signatures defined with two atypical jets with a narrow cone, since the jets is originated really close to the hadronic calorimeter. But since it's inside the hadronic calorimeter, this jet has a very low EM fraction. So mostly these are the two ingredients to identify this jet, along with the fact that the long-lived particle is neutral, so we don't have any track associated with the jet. The analysis starts with a dedicated trigger called so-called calibration trigger that actually use this kind of ingredient as the fraction of low EM fraction with respect to hadronic energy and no tracks associated with the jet. Then has an event selection based on boost decision tree that mostly inside has some ingredients, some observables related with the jet's information. And then the background, it's estimated by using the ABCD method. Just highlight that the background here are mostly non-standard, so due to cosmics or beam-induced background, of course, along with the multi-jets. Moving to the displaced jets in the mu spectrometer, in this case, the analysis looks for one or two displaced vertices in the mu spectrometer. The model interpretation can be different. Here we have different approaches depending on if we look for two muon vertices, simultaneously two muon vertices, or we look at one muon vertices plus MET for the baryogenesis model, or plus two prompt jets if we are trying to identify and to set the limits in the stealth SUSY. The searches for two simultaneous MS vertices can cover and can be interpreted in all the models explained here. In this case, just to highlight that the analysis has a different algorithm to make a tracklet, to make this segment of muons inside the muon spectrometer that mostly it's based to some searches of vertices with additional quality cuts on the precision chambers and the trigger chamber hits. In this case, as well, the main backgrounds are QCD, multi-jets, and the non-standard events actually beam-halo, so beam-induced background, and cosmics. Last, let's say, signatures driven by displaced jets is the analysis that actually combined displaced jet mu spectrometer and the displaced jets in ID. The model interpretation, it's the same as seen before. So we have an hidden sector that actually decays into as this heavy fermion, heavy scalar boson that decays into these two long-lived particles. In this case, one long-lived particle decays in the ID and the other decays in the mu spectrometer. So for the mu spectrometer search, we have the same approach described before, but for the decays inside the ID, so the other long-lived particle decay, we have an ad hoc tracking algorithm, so-called large radius tracking, that actually run on the leftover hits by the standard tracking, but with a looser cut on D0 and Z0. In this case, in addition, we have, of course, in the cut flow, in the selection, additional cuts on the mass and the number of tracks for each vertex. In this case, the main backgrounds due to the displaced jets in ID come from the interaction with the material from hadrons. So in this case, it's quite crucial to have a clear map of the interaction with the inert material of the detector. Moving to the combination, we add some combination of the limits in these plots without really going to each details, because there are several combinations here. Just I try to highlight some of them. You can see that in principle, starting from the displaced jets in hadronic calorimeter, displaced jet in mu spectrometer, we make even the combination of one jet in hadronic calorimeter and the other one in mu spectrometer. So mostly it's the green curve in all of this plot. And in the bottom one, you have the combination of the displaced jets in the tracking system plus a jet, displaced jet in the hadronic or in the mass. All of them, of course, belongs to the standard model heavy scalar boson in the hidden valleys scenario. Next search is a dark photon. In this case, we look for a dark photons. So it's mostly it's a light neutral particle that decays into fermions. So in this case, the final state can be leptons or electrons or light hadrons. This kind of searches, as you can see, it's driven by the FRVZ, Falkowski, Raderman, Volaski, Zuperman model. So these are the benchmark model with 4 or 2 gamma dark as a final state. The analysis looks for gamma dark decays into the mu spectrometer. So this will end up in muons in the mu spectrometer, so mostly segments in the mu spectrometer. And the other one, gamma dark decays into the hadronic calorimeter. In this case, will end up in a signature very, very similar to the displaced jets in hadronic calorimeter described before. Different combination in sense that we can have a gamma dark decay in the mu spectrometer and the other in hadronic calorimeter, or both in hadronic and both in the mu spectrometer. So for the background, we should try to define a different class of backgrounds depending on the final states. So for the muonic displaced gamma dark, we have mostly cosmic muon that actually can mimic the signature in the mu spectrometer. Or for background, let's say background for hadronic gamma dark, we have mostly BIM-induced background and QCD. So here it's the final way to get the estimation of the background. It's of course, even in this case, the driven ABCD method. Let me highlight the plot on the bottom left, where we have the limits set in a plane where you have on X the dark photon mass, and on the Y the epsilon, that is the coupling for, let's say, the mixing between the standard model and the hidden sector. So here you can see even the comparison between the results obtained in run 1 and what we get for run 2 at a different branching ratio of an Higgs standard model. In this case, decays into 2 gamma dark. Moving to one of the latest results, we have the reinterpretation. So the displaced jets in hadronic calorimeter has been preserved by using recast, and thereafter this has been used for mostly constrain other models that has not been studied by the displaced jets analysis itself. So the results has been used to make a constraint to the stealth-SUSY model, the Higgs portal baryogenesis model, and the long-lived dark photons. Here just a couple of examples on how the recast of these models look like, and on top you have the dark photons with the recast of the results by using the hadronic calorimeter jets analysis, and on the bottom left you have the displaced MS. In backup you have other plots and other limits with all the possible combination for the other models. Just to highlight that with this reinterpretation, the existing limit obtained by the direct analysis have been moved to shorter lifetime and decay length. So there is an improvement to shorter lifetime with the recasting. Moving to something different, so the heavy neutral lepton. This kind of search is produced through the mixing of muon or electron neutrinos. This analysis actually has 2 main searches, the prompt one and the displaced. In the prompt signatures, we require 3 leptons that are mostly mu E or EE mu, and the analysis, the selection is driven by EV on the same flavor opposite charge topologies. For the displaced analysis, displaced signatures, we look at the prompt muon, in the case actually obtained by W decays that triggers the event. And then we require a dilepton vertices that is displaced, vertices composed by mu mu or mu electron. So the signal region for the 2 searches, of course, is different depending if it's displaced or if it's prompt. In the displaced case, we have an additional, I think one of the main points, it's the cut on the invariant mass of the displaced vertices that should remove the metastable states and actually the interaction with the inert material. And for the signal region in the prompt searches, there are a cut on the primary vertex and a cut on the invariant mass of the 3 leptons. In this case, for the displaced ID vertices, as it's said, for the displaced jet in ID, we have the large radius tracking algorithm used for this kind of events. As seen before, we don't have any evidence on new physics, and in this case, the teams set limits on the coupling strength by using the prompt and the display search. Last analysis reported here, it's the magnetic monopole and the high electric charge object HEC. In this case, the analysis is interpreted in terms of Drell-Yan pair production by using stable particles with two spins hypotheses and different masses ranging from 200 GeV to 4000 GeV. In this case, the two observables that actually drive the search is the energy in the TRT, because they have an high ionization energy coming from the tracking system, in particular from the TRT, and the shape of the energy deposit in the electromagnetic calorimeter, that it's really pencil shape energy in the clusters. Even in this case, the background, it's due and it's obtained by the ABCD method. And on top right, you have the plane here, where you have the distribution by looking at the two observables used for the ABC, that is the fractional high threshold charge in the TRT on the Y, and on the X, you have a W that is a variables linked to the energy deposit and energy shape in the calorimeters. So I'm moving to the conclusion. I try to cover some of the unconventional searches in Atlas, so the displaced jets, HNL, dark photons, and the monopoles. Of course, the program of the unconventional signatures in the SOTIX searches are wider, but here I just try to highlight some of the results. As you can see, I try to highlight mostly the unique and unusual way to try to identify the events and try to estimate the background. As seen, we don't have any evidence, so no significant deviation observed by using only 15 and 60 data taking for run 2. Of course, all the teams are working to improve the statistics by using the for run 2. So mostly all the analysis we will follow up with the complete luminosity for run 2. That's all, and thanks.
Okay, thank you very much. So it's time for questions. I can see a hand raised by Rebecca. Rebecca, please.
Hi, yeah, it's me again. So I'm just interested in this. So thank you very much, Monica. These were a lot of results, and some I, of course, was aware of, but I have a little question about slide 6.
Yes.
It's one of the first. So yeah, this one. So in here, you said that you have two displaced vertexes. One is in the muon spectrometer, and the other one is in the inner detector. And I was wondering, it feels a little bit unbalanced. So I was wondering if it's because the signal is like this, or it's just a compromise in order to, profit from the trigger. So if you could elaborate a little bit on this, if you are involved in the analysis, and maybe just give us a small summary of the sensitivity of this one, because I think it's not super clear to me from here.
Okay, yes, this I'm not involved in this analysis directly. This mostly, it's the same model that you have seen in all the class of displaced jets. So in this case, the team, I don't know if I have probably in the slide after, some sensitivity, but in this case, it's the combination of, but here you have the sensitivity for the ID, bottom right. So the limits set in this case, depending on in this case, the long-limb particle. So this is the C tau. And in green, you have the search for the ID, so mostly what we discuss. And in the other case, you have the possible combination, for example, with the color ratio that actually is missed. So they are just exploring the tracking system plus the muon spectrometer, but not, for example, tracking system plus jet in the calorimeter. So this mostly it's the possibility for a combination of this. And I don't know if this answer to your questions.
It's because the reference in this thing seems that it was submitted to arXiv like 1 year before than the previous. So this is what I was wondering of if the analysis of the previous slide has like improved over this, or is, I mean, I was maybe a bit confused about this. Yes, but I can also follow up myself offline.
Yeah, the latest, I think it's coherent with the last slide. Just a question of how we publish this. I don't know if there is someone from the analysis that can correct me if I'm saying something wrong. But as far as I can understand, this should be mostly correct, these limits on the bottom plot, bottom slide on 7.
Thank you very much, Monica.
Okay, thank you, Rebecca. There's a hand raised by Christian.
Hi, yeah, can you hear me? So thanks for the talk. I had a question on the I think almost last part on the heavy neutral leptons. More generic question actually. So it's do you know if there are plans to target for the displaced case like longer decays? Like I'm thinking about that at least Atlas has the ability to reconstruct muons as muons when they decay in the muon system as opposed to CMS or for example for electrons and other particles, so because of the no material in the muon system. So I was wondering if there are plans to do that as well, to try to cover.
You mean to extend the, let's say, the vertices not at the 300 millimeter, but just moving to muon spectrometer? That's your question? Yes,
basically, because there is this like corner parameter.
Yeah, as far as I can no. The only extension that we're expecting for a full run 2, it's the possibility to have in the displays signatures the electrons. So electrons as a prompt that is missed here, for example.
I see. Okay, thanks.
Okay, I don't see any other hands. So let's move on. Actually, from CERN to Fermilab. Thanks. Yeah, thank you very much, Monica. Indeed. The next talk is by Paweł Guzowski on long-lived particles at microboon.
Okay. So thank you. Yes, I want to thank the organizers for let's move this video out of the way. Thank you to the organizers for giving me the opportunity to talk to you all today about some exciting new physics results coming out of the microboon experiment. I'm not a collider physicist, and I assume a lot of you are. So microboon itself is a neutrino experiment running at Fermilab, and it's primarily designed to study neutrino interactions on argon and to search for evidence of a light sterile neutrino. And microboon sits in a booster neutrino beam in Fermilab, where 8 GeV protons hit a fixed target. Pions and kaons are produced, and these pions and kaons decay to neutrinos. It also sits off-axis slightly from the NUMI neutrino beam, which is a higher energy beam of 120 GeV protons hitting the target, but a very similar principle. And these are very high intensity beams with 10 to the 21 protons on target of exposure. We have 7 talks at ICHEP this year. So if you want to hear our neutrinos results, I invite you to come to them. I also invite you to come to our neutron anti-neutron oscillation talk, which may be of interest to some people in the BSN community. However, what most of you probably haven't realized, even if you have heard of microboon, is that it's actually sitting in a potential high intensity beam of long-lived particles. Now, these are slightly lighter long-lived particles, sub-GeV long-lived particles, and have much longer lifetimes of order milliseconds than the 2 LHC talks we've just heard. And they come mainly from pion and kaon decays, if they exist. And they can travel the few hundred meters or so and decay inside microboon, where we can observe them if they decay to charged pions and charged leptons. And so the main focus of my talk today will be 2 specific models of long-lived particles, heavy neutral leptons and Higgs portal scalars. This last model, I'll be showing you brand new results released today just for this talk at ICHEP. Microboon itself is what's called a liquid argon time projection chamber. This is essentially a 21st century version of the bubble chamber with digital technology. So you can take these beautiful pictures of neutrino interactions happening with like millimeter scale positional resolution. The active volume is 50 cubic meters. It's actually got quite a long readout of 2.3 milliseconds to read out one of these events. So that we do actually have a PMT system as well to provide the nanosecond resolution timing for the scintillation light happening in the interactions. And for more details, please come and see our present detectors track talk by Relitza. So microboon has been running for 5 years. Around halfway through that runtime, there was a cosmic ray tagger installed. This is essentially a plastic scintillator paddle around the detector to tag any cosmics coming in. So, as I mentioned, microbins we've been running for 5 years. We have these 5 runs. And the data sets I'll be talking about from what's called run 3. A couple of years ago, this was for the heavy neutral lepton search for BNB data. And also for the scalar search, we've analyzed a small fraction of run 1 and run 3 data from the NUMI beamline. This is the only slide I will have on the heavy neutral leptons, because there was a talk already yesterday in the BSM session by Owen. I invite you to come and watch that talk in the replay sessions again, where Owen went through in the whole talk devoted to this analysis. These are the limits we set on the heavy neutral leptons there. Significantly lower masses than compared to the collider talks we just heard. Sub-GeV, as I mentioned, but we do have some sensitivity there that's competitive with other experiments. And I'll mention here as well that we've only analyzed one particular production channel and one particular decay channel, and only one of the beamlines. So we do have a lot of data here that we can still process and get better results. However, what I'd like to switch now to is the main topic of this talk, and that's the Higgs portal model. And this is a new physics model where you introduce a new dark sector scalar, let's call it S here, for example, and it mixes with the standard model Higgs boson. And via this mixing, the Higgs becomes a portal to the dark sector, and that's why the model was given its name. But also because of this mixing, the scalar acquires the Yukawa coupling to the standard model fermions via this mixing angle as well. And that's how you can produce and observe it as well in standard model detectors. For the analysis I'll be presenting, we're looking at masses below the dimuon threshold. So around 100 to 200 MeV scalars. The lifetimes here are hundreds, or decay lengths, sorry, hundreds to thousands of kilometers. So again, quite a lot longer distance than the collider talks we just heard. These masses and in our beamline, the scalars are mainly produced by kaon decays, kaons to pions plus a scalar. And below the dimuon threshold, we're looking for electron-positron pair production in our detector. The specific search strategy we're employing for this analysis was actually first proposed by a group of theorists in this recent paper. So we'd like to credit them with coming up with this strategy. And they proposed to search for, or to use kaons decaying at rest in the hadron absorber of the NUMI beamline. And this is essentially a 5 meter deep block of steel that stops any remnant protons or charged mesons that remain in the beamline. And then these could produce kaons as well that decay at rest. And this gives rise to monoenergetic scalars that fly away isotropically from the hadron absorber around 100 meters away from our detector. And these monoenergetic scalars give rise to a strongly peaked opening angle in our detector, and also a sort of delayed signature. There's around 600 nanosecond delay between our neutrino backgrounds in the detector and any signal decays. And we can use this as a control region for testing our reconstruction and selection before unblinding. Here's an example of what an event looks like in our detector. So you have your neutral scalar coming in, and it decays to an electron-positron with quite a large opening angle. And this is the sort of decay topology we're trying to reconstruct, essentially a kink topology with a directionality in line with the hadron absorber. And we use what's called the Pandora pattern, Pandora particle flow framework to do our reconstruction. And this is used in many liquid argon experiments. So what Pandora does is to group together reconstructed objects into what's called slices. And then we try to identify, of the many slices in an event, which one of those correspond to or are coincident with the beam spill signal. So we produce this hypothesis of what the scintillation light should look like for the slices, and try to match it to what was actually measured on the PMTs itself. And that way we can identify the beam coincident objects, reconstructed objects in our detector. As I mentioned, for run 3, we also had a cosmic ray tagger, and that way we can identify coincident hits to identify through-going cosmics and reject those as well. Once we have a slice that's passed all these pre-selections, we also try to pair up the objects in the slice, making sure the endpoints of the two objects are less than 5 centimeters. And we place a candidate decay vertex in between this distance of closest approach. And this reconstructed vertex has to be within the active volume of the TPC. At this stage, we take all possible events and we use a BDT to filter out signals from the backgrounds. We train 2 different BDTs, one against this, the main background of cosmic interactions. That's represented by this gray area in this distribution. It's the pure cosmic background. And another BDT trained against the simulated neutrino background, represented in blue in this distribution. And the BDTs have been trained to be approximately mass agnostic by having uniform masses in the transmodel between 100 and 200 MeV. And we verified all our input variables for the BDTs using that 600 nanosecond prompt control region I mentioned a couple of slides ago. So we trained the BDTs. We did this all blindly. We set BDT cuts to optimize our sensitivity. And then we unblinded a couple of weeks ago. And we observed 6 events in our signal region with a background expectation of 2 plus or minus 0.8. One of these 6 events we reject because its PMT timing is just before the beam spill window. And we've also hand scanned the remaining 5 events, and they're all consistent with being background rather than electron-positron decay products. These are the BDT distributions showing you our cuts and the events surviving. You can see generally good agreement of the BDT between the data and our model prediction. So we use these 5 events to set an upper limit on the model parameter theta and as a function of the scalar mass. And this is the observed upper limit at the 95% confidence level that we obtain. You may be wondering how this compares to other experiments that have searched for this particular model. And to answer that, I'll just take a quick detour to Japan, because recently, just last year, the Koto experiment, which is running in Japan, has reported an anomalous excess of neutral kaon decays to neutral pions and some missing energy. And this is at the level of 2 orders of magnitude higher than the standard model prediction. There was a talk yesterday in the flavor track sessions describing this experiment and this result. And so there are slightly updated results. So what I'm about to show you is slightly out of date with respect to this line. But you can use the Higgs portal model to explain this anomalous excess if you have a neutral scalar that escapes the Koto detector before decaying. And so this blue line represents the model parameters you would need to explain this anomalous excess within this model, plus or minus the 1 sigma. And these are some of the exclusion limits that other experiments have placed on this model. There's charge kaon decay measurements, and also the charm limit from 1985 is a reinterpretation of an axion-like particle search. And when we place our microboon result on top of this plot, this is our 95% contour limit in terms of this model. So you can see within the remaining allowed parameter region, we can now exclude at 95% confidence this remaining allowed region for the central value. And we have this public note that's just been released to describe this analysis in more detail. And this is the first result in this region in 35 years. So to summarize here, Fermilab neutrino beamlines are potentially also high intensity long-lived particle factories, and microboom could be discovery experiments for these types of particles. We recently published our first search for heavy neutral leptons, and I've just shown you today new competitive results for Higgs portal scalars in the 100 MeV to 200 MeV range. And we can exclude the Koto central value at 95% confidence level, the remaining parameter space. So I'd like you also to stay tuned for future results coming out over the next year or two, including updated data for these 2 models, and other BSM models, for example, dark photons, inelastic scattering of dark matter, milli-charged particles, and neutron-antineutron oscillation. So stay tuned. Thank you very much.
Okay, thank you very much, Pavel, for the nice presentation. We've got three hands. So who was first? I think Daniel.
Hey, thanks, Pavel, for this great talk. So I have a couple of questions. First of all, one comment. So the Koto experiment now believes that one of their events, it's not right. So the blue line with the central value, it's going to move down. So it's likely that after that's taken into account, then your bounds will still not exclude the explanation 95% confidence level. So that's just one comment. Another couple of questions that I had is that you seem to have, after you unblind the data, 2 events, you expect 2 events, you have 6. So what's the significance of that if you interpret it as an anomaly?
So we use 5 events rather than 6 because one is an obvious cosmic.
Right.
The significance there is less than 2 sigma. It's between 1.5. So we have looked at all of these events, and they all look like stopping muons from cosmics or neutrino interactions.
Okay.
But so we still use that for the limits because we'd have to hand scan our Monte Carlo to realize what our efficiency is in our systematics on hand scanning. So we keep all 5 events, but it's not significant.
Okay. And how much do you trust your signal generation? You have to generate these kaons that are produced at rest in the target that you do not take from data, right? So that you simulate. And on top of that, your background seems to be pretty large. So how much do you trust your signal generation and your background estimates?
The signal generation, so there was a mini boon measurement of the kaon decay at rest.
Okay.
A couple of years ago, they measured the neutrinos coming from there.
Oh, I see.
And we're also doing that in microboon. There should be results of that in the coming year or so.
Okay.
In terms of the background, we measure neutrino interactions. So the cosmic background is data driven. That's the big gray one, and the other backgrounds are simulated. But also we have different channels to measure those neutrino interactions, especially as we're a neutrino experiment and we're trying to see evidence of a light stellar neutrino.
Okay, thank you.
Thank you. So next one was Kari. You're still interested in asking question or?
So Daniel ended up asking the questions that I was going to ask. So thank you for that.
So
and thank you for your answers.
Okay. This one more, Ahmed.
Hey, thanks for the interesting talk. I had a couple of questions. One was, is there any interest right now in Microboon in doing a search for the Higgs portal scalars that are produced on axis, or has it already been determined that that's not going to be as useful as this interesting kaon decaying at rest technique that you guys tried? And I also had another question to go back to the HNL search about how easy it would be to reinterpret it in terms of something decaying to 2 muons. Is the muon pion discrimination very important, or how well do you have a sense of it? So thank you.
Quickly to the second question, yes, we can reinterpret these as dimuon searches. The muon pion separation on microboon it allows us to treat this as a dimuon interaction, and we do have some students working on that as well. The students that are working on heavy neutral leptons will be doing that as well. In terms of the on-axis, we do actually have other students as well working on the on-axis results. We do expect that to be more sensitive. It does suffer from more neutrino background, so we have to take some more care into trying to really understand that before releasing results. But we expect that to be more sensitive. So that is the next generation of these results should cover that.
Perfect. Thank you so much.
Thank you. So I'm afraid we need to move on now. So next talk is by Tova Ray Holmes. Tova?
Hi. Let me share my screen 1 moment. Okay. Okay. Can you see that slide?
Yeah.
Okay, great. So hi, I'll be talking today about searches for SUSY with long-lived particles in ATLAS, so a little different perspective than the one that Monica gave. But I'll start probably in a similar way to how Christian started by talking about a little bit about why we care to search for long-lived particles. So here's a plot of the lifetime of the standard model particles as a function of their mass. You can see the c tau on the y-axis, so roughly the distance they would travel. And all of these particles are created at the LHC and studied in ATLAS. And up at the top, we have our stable particles, which are the lightest particle with a particular quantum number. And then in between, we have our metastable particles. So here I've circled the neutron, where of course the neutron is metastable. It lives for about 15 minutes because it has to decay through a W boson, which is so much heavier than the mass splitting between the up and the down quarks. But in general, you can have metastable particles for a number of reasons. You can have highly virtual mediators, very small mass splittings, or very small couplings for other reasons. And then all the way down the bottom of this plot, you have very promptly decaying things like the Z boson. From the experimental point of view, though, it looks a little bit different. At the top, we have particles that look stable in our detector. At the bottom, we have particles where they decay more quickly than we can actually resolve, so the decay products look prompt. And in between, we have this region where c tau is about 1 meter, which is particularly interesting because the length scales here are the same order as our detector. So these particles can decay really anywhere in our detector, and we can get a range of different signatures. So these long-lived particles exist in the standard model, but the question, of course, is could they also exist in BSM physics? And the short answer is yes, of course they could, because beyond the standard model particles could be long-lived for the same reasons as the standard model particles, the small mass splittings, the small couplings, or the virtual mediators. And this happens in all kinds of theories of new physics, but I'm going to focus on one, which is supersymmetry. And supersymmetry, of course, is not just one model. It's the relationship between fermions and bosons that can manifest in many ways. So let me give a sense for these different types, for what these different types of SUSY are. Here are a few examples of different flavors of supersymmetry that can lead to particles with macroscopic lifetimes for the reasons I mentioned before. So the three I'm going to focus on here are gauge-mediated symmetry breaking, anomaly-mediated supersymmetry breaking, and split supersymmetry. And so in these cases, though not in all models of supersymmetry, there is one stable particle, that's our lightest supersymmetric partner. And that, of course, is a long-lived particle, but it's neutral, so it escapes detection, and usually we look for this with a missing ET signature. But in these particular models, it's not just these LSPs that have macroscopic lifetimes. So in the plot on the, or in the diagram on the left, in our gauge-mediated supersymmetry symmetry breaking, we have a tiny coupling, the Planck scale section of the coupling to the gravitino, and that gives our leptons a long lifetime. In the anomaly-mediated symmetry breaking, there's a very small mass splitting between the chargino and the neutralino, which gives a long lifetime to the chargino. And finally, in the split supersymmetry case, the squarks are at a much higher energy scale than the gluinos, but the gluinos must decay through them, so the gluinos get a long lifetime. And each of these models can produce a range of different lifetimes for these particles. So I hope I've motivated the idea that SUSY is a natural place to look for long-lived particles, but now let me spend a moment motivating SUSY. So some reasons why we love SUSY. It gives a solution to the hierarchy problem, gives a dark matter candidate. It's a particularly elegant mathematical concept, and should it exist, it would give rise to many different particles with complex and unpredictable spectra. So if we started seeing it, it would keep us all employed for decades. And so to contrast that, the real reason we don't love SUSY is just that we thought it would be easier to find. But to me, given the range of ways that SUSY can appear, I don't think this is a disqualifier. So while there are lots of other BSM models that can produce long-lived particles, SUSY is a great benchmark because it exists in so many variations, which means in order to look for it, you have to basically look for everything and cover many of the other models. Okay, so let me back up for a moment and talk a bit more about what makes models with long lifetimes so much harder to search for. So varying lifetimes creates these fundamentally different signatures in our detector. In the plot on the right, you can see the probability that a particle is decayed for a particular energy and mass of a particle as a function of the distance traveled the detector. And so in particular here, you can see that for a range of lifetimes, most particles will almost entirely decay in the inner detector, but for some of them will decay almost entirely in the calorimeter, some almost entirely in the nuance spectrometer. And so you really have all of these variations. And each of those variations has to have dedicated searches for each type of signature, which adds a new dimension to the type of searches we need to cover all of our SUSY scenarios. And in particular, one challenging thing is that many of those variations include signatures that we didn't design Atlas to reconstruct. So put simply, adding lifetime is hard because it means that each model has different signatures and you have to figure out unique ways to cover them all. So in practice, here's what this looks like. So for one particular model, a split SUSY model produces a gluinohadron, which decays to jets and missing energy. And in order to cover the full lifetime space, we had to do 3 searches with completely different strategies. So over all the way on the left, the lowest lifetime, we have limits from a prompt jet search. After that, it's quickly overtaken by something that specifically looks for displacement, so a displaced vertex search. And finally, covering the very high lifetimes, you directly look for a long-lived particle with highly ionizing track searches. And because this requires so much dedicated effort, not all models have been as thoroughly covered. So for each different model and different signature, you need another set of searches. So for example, you could take this model, we're pair-producing stops, which decay through an R-parity validating coupling to a quark and a muon. And it's very similar, still produces an R hadron from the stop, but the final state has muons and fewer jets. So the large lifetime can still be covered similarly by looking directly for that R hadron with the highly ionizing tracks. But the smaller lifetimes require a new strategy because you have displaced muons now. So this search looks for displaced muons plus displaced vertices. And with the introduction of the displaced muons, you also introduce a brand new type of background, which is cosmic ray muons. So in the plot in the middle of the slide, you can see that in some regions for this analysis, cosmic rays completely dominated the background contributions. And so in order to handle this, they developed a highly efficient cosmic tag to help reduce this background, which takes advantage of the geometry of the cosmic muons. So it looks for activity on the exact opposite side of the detector from the muon that's detected. And with that, we're able to produce very strong limits across a wide range of lifetimes, you can see in the bottom right. And this paper was newly accepted to PRD. Okay, so now there are plenty of models that don't just produce muons, but also electrons. For example, like this R-parity violating on the top left. And adding electrons to the signature further complicates the search. So with the muons, in the muon spectrometer, we have extremely clean signatures with very little bremming and few fix. But in the electrons, we are both swamped with activity in the ID and calo, and brems and conversions create genuine displaced electrons in our detectors, which, as you can see in little diagrams in the bottom left, look exactly like a displaced electron if you don't reconstruct them fully. So what this search did was use a likelihood-based identifier of electrons that didn't depend on zero, but could still discriminate between these situations. And with that, this search was able to set limits for several orders of magnitude of lifetimes as well. Now, what happens if we wanted to compare these two results, though, which should both be sensitive to both of these models? Or what if we wanted to compare to a third model that we haven't actually placed any constraints on? Well, in general, the LOP signatures we search for tend to be generic. We're often just looking for these displaced objects and not a whole bunch of fine details about the missing ET or the overall energy that comes with most SUSY searches. So it can apply to many models, but it's typically not possible for a search to interpret in all of them. And in particular, because our long-lived particle Monte Carlo grids have this extra dimension of lifetime, just the computing power required to do that makes it impossible. But it's very hard for a theorist, for example, to reinterpret after the fact because of the strong efficiency dependency on many different variables. And so the solution that Atlas has come to here is to provide many multidimensional efficiencies and kinematic distributions for the models that are used. And so far, this strategy has been enthusiastically embraced by theorists, and we've gotten lots of reinterpretations on the results we've released with this strategy. But even better, we've recently been able to use recast. This was mentioned a little bit by Monica, to reinterpret along with particle result that was done in the exotics group with a new SUSY model. So recast is a framework that lets us preserve the background estimates, the signal sample processing, and the cut flow. And if a new model is thought of later, we can simply run over it and produce new limits. So in this displaced jet search, I won't get into the details of it, but it identifies unusual activity in the calorimeter with a complex BDT-based identification that's very hard to parameterize. But because it was successfully preserved in recast, we were able to reinterpret this with a stealth SUSY model, where a small mass splitting in a singlet superfield results in long lifetimes. So the initial search was generic enough that the new limits could be set on this model with this reinterpretation, and you can see it on the bottom right. And in some regions, it overtakes another search that explicitly targeted this model. So using this method, we hope to be able to expand the number of models we can limits on, covering more of the LLP space. So in conclusion, long lifetimes are a common feature of SUSY models, which means more unique searches are required to cover the full space. These exotic-based object searches are often broadly applicable in principle, but very hard in practice to reinterpret. So a lot of work has been done on Atlas with parameterization and recast to make this possible. But of course, reinterpretation materials can't do all of the work. They can't cover brand new signatures. So please stay tuned. There are many new Atlas LLP searches on the horizon. Thank you.
Okay, thank you very much, Tova. Time for questions. I don't see any so far. So maybe I can have just a very naive, like outsider's question. I think at page 14, you are complaining a little bit that the Atlas was not really designed for these searches. So was it really Atlas or the trigger system?
Did you say, was it Atlas or the tracker system?
The trigger system.
Trigger system. Yeah, great question. So I would say one thing that makes some of these searches challenging, particularly as you go to large lifetimes, is that the way that we identify particle in Atlas depends on having all the complementary information from the different vectors. So you can differentiate a photon from an electron because you have that tracker info. But if you have a displaced electron that only shows up in the calorimeter, you have no way to know if that is just a photon. So in some ways, the sort of concentric nature of our detectors is inherently looking for prompt particles. But it's also very much the trigger system. So for example, the fact that we can't use the tracking information in our trigger for the most part makes it extremely hard to specifically trigger on most of these events, especially in the SUSY group. We rely very heavily on interdetector signatures, and none of the, almost none of the searches for SUSY, for long-lived particles with SUSY, rely on any triggers that specifically target displaced objects. And so you really do lose efficiency in a lot of cases because of limitations of the trigger.
Excuse me if I jump in. Out of curiosity, I had it even before this question. So the trigger, of course, is a limitation, but then what about the readout? I mean, let's assume you have a collision. Then at least in CMS, the tracker detector takes in a buffer up to 8 BX. So the signal from 8 BX, and then you throw away everything because you do not have the space. So anyhow, regardless of the trigger, because the tracker detector don't belong to the trigger system, anyhow, I can provide up to 8 BX info. So 8 times 25 nanosecond signal after such an amount of time is simply delete. So it's not just the trigger, I guess, but something behind. We don't know exactly the details of the Atlas detector.
Yeah, that's true. I mean, so that only applies, so that's relevant for basically cases where you have a very long-lived heavy particle, so it goes quite slowly, which is only a subset of the long-lived particle cases, but it's true. And also in Atlas, we have some work to sort of combine different bunch crossings to see if we can target some of those cases. We have, for example, late muon triggers and things like that. But there's, of course,
how many?
Sorry, how many bench crossings?
Yes.
I don't know the exact number. Maybe Monica knows, I'm not sure.
I thought it was 1.
Okay.
For the late muon trigger?
Yeah, there's that one, just 1?
I think so.
And then there's, yeah, there's some other things in development, but I also don't know the exact numbers that are, I don't know the exact number of bench crossings for those.
And another, out of curiosity, you know that in the LHC filling scheme, there are 3 microseconds of beam dump at the end of the fill, of the scheme. So there you know that you do not have collision. Are you somehow exploiting them, or even the empty BX between adjacent trains?
I would love to show results on that. I don't have them yet.
Stay tuned. Okay, thanks.
That's a stay tuned one.
Thanks.
Okay, thank you very much, Tova. I think we need to move on, and we are moving to Alice with Beatrice Gay. Beatrice?
I'm here.
Great.
It's fine?
Fantastic, yes.
Okay. So thank to the organizers to keep this presentation. I'm happy that this is a work that is being developed in Porto Alegre, Rio Grande do Sul, Brazil, with my student Bruna Carlos. So my talk is concerning magnetic monopoles in PP collisions. We would like to have a look at this in Alice, since part of my group is connected with this experiment, and we'll see what is going on in the future. So the outlook of my talk is that direct monopole and the quantization condition, effective couplings, monopolium, monopole production in PP collisions, studying Drell-Yan pair production, photon fusion pair production, monopolium production by photon fusion. We present also some interesting energy distributions and the perspectives in future accelerators. Everything starts with the Dirac monopole and the quantization conditions. Since in 1931, the Dirac showed that the magnetic monopoles are consistent with quantum mechanics. So introducing arguments concerning uncertainty of the wave function phase, he proposed a quantization condition, which is this one, Pg is for Pn, n being an integer, meaning a quantization condition. This monopole proposed by Dirac has some properties that doesn't make it very easy to work with. For instance, the undefined mass and spin, a heavy, big coupling like alpha m proportional to G2 much bigger than 1. This means that we cannot do easily calculations in perturbative approaches, meaning we have to work mostly with effective models for this monopole coupling. And indeed, there are some approaches that I would like to present to you. One of them is the velocity-dependent coupling, meaning the moving monopole will be treated as an electric charge, which enforces the EB symmetry. In this case, we take the monopole as in the place of an electron in many processes only by a replacement, like a GB, beta. And the perturbative expansions will be made only when we can assure beta is much slower than 1. And beta is related with this velocity. And then the K-dependent coupling, in which a magnetic moment is added to the GB coupling. And this magnetic moment will be given by the expression below, which also connects with the mass and the spin of the monopole. In this case, the perturbative methods can be employed in limits where Km much bigger than 1 and beta is smaller than 1. Then for the monopolium, which is a theorized bound state that connects a monopole and an antimonopole, the coupling will be just G, because the monopole doesn't couple to the photon, only to an antimonopole. So it is possible to introduce a potential with the form proportional to R minus 1, and includes an exponential with cutoff that relates with the mass of the monopole and antimonopole. So when considering the simplest case for the monopolium, which is the spin 0, the wave function for the ground state will be written as this expression you're seeing, where we can see both masses, the monopolium one and the monopole mass, plus the binding energy of the monopolium, in the case monopole, anti-monopole. Having that, you can move on and try to see those production in PP collisions, as well as for monopole and monopolium. And following the factorization formulation, the cross-section in PP collisions will be written as the expression that involves the distribution functions inside the proton, or photon flux, if it's the case of photon emitted by protons or quarks, and the fundamental cross-section of the subprocess in question. And also X1 is the fraction of momenta carried by the I particle. Having this in mind, you need to consider the cases for photon fluxes, which means that for the elastic collisions, I'm gonna have the written expression where Z is the fraction of energy carried by the photon, A is the final, and Q2 is related with the mass of the proton and this fraction of energy. For the inelastic collisions, which involves quarks inside the proton, you have this expression where we need to introduce the transfer of momentum maximum and minimum, which means Q2 and Q1 as presented in the transparency. Having this in mind, you can move to the calculation for the Drell-Yan production for monopole for the two different couplings, which means sigma Drell-Yan that introduces neta, which is the charge of the quark involved divided by E, and the magnetic moment dependence, this following cross-section that involves the K as presented before for the magnetic moment model coupling. Having this, we can think also on photon fusion now, the cross-section for the two coupling models that is velocity dependent, the first one, and the K dependent, the second one, which is a very heavy calculation and expression. which I have again to emphasize the presence of the obviously of the magnetic moment. Now I can show you the productions you can have, the sigma for the different, the distinct contributions, which is Drellian, the lowest one, followed by the composition of the cross sections, elastic, semi-elastic, and inelastic. Then you have the gamma-gamma total, which is the red higher one, for different masses of the monopole. This is what you can have for K equals 0 on root S 14 TeV. When you work on K equals 0, you are saying that you're just taking the velocity dependent model and not the magnetic moment introduced before. Here in the second plot, I can show you the gamma-gamma production, the photon fusion production for root S 14 TeV for different values of K, now 0 and Km, in fact, 1, 2, and 3. And we have this increasing in the production for photon fusion once you increase the value of K. And again, the red curve is just velocity dependent. And the next plot, you see for the different values of K, different values of M. And then what you can say is that the gamma-gamma has higher cross-sections for monopole mass smaller than 5 TeV. You have a limit for LHC detection around 3 TeV, and higher values of K give you higher values of cross-sections, as implied by this new approach that introduces the magnetic moment in the calculation. Now for monopolium, the spin zero production by photon fluxion, you have this expression for the cross-section that takes into account a value of R that is the root into M divided by the mass of the monopole and the decay rate, and also this epsilon introduced here. What you can have in this production is that it is increased for higher values of the monopole mass. Here you can see the different contributions, elastic, semi-elastic, inelastic, and total. The red one is the total cross-section for different values of monopolium mass, taking into account fixed monopole mass of 3 TeV. You can see this differently, saying that you fix the monopolium mass as 1 TeV, which is maybe lowest possible interesting case. And now you analyze this concerning the monopole mass, and this is the behavior you are going to have in this case. Now we can be interested in energy distributions, which means they take derivatives of those cross-sections, especially the center of mass energy of this sub-process. A photon root S. And here you can see for K equals 0, which means just velocity dependent coupling, which is not the most favorable one. you can have this behavior for Drell-Yan, which is the lowest contribution, then follow the elastic, semi-elastic, and inelastic contributions, and then the total one, the total contribution for this energy distribution. You can see the same distribution now, introducing the coupling with the magnetic moment. And then you're going to have for 0, this curve corresponds to that one. However, we have a different scale here, which is logarithmic. And then you have the following distributions for Km 1, 2, and 3 here. And then the monopolium production for M equal to 1 TeV, and the monopole mass of 3V. This is the behavior you are going to have for the different contributions on the total contribution. With that, we can say that for the monopoles in future accelerators, putting a detection limit as at least bigger than 1 per year. For LHC, high luminosity LHC root S 14 TeV on this luminosity, the detection limit will be around this value of the mass of the monopole. And then for high energy LHC, which means root S 27 TeV luminosity as that, the detection limit will be around mass below 6 TeV, around that. For future circular collider, which is this root S, the detection limit increases strongly, and it goes around 20, 21 TeV. And these are the plots that we can present for the different ranges of masses for the different possibility of detectors on the different processes, Drell-Yan and photon fusion in this case, and this for the fixed mass of the monopole as 3 TeV, the production of monopolium having this behavior for the 3 different possibilities, HL, ICHEP, FCC, respectively. And still here, I didn't comment, but this is K equals 0. So this is our some studies on monopole and monopolium that are starting to attire again, I would say, the attention of theoreticians and experimentalists. It's mostly open discussion, but in our case, we'd like to present the limits we can provide with cross-sections that are mostly indicative because they rely partially on perturbative methods, which is, I have to take this carefully for this kind of strong, heavy, so to say, big coupling. For current lower limits given by Murdoch and Atlas experiments, M bigger than 2 TeV monopoles have very few chances to be detected in LHC. For heavier monopoles, the detection maybe could happen in future accelerators, a direct detection, or indirectly for the monopolium. The K-dependent coupling, in fact, increases significantly at the cross-section up to 10 to the second times the value, and the limits of detection for LHC up to mass of 4 TeV. Thank you.
Okay. Thank you, Beatrice. Actually, we are several minutes over the time slot, so maybe let's defer the discussion for either the discussion session or Mattermost. And I'm afraid we have to move on now. So the last speaker of this section is James Penfold. James, are you around?
Sure, yeah. So I'll just share, okay?
Sure.
Let me just back to the beginning. Getting there. Can you see it?
Yes. Could you go full screen?
Okay. Just get that out of the way. So just want to move this window. There we go, full screen. Can you see that still?
We see still the same.
But it's probably coming. It's full screen on my screen here.
This is Mac, isn't it?
Yes, Mac, yeah.
There may be an issue with going full screen with a single window on a Mac. So
why don't I just go back to where I was before and
yeah, let's do that. Just do it in a window view.
Yeah. Now can you see that now?
Yes, we can.
Okay, so I'll just stick with that. Yeah, the Mac, I've always had trouble with the Mac. So let's start with the first slide, although that's not much information on it. So I'm going to tell you about the Myrtle map detector. It's the LHC's first dedicated search experiment deployed around the LHCb region. So here's the current collaboration. We've got 70 physicists from 5 continents, including India, from 14 countries. So we're a pretty diverse group. And we've been working away on run 2, producing limits on highly ionizing particles. Unfortunately, no discoveries, as you would have heard that by now. The metal baseline detector, which has been deployed for run 2, is a kind of unique collider detector. It's totally passive. It creates a permanent record of new physics. It's able to directly detect magnetic charge. We don't require a trigger because of the passive elements. This is because the threshold of the nuclear track device is so high, we eliminate most of the standard model particles, and we don't have any standard model physics backgrounds, although we do have backgrounds that can sort of fog the film rather than create new physics. The 2 new types of detectors are a trapping detector, where we have about 1 ton of aluminium that can slow down and trap highly ionizing particles, for example, magnetic monopoles or any other electrically charged highly ionizing particle. And we have a nuclear track detector system that essentially photographs the event, and any track that's got a higher threshold than about 5 times the minimum ionizing particles will be registered there. And we look for that as etch bits when those foils are etched after they've been exposed. So we look for those telltale signs of evidence using computer-controlled optical scanning microscopes with some machine learning. So what have we pushed out today? On the left, we can see the limits we've put out today, and we see the Atlas limits. I'll include the CMS limits and any Atlas limits as they come available. We see that we're just about squeaking up to 2 TeVs. A previous speaker said that 2 TeV seems to be a limit, but if we look at run 3, our estimates of run 3, we see we go above 2 TeV for the spin half. Now we've got to also consider spin 0 and spin 1. There's no spin being defined for the magnetic monopole. So what have we done today? We've got the world's best limits on multiply charged magnetic monopoles. The only limits on magnetic monopoles where we can distinctly discern that we do have magnetic charge. All the other limits just rely on high ionization. We also do high ionization, but we also look for the magnetic charge in squids from magnetic monopoles trapped in our trapping volumes. We've also produced limits on spin 0, spin half, but also spin 1 monopoles for the first time ever, I think, and we produced the first limits on photon fusion production of monopoles at the LHC. And we've also just getting published now the limit on dion production, where we know a dion is an electrically and magnetically charged particles predicted by Schwinger. And that's coming out now. And I think that's the first time anybody's ever put a direct limit on the dion. What else is in preparation? Search for highly ionizing electrically charged particles, or HECOs. Search for highly charged monopoles in the CMS beam pipe. Another interesting thing, considering comments made in the last talk, very nice comments, of course, very accurate, but we do also search for the monopoles produced by the Schwinger mechanism. That's using the intense magnetic fields in a heavy ion collision, and those monopole production is not subject to the problems of the large coupling constant that makes the calculation of the cross-section non-perturbative, which was alluded to in the previous talk. In this case, it's perturbed. There's no problem with the cross-sections calculated here, and also we would expect monopoles to be suppressed if they have finite size. And again, this Schwinger mechanism production doesn't suffer from anywhere near the exponential problem that, say, studying the Drell-Yang production does, or photon fusion production. We're also looking for highly ionizing particles, supersymmetric particles with a metal detector, and I'll talk a bit about that later. We're now preparing for run 3, and here we see the run 3 plan for LHC. I think a lot of us have seen. For run 3, for the first part of run 3, we expect just to redeploy the metal detector, as you've just seen, but also the first stage of the MAP detector. That's a metal apparatus of penetrating particles that will be primarily designed to detect mini-charged particles or milli-charged particles, but also some long-lived particles. And phase 2, later on in run 3, we will deploy MAP 1 as part of that process, and that will detect long-lived particles, competitive with experiments like Codex B and some senses Methuselah. And then phase 3 for high luminosity LHC will deploy MAP 2. So I'll tell you a bit about those detectors a little as we go on. So the metal LOI and TDR that describes that program was submitted to the LOI was considered by the LHC in Feb 2020, and they endorsed our physics program, and the TDR phase 1 is submitted in June 2020, and that was also encouraged and to carry on. But of course, we've all been hit by COVID, and that's delaying us quite a bit, but everybody's being delayed the same way. The metal MAP detector is shown here. We see on the left, let me point to that. On the left, we see the metal detector far off in the distance, and about 50 meters away from metal, we have the MAP detector, phase 1 here in the middle, and phase 2 around the outside. Here we see some sort of more schematic views of MAP 1, about 5 degrees, deployed about 5 degrees of the beam line away, and about 55 meters from metal. That will be deployed in run 3. And for high luminosity LHC, will have a much bigger map, which we call MAP 2. So what are we deploying? In run 3, we're deploying the baseline metal detector. We're deploying the inner core of the MAP detector, which is designed to detect mini charged particles, and a little later we'll be deploying the long-lived particle detector, which is comprised of fine-grained scintillator hodoscopes. The mini charged detector is comprised of hundreds of scintillator bars, given about 3 meters of scintillator to each mini charged particle that passes through, with 4 PMT coincidences to reduce noise. So the metal map physics program relies on detecting 3 very clear avatars of new physics: highly ionizing particles, which we've already been doing, long-lived particles, and mini charged particles. And each one of those is a problem, not a necessary, should we say, a challenge for the main LHC experiments. They were not optimized to detect those particles. Of course, they can do great work, and we've seen a lot of that. But when we push to very long-lived, when we push to very small charge and push to very highly ionizing particles, it's a challenge for the bigger experiments to be able to compete. Supersymmetry, the things we can do, we can look for supersymmetry, extra dimensions, other exotic particles, cue balls, strangelets, magnetically charged particles, multiply charged particles. But now with the long-lived and the mini charged particles, we can look at dark sector models and hidden valley models as well. So we expect an exciting expansion of our physics program. When we get to run 3, the first thing we'll do with the baseline detector is to push up the search to above 2 TeV. It isn't a limit for us, we feel. We feel that we can, 3 TeV is a better limit for LHC at run 3. And of course, when we go to high luminosity LHC, we go above 3, but we've got to be, but we haven't got that shown here. The other thing we can do with more, when we use our lower threshold nuclear track detectors, we can look for supersymmetric particles, say gluino production, where we have neutralino production that decays to a STAU and a tau. And when you look at that, some analysis, we pick here a particular atlas analysis. We see that when we look at C tau for the neutralino against the mass, you see these colors. The yellow section is the atlas search, and the colored sections above the yellow sections are various metals searches. And you can see that for long lifetimes, we can do better than this particular analysis. That's not saying, of course, that we can beat Atlas at SUSY, of course not. But in this one analysis, we have a sort of an area where we can push the searches that exist maybe a bit further. But the other great thing, of course, is we're totally trick-free, and our systematics are totally different than Atlas and CMS. So they make a really good, I think, complementary study to the main experiments. Carrying on with the phase 1 MAP mini charged particle detector, we can detect, for example, the decay of dark photons to mini charge particle pairs. Here we see on the left the mini charge. You can see it goes down to 10 to the -3, or thousandths the electric charge. And here we have the mass, and there's a vast unexplored area here. And this is what we can do with 3 inverse femtobarns, 30 inverse femtobarns, and 300 inverse femtobarns by way of illustrating our sensitivity. That is for 3 events seen. Another area where we would expect, should we say, lightly ionizing or feebly ionizing particles is with the heavy neutrino, which happens to have a large electric dipole moment. So using a light electric dipole moments are still not being excluded. We can carry on and exclude, for example, here we have electric dipole moment. Here we have the mass of the neutrino. We can exclude quite a large region of the allowed plane, up to 240 GeV. We can now move on to the next phase 2 of the MAP detector, which installs somewhere midway through run 3, where we install run 1. And here, using the Higgs portal, we look for new light scalars, decay to mu plus, mu minus. And on the top one, you can, at the top plot, you can see something involves sine squared theta, should we essentially say the coupling, and then the mass of the scalar on the bottom. And you can see Methuselah, which pushes down to very small couplings because it's able to detect very long-lived particles. But you can see that it doesn't, that it falls off at high, at shorter, smaller couplings. But if you look at MAP1 for 30 inverse femtobarns and MAP1 with 300 inverse femtobarns and MAP1 with 1 attobarn, you see that for 300 inverse femtobarns, we're competitive with Codex B, which is another competitor of ours, I think, and we're easily compatible with SHIP, doing essentially about the same as SHIP. Of course, I think our role is primarily, as we're an intermediate distance, is to fill in the space between, should we say, the main detectors like LHCb, shown here, and Methuselah. We cover the mid-range, so to speak, in quite a number of studies. And the study below illustrates that, where we look for the pair production of right-handed neutrinos from the decay of an additional Z0 Z boson. On the left, we see MAP1, that's only inverse, that's only 30 inverse femtobarns here, MAP1 against phaser, which is phaser 2, which is about 3 attobarns, I believe. But if we go to MAP2, which for 300 inverse femtobarns, we see that we again cover the space between LHCb and Methuselah. We are the sort of intermediate range experiment in this area. But nevertheless, those gaps exist, and while they exist, there's uncovered area. So we also want to deploy a small detector called the metal map detector, where we take our decay volumes, which we can actually look for, we can pass through squids to look for monopoles, and we stack them and look for the decays of electrically trapped particles, and we can push out to lifetimes of 10 years or more in this way. And this is a very uncovered area. No one's been in our, there's been a few searches for ultra long-lived particles, but we can push them further. And it's a very, should we say, a relatively uncovered area. And there are theories that push out here. For example, Feng has produced, here's a reference, a nice super WIMP model where the gravitino is the lightest supersymmetric particle, and he's predict there. For example, they predict a charged lepton, that can have about. I wonder if I can move this out of the way. I'll just have to wait for it to go. But there they could predict the particles that go out with a lifetime that's of around 10 years or so or more, and you can see this in the above plot. So wrapping up, for metal map run 3, we haven't talked much about beyond, but beyond exists by running for longer. If we look at metal, we were all sensitive to HIPs, highly ionizing particles, but not to weakly ionizing or long-lived. For beginning of TDR, our TDR phase 1 or the beginning of run 3, we will be able to include weakly ionizing particles to that list, and maybe some long-lived particles. And then with MAP1 a little later in run 3, we can look for neutral long-lived particles and charged long-lived particles with MOL. And then finally with MAP2 for high luminosity LHC, we can push long-lived particle searches out and help to fill in the gap between, should we say, LHCb type detectors and the Methuselah type detector. So overall, we cover all of the avatars of new physics that are clearly seen and are a little bit of a problem or a challenge for the main LHC experiments. Thanks.
Okay, thanks. Thank
I
you.
completed my talk.
Time for questions.
Hello, it's Mia. I have a few questions. The first one is slide number 5, where you have the schedule of LHC for the coming years. And then you have mentioned about your LLP detector to be installed in 2022. Since this LHC schedule is a little bit shifted because of the COVID, the crisis.
Yep.
So I'm wondering if you are in time for the LLP detector to be installed by the beginning of 2022, when we will expect LSC back.
Yeah, so I would say that just about, I'm also on Atlas, so I know most experiments have been delayed in their preparations to start running at run 3. So we would expect our module to be pushed as well by the order of 6 months.
I see. Therefore, LLP will not be ready at the beginning of run 3.
I think it will be, I suspect, ready for the last year of run 3, because it could be, if run 3 starts late, and we don't know that yet, it may be extended itself. So I think what we did is, what could we do? We shrugged and said, we can only show the schedule we have. But I would expect everything to be pushed up, but you know, who knows what will happen in the end. We expect to be able to deploy for run 3 in the last year of run 3. That's what we expect. But what the definition of run 3 will be, we don't know. We sort of suspect that run 3 will be extended and may start late because the other experiments are having problem wrapping up in the time that they have available. Certainly LHCb and Atlas, I don't know. CMS, I assume, is in I don't know, I can't assume what the position they're in because I don't have any connection with them, but we do expect, I would say the statement I would make is we expect to run in the last year of run 3 for MAP1 LLP. Having said that, we do have some ability to do long-lived particles with the with the MAP1 detector. Only the limits there will be a lot restricted because the MAP1 detector's got a smaller decay volume.
Thanks. Just a comment. As far as I know, the most recent updated schedule have the start of the machine in February 2022, while 2021 will be just commissioning for the machine.
Yeah. And that, of course, that's a significant delay from the.
But the end will be still 2024, in order to avoid extending the delay for round 4. But okay, thanks.
We expect to get in for the last year, or we're pushing to get in for the last year, but we expect things to be delayed. Is the answer? Yeah.
Yes, thanks. And then another question about, so you are looking for signal coming from LHC collision. Do you have the sensitivity for astrophysical sources?
Not quite sure what you mean by that. You're saying can we detect cosmic rays underground or something? Is that what you're saying?
Not really cosmics, but possibly beyond the standard model particles produced in the universe.
Yes, I mean, this may not be answering your question, but we're planning to deploy a nuclear track detector at higher altitude to search for monopoles, gut monopoles, and intermediate mass monopoles. I don't know if that answers your question. What we plan to do is to connect up with the monopole search at TV range and push it up to the gut level by deploying a large array at high altitude.
At high altitude, so in a different, okay, thanks. And very last
different location.
Okay, exactly.
We are now like pretty much over time, so maybe it's time to thank all the speakers of this session, and also all the brave attendees that are still here for their nice job. It was a great pleasure. And just to remind you, we are not finished yet. The Zoom room will stay open for at least the next 15-20 minutes for a discussion session, so we can still ask our speakers those questions that we couldn't respond to during the session. And let me just remind you that tomorrow's session will actually start in the morning of the Central European summertime at 8 actually. So we are kind of changing the scheme a bit. So don't forget to adjust your alarms. Okay, thank you once again. And now the stage is yours for questions, whatever.
Ana Rodriguez has raised her hand.
Yes, I was wondering if I could ask a question to Beatriz, if she's still there.
Here I am.
Hi. Yes, thank you for your talk. I work with a monopole search in Atlas, and we were wondering what role would Alice play in the future? What do you expect your systems in Alice how would you expect them to respond in terms of monopole detection? And yeah, if you could just say a few words, mainly about the detector and its sensitivity.
I cannot. I'm a theoretician.
Ah, I see. I see.
You see, I have colleagues, and I help them in the theoretical, in the experimental group, but I'm a theoretician. I cannot be specific on the detector, but I know people that can answer you this question in Alice, if you want.
Okay, thank you very much. So I'll probably send you an email to follow up on that. Thank you.
Can I ask a question of the Atlas speaker? Is anybody acknowledging?
Please.
Okay. Hi. So I know I'm on Atlas too. I should know a lot of these things, and I don't. But so this is why I'm asking you. I know Atlas will be going to an all silicon solution for high luminosity LHC, right? Hello.
Hi, this is Anna again.
Anna. Yeah.
I'm assuming you meant me. Sorry about that. Yes, there will be changes in the tracking system. Yes.
Yeah. So I know TRT. You probably don't know much about the monopole analysis, but maybe somebody listening does. So the TRT features strongly in the current monopole search, and that will be removed.
Part of that analysis. Yeah.
Sorry?
I'm part of the analysis.
Yeah. So when you get to high luminosity LHC, will you just change to another kind of detector system, or does that create a real problem for your analysis? I imagine you can scoot around it somehow. I'd be interested in knowing how you're going to handle it when you don't have the TRT.
Yeah, well, so far we don't have an answer for that. It definitely changes our analysis completely, because what we look for in the TRT is hits that pass a high threshold. And in that sense, we would have to have that GEDX basically, which we don't get with the new tracking system.
Yeah, that's what I thought. But yeah. I imagine you'll think of something. But
we're still concentrated on the current version of our analysis. But yes, it is something we have in the back of our mind. Yeah.
Okay. Thanks. And perhaps I can ask a question to get Beatriz too, which I'm sorry you may not be able to answer. It isn't very detailed. I was just asking, how would you detect your monopolium? Beatriz, if you're there.
Yes, it will be through the decay of the monopolium.
So you assume it just annihilates to a shower of photons or something? Is it? Is that what you mean?
Photon, mostly photon. I think so.
Yeah. Okay. Thank you.
Jim, this is Wendy from
Hi, Wendy.
Search. The D0 actually searched for I think a 2-photon signature from the monopole. Well, not the monopolium, but you know, so there is this indirect technique.
Yeah, I think that's got some theoretical questions, but yeah, that's a very, very valid thing to do anyway. That had some theoretical questions involved with it, but it's certainly something that should be done. At the LHC, I read the papers, of course, from Fermilab. So that is something you could do, and it sounds to me it's going to be similar to the monopolium. You're going to get just some heavy showers, EM showers. So
may I ask to James?
Yes.
Why do you focus on spin 1 monopolium?
No, we don't. I just said we do spin 0, spin half, and spin 1. But spin 1 has, I just said that hadn't been done before as far as we could see. People hadn't given any limits in terms of spin 1. That's all. That's what I said. We do spin half and spin 0, of course. We also do.
Thank you.
We also do beta dependent and independent because we produce that paper you nicely quoted there on photon, and also beta dependent and independent stuff is something we've looked at.
Maybe I can just go ahead,
sorry.
John. Finish.
I was just saying that I think an exciting thing that we can all look at, and particularly Atlas, is this heavy ion production. Now you could say, well, you know, that's very low luminosity and et cetera, but the nice thing about heavy ion, it's more like a barrier penetration process through the immense magnetic fields. And what it means is you don't get the exponential suppression. It's quite possible that the monopole has got a finite size, and I think most people expect it to have some sort of finite size. And that means you'll have exponential suppression of the cross-section. And this mechanism, the Schwinger mechanism, doesn't suffer so much, anywhere near as badly as the main Drell-Yan photon fusion methods of producing photons from that problem. So I think it's something every experiment should have a go at. That's my comment. Sorry, Wendy, carry on.
No, it's fine. Actually, since you mentioned that, the Schwinger mechanism, how do you model that in your detector? Like we use MagGraph to get all these events. So how do you do it?
Yeah, it's a good point. So we have a big bunch of theorists working on it. They're producing momentum distributions for us. It's a bit half-assed, I know, but we have the same problem that you have. It's very difficult to model such a process with MagGraph, right? Because you need Feynman diagrams. And,
yeah, exactly. So you're just, how are you calculating those distributions?
Well, we have a team of theoreticians. We have quite a lot of theoreticians in our experiment, and this is the theoretician involved you might want to talk to is Artu Rajanti from Imperial College, but he's also got 2 students working on the same problem. Oliver Goff, that's now in Helsinki, another metal group, and he's also got a student working on it called Andrew Ho, and they're all members of metal, but I'm sure you can get the same information that we can, and I would think it would be interesting for you to follow that up, because you get I don't know what your luminosity is for heavy ions, but it would be good for everybody to look for these things. The problem is that the momentum distributions seem to be a bit softer, obviously, and that may be a problem for Atlas because it's more massive, but it's certainly worth looking at. Yeah,
my student Wen Yi, she has done some calculations for the ultra-peripheral collisions. And from what she's found so far, it looks like the energies of those events are way too soft.
Yeah, they're way too. We're sort of lucky, but even for us, it's a bit of a challenge. We do have the beam pipe from CMS, which there they don't nothing. They don't have to penetrate at all. Really, just go. They can get trapped in the beam pipe. But so we have an opportunity to do that. But I think it might be a niche area for us. But it's maybe worth looking at. And certainly, if you want to know more, talk to Arttu Regenti. And I think these guys have come up with an approximation now for the Schwinger mechanism production that is slightly more momentum than we had before. We had our previous approximation gave us a very disappointing result, even for us, with our very minimum mass between the vertex point and the detector. We were still having trouble. Things were getting stopped in the LHCb silicon, for example. But now it's a lot better. So it might be worthwhile looking at it, as I say, for the obvious reason that it could be the cross-section so small using Drell-Yan that we're not seeing it because, you know, we don't have enough luminosity or something.
Yeah.
I mean, you may never have enough luminosity if it's suppressed exponentially, but this is not a problem with the Schwinger mechanism.
Thanks. Well, I've read his papers and we're aware of them, but so we would need to ask Arttu how he's calculating those momentum distributions.
Yeah, yeah.
Actually, can I perhaps ask a very naive outsider question about monopolium? I mean, what are the typical lifetimes there? Like for, say, one TV monopole, like lowest charge and so on and so forth. Just ballpark numbers.
Well, Beatrice is a person, I'll just answer for that. We've obviously had a big team looking at monopolium, and monopolium can essentially be collider stable in some models, incarnations, which makes it essentially neutral, a neutral object, or else it immediately decays via annihilation into photons. So I think there's probably a range of lifetimes. If you wanted to have it a long lifetime, you could probably do it. And if you want, and if you need a short lifetime, you could do that as well. It's my experimentalist sort of pseudo phenomenologist type answer. Okay, but I can certainly send you, if you want to just drop me a line, I can send you the papers on it. But theoretically, there's no problem with making it long-lived. You may not, one may not like that, but also most people expect it to immediately annihilate.
Okay. So if I can add something.
Certainly, I'm certainly know, Beatrice, you know more than I do about it, I'm sure.
No, you know more than me. Just to say that will depend also on the case, if it's 1/2, 0, 1. Yes. So this is so much of an open problem. So you don't have a definite figure how long it will live. It will depend on the case again, but we are looking mostly on photon decays, decay on photon, which is the most favorable process.
Okay, thank you very much.
I have a question for Beatrice, if that is more of a theoretical question, if you don't mind, about the beta dependence.
Again?
So the beta dependence of the coupling that you have, right?
Yes.
And
yes,
you know, yes. I know that metal uses that as well. In Atlas, we stopped using the beta dependence about 7 years ago because the argument, my understanding is the argument that leads to the beta dependent monopole photon coupling also implies that the fine structure constant would be beta dependent. Can you comment on that from a theorist perspective?
I didn't hear the second part of your question.
That if you have beta dependence in the photon monopole coupling, you would also have it in the fine structure constant, the electron photon coupling.
Ah. Well, I don't see exactly why we should, because in fact, the idea is the idea from Dirac is a replacement, which means no, I don't see this full connection.
I mean, we don't have to get into the details right now, but the beta factor originates from the Lorentz force law, right? So when you, so in the Lorentz force law for electrons in a magnetically charged field, you also have a magnetic field, you also have a beta dependence. So even though so you do this EB symmetry, and that takes your beta and gives you that dependence in the DEDX formula. But I think it doesn't actually imply that it should also be in the photon monopole coupling.
And what would be the problem to have this in the?
Well, the only problem is that the argument is, I guess, flawed. And in reality, it just when you put the beta dependence, it enhances your cross sections. If you take it out so that, there's no beta dependence, then your cross sections are a bit smaller, but ultimately that leads to a more conservative limit when you do your experiment.
It enhances, it cannot be that direct that it enhances, because you can only rely on those calculations if beta is small. So it's not a direct dependence.
No,
but this is not your main point. I understand this is not your main point in the discussion.
Anyway, it was just something, because what's happened now is Atlas is everyone's using the beta dependence. We dropped it, and so I know Metal offers results without it as well. But so it's nice to just turn it off.
Yeah. Did you see the paper that was produced? Well, the theoreticians involved were Nicholas Mavromatos. Did you see that paper where we did discuss the beta dependent coupling quite extensively? And I think
the one with Stephanie Baines, right? Yeah.
Yes, with Stephanie Baines. It's a nice. I don't think that particular problem was addressed directly in the paper, but what I can do is get Nick to have a look at that. Right? I don't think so, but it's an interesting point, and it will be good to, as an afterburner for that paper, to discuss that particular problem. So I can get back to you on that.
Okay, thank you.
Me too, because I'm using, in fact, I'm inspired by this Baines paper on the issue of the magnetic moment. But maybe I didn't follow all the details concerning the beta. Yeah. Okay. Yeah. I go through that more carefully. So this is so to say, I'm a heavy quark person, physics-wise. It's the first time I'm studying this subject of monopoles, which means I'm learning now. So the motivation is that there are so few works on that it's indeed very important to go more deep on that subject.
So I can certainly, that's a very nice theoretical question. So I think you'll have an answer pretty quickly.
Hello, Michael. Hello. Hello.
Yes, we can hear you.
Yeah. So the meeting is over. So should I stop the streaming?
Yeah, I think now maybe it's a good time to do it. I mean, let me ask the attendees. I mean.
Okay. Sure.
Yeah. So I think we are pretty much over now with the discussion section, at least the one that's taking place in our Zoom meeting. So I would like to thank all of you again for this nice and refreshing discussion, and see you tomorrow again.
Thank you. Goodbye.
Bye-bye.
Bye.
Bye.
I wish I could have been in Prague, by the way.
Bye-bye.
In 4 years, maybe. Okay, bye-bye.